Chapter 1 Fundamentals of Thermodynamics. Section 1.1 What is thermodynamics? Thermodynamics is the study of the transformation of energy and the behavior of matter on a macroscopic scale. What is a macroscopic object? A macroscopic object often contains many atoms or molecules. For example, 7-gram helium gas contains 10 to the power 24 helium atoms. Even just 1 nanogram of water contains about 10 to the power 14 atoms. So these two examples are macroscopic objects. If we study the transformation of energy and the behavior of this helium gas, or just 1 nanogram of water, it's thermodynamics. Conversely, quantum chemistry study only one or several atoms or molecules. That's called microscopic level. For example, we can study the vibration of one water molecule. We can study the energy of a water cluster that contains 2, 3, 4, or 10 water molecules. And that's quantum chemistry. We'll have to solve the Schrodinger equation for water molecule or 2 water molecules to get the energy and some other properties of individual water molecules. There's a bridge between quantum chemistry and thermodynamics. It's called statistical thermodynamics. So for example, if we study quantum behavior of one water molecule, we can use statistics to extrapolate the behavior of 1 mole water molecules. And we can also study the same system via 2 different methods, quantum mechanical and thermodynamic. The reason is, when we look at this diagram, this is the evaporation and condensation of helium. This is liquid helium, and we have moving helium atoms in the gas phase. We can either study the property of individual helium atoms, or we can use statistics to look at the collective behavior of many helium atoms in the gas phase and in the liquid phase. So we can study the same system using quantum mechanics or use thermodynamics. Again, there's a bridge between these 2 studies. The bridge is statistical thermodynamics. Again, thermodynamics is the study of the transformation of energy and the behavior of matter on a macroscopic scale. Whatever we study, it's the system. And the rest of the universe is the surroundings of the system. Between the system and the surroundings, there's a boundary. The boundary does not contain matter. The boundary does not contain any atoms, molecules, or particles. It's not a physical entity. The boundary is neither a part of the surroundings nor a part of the system. Now, we can tell the system plus its surroundings is equal to the entire universe because of the definition of the surroundings. Again, the definition of the surroundings is the rest of the universe. So if we look at some thermodynamic properties such as heat or work, we have these 2 equations. The heat flows into the system plus the heat flows into the surroundings is equal to the heat that flows into the universe. We're going to assume the universe is an isolated system, so heat does not flow into or out of the universe. Therefore, Q sub universe should be 0. And therefore, we have Q system plus Q surroundings is equal to 0. Similarly, the work done on the system plus the work done on the surroundings is equal to the work done on the entire universe, and that has to be 0. There are 3 different kinds of systems: open system, closed system, and isolated system. What are the differences? We look at 2 important features. We look at if there's any matter exchange between the system and its surroundings. We look at if there's any energy transfer between the system and its surroundings. An open system may have matter exchange and energy transfer with the surroundings. For a closed system, there's no matter exchange, but it's possible to have energy transfer. For isolated system, there's neither matter exchange nor energy transfer. We're going to study many thermodynamic properties in this class. For example, pressure P, temperature T, volume V, entropy S, and also internal energy U, enthalpy H, Gibbs free energy G, and Helmholtz free energy A. We will also study heat capacity, chemical potential, denoted by mu here, in thermodynamics. And those thermodynamic properties or functions, they depend on each other. For example, enthalpy H is defined to be U plus PV. Helmholtz free energy, or simply Helmholtz energy, is defined to be U minus Ts. Gibbs energy is defined to be enthalpy minus Ts, temperature times entropy. Again, this is just the definition of the Gibbs energy or Gibbs free energy. And we know H is U plus PV, and also we know A is U minus Ts. So we can have some other equations. The changes in this thermodynamic properties of a system are always governed by the laws of thermodynamics. In sections 2, 3, 4, and 5, we will introduce the zeroth law, first law, second law, and third law of thermodynamics. Chapter 1, Fundamentals of Thermodynamics. Section 1.1, What is thermodynamics? In the previous video, we covered the essence of thermodynamics and briefly mentioned a few thermodynamic properties such as pressure and temperature. In this video, we will show that the pressure and temperature of a gas is determined by the collective behavior of all gas particles in the system, using several example problems. So first example problem in this section 1.1.1, we'll calculate the pressure of 1 mole helium gas in a 27-liter cubic container. We'll assume the speed of every helium atom is 600 meters per second in the X, Y, and Z directions for easier calculation. So now let's look at this container. It has a side length of 0.3 meters. 0.3 meters to the power of 3 is 27 liters. Now let's focus on one helium atom. This helium atom is moving towards this shaded area at a speed of 600 meters per second. It's about to collide with this shaded surface area, change its direction, and then collide with the opposite surface, and then get back to the original position. It will keep doing this, collide with the surface on the right hand side, and then collide with the surface on the left hand side, get back to the original position, and it's going to start a new cycle of collisions. Now first, we'll calculate the time period for each collision. This particle moves at 600 meters per second in this direction, and the side length is 0.3 meters. This particle will have to travel 0.6 meters to get back to the original position. So that means it takes 1 millisecond for this particle to complete one cycle of collision. During 1 millisecond, there's one collision between this particle and this shaded area. So during a 1 second period, this helium atom may collide with this shaded surface area 1,000 times. In each collision, the momentum of this helium changes. This is because although the speed remains constant 600, the direction of the velocity of the motion of the particle changes. So you can say it changes from 600 to negative 600, or from negative 600 to positive 600. Anyway, the magnitude of the change of the velocity is 1200 meters per second. So there is some momentum change to this helium atom in each collision. And now within 1 second, there are 1,000 collisions. So we can calculate the total momentum change caused by the collisions, which is just 1,000 times the mass of helium times 1200 meters per second. Again, this 1200 meters per second is twice the speed of the helium, because again, the direction of the helium changes before and after the collision. Now we have the force calculated using this equation. Force times delta T is equal to mass times delta V. So this is from Newton's law. We just need to divide this m delta V by delta T. Within 1 second, there are 1,000 collisions times mass times the velocity change. And by the way, this is the magnitude of the velocity change, and divided by delta T. And then we get this expression, mass of one helium atom times 1200 kilometer per second squared. Alright, this is just one atom. What if we have one more helium atoms? We just need to take account the collective behavior of all atoms. All atoms are moving around, and then each of them is keeps colliding with this shaded area, again 1,000 times per second. So we can calculate the force by multiplying this expression by Avogadro constant. How do we multiply the mass of helium by Avogadro constant? We'll simply get the mass of 1 mole helium, which is 4 grams, or 0.004 kilogram. Kilogram is the SI unit of mass. That's why we're going to use kilogram here. Therefore, the force is the mass of 1 mole helium atoms times this 1200 kilometer per second squared. We get 4,800 newtons. Remember, 1 newton is 1 kilogram meter per second squared. Now we can calculate the pressure, because pressure is the force divided by the area. We have force on top, area on the bottom. We get 53 kilopascals. This is roughly 0.5 bar. We can also calculate the temperature using ideal gas law, PV equals RT, because we have the pressure calculated, 53 kilopascal. We have the volume, 27 liters, converted to 0.027 cubic meter. And then we have the number of moles. We have the gas constant on the bottom, 8.3 joule per mole K. We can compute the temperature of the gas, 173 Kelvin. So from the speed of a helium atom, somehow we get the pressure, 53 kilopascals, and the temperature, 173 Kelvin, by looking at the collective behavior of all gas particles. Now, let's do more quantitative analysis. What if the speed of all helium atoms doubles? Let's go from 600 meters per second to 1200 meters per second. What happens to the pressure? What happens to the temperature? It's pretty simple. When the speed doubles, the momentum change of the helium due to the collision also doubles. So before, it's going from 600 to negative 600. Now it's changing from 1200 to negative 1200. Therefore, the momentum change of each collision doubles. In addition, the number of collisions per second doubles. It's just because this particle moves faster, twice the speed. That means it takes now only 0.5 millisecond to complete an entire cycle of collision. Within 1 second, there will be 2,000 collisions. The number of collisions doubles, and also the momentum change doubles. Consequently, the force exerted on this area quadruples. And since we have the same area, the pressure quadruples. Using PV equals RT, the temperature quadruples. And actually, we know that the temperature of a gas is a measure of the average kinetic energy of the gas particles. So it makes sense the kinetic energy is proportional to v squared. Therefore, when the speed doubles, the temperature and the average kinetic energy are supposed to quadruple. For simplicity, we assume that all gas particles move at a constant speed v. So in the previous examples, 600 meters per second in each dimension. And what about the expression of the total kinetic energy of all those atoms? Well, it's pretty simple. We have n atoms. We have 3 dimensions. In each dimension, it's 1/2 mv squared. So we have this formula. And in general, the gas pressure caused by collision can be expressed this way. Pressure is force over area, and force, again, it's just delta P over delta T if you have only one single helium atom. Delta P is the magnitude of the change of the momentum of a single helium atom. But now what if we have n such atoms? We put n here, and delta P is the momentum change. It's 2 mv rather than 1 mv due to the change of the direction. So the velocity goes from mv to negative mv. So the change, the magnitude of the change is 2 mv. What about this delta T? Delta T is the time period. So it's the amount of time it takes for a helium to collide with the shaded area and then collide to the opposite surface and then get back to the original position. It's 2L over V. So putting everything together, we get this simplified expression for pressure. The number of helium atoms is uppercase N. M is the mass of one helium atom, and then V squared. V is the speed of a helium atom in the X direction or Y direction or Z direction. On the bottom we have V. Why do we have V? Because we have L here, we have A here. L is the side length and A is the area. A times L is the volume of the container. Alright, and also we know temperature is PV over NR for ideal gas. And then we can plug in the expression of P. P is this. We're plugging in here, we get temperature. Temperature is equal to the number of helium atoms times the mass times V squared over NR. Now you can see actually temperature is proportional to this V squared. Again, when the speed doubles, temperature quadruples. What about the total kinetic energy of all particles? We have 3/2 N mv squared. N is the number of atoms. And why 3/2? This is because we have 3 dimensions. And then we have this equation that can be used to compute temperature given the speed of individual helium atoms. Again, I want to emphasize this temperature is proportional to the total kinetic energy. Temperature is proportional to this mv squared. So again, if we assume all gas particles move at a constant speed v in each dimension, we have this equation, and we can divide this equation by the number of moles. We get this equation. This is just because the number of atoms divided by the number of moles is Avogadro constant. Avogadro constant is 6 times 10 to the power 23. Now both sides further divided by the Avogadro constant, we have this 3/2 mv squared is equal to 3/2 kBT. On the left hand side, we have the kinetic energy of one individual atom. Again, 3/2 mv squared because there are 3 dimensions. In each dimension, it's 1/2 mv squared. Alright, over here we have 3/2 kBT. Kb is the Boltzmann constant. We can see from here R divided by Avogadro constant is K sub B. So we can calculate the Boltzmann constant. It's this ideal gas constant divided by this Avogadro constant. The result is 1.38 times 10 to the power of negative 23 joule per Kelvin. Now the kinetic energy of each particle is 3/2 kBT in 3 dimensions, or you can say 1/2 kBT in each dimension. Later in chemical kinetics, we can prove the average kinetic energy is 1/2 kBT by assuming a more realistic Boltzmann distribution of velocities. So in this Boltzmann distribution, the particles do not have to have the same speed. They can have a wide range of speed in each direction. Now here's another example problem. We can calculate the temperature of 1 mole helium gas in a cubic container, but this time let's just assume the average kinetic energy in each dimension is half kBt, and we're going to use this equation. So again, in each dimension the kinetic energy is 1/2 mv squared. It's also 1/2 kBt. We'll prove this actually in chemical kinetics for a wide range of distribution of speed. But now let's just use this equation. By using this equation, we can see temperature is just mv squared over kb. It's not easy to actually get the mass of a helium atom. It's just because you need to use 0.04 kilogram divided by Avogadro constant. So why don't we multiply the top and bottom by the same constant, Avogadro constant, and this m is converted to the molar mass, and this case of B is converted to ideal gas constant. So this is a lot easier. When you do numerical calculations, we have just molar mass times V squared over R. This is a molar mass of helium. Again, gram is a non-SI unit, kilogram is the SI unit of mass, times V squared divided by R. We get the temperature 173 Kelvin. That's the temperature of the gas. Just based on this information, the speed of helium is 600 meters per second, and by using this equation. All right. So in general, we have this on average, the three-dimensional kinetic energy of a gas particle is 3/2 kBt. We'll prove this in chemical kinetics, but for now we'll just use this formula, and we can see that we can compute the three-dimensional root mean squared speed for those ideal gas particles such as helium using this equation. Again, this is three-dimensional, that's why you see a 3 here. And kb over lowercase m is actually this r over the molar mass. Make sure you use SI units for all three properties, R, T, and M. You'll be able to get this three-dimensional root mean square speed also in SI unit, which is meter per second. Alright, I want to show you the distribution of the three-dimensional speed over here. So if you look at this graph, there are three different temperatures: 100 Kelvin, 1200 Kelvin, and 3000 Kelvin. On the vertical axis, it says number of particles. On the horizontal axis, it says speed in meter per second. Again, this is actually three-dimensional speed. So from this graph, you can see actually we have more particles with this speed at 100 Kelvin. This is a little above 400 meters per second. When you have a higher temperature like 1200 Kelvin, we have a larger, most probable speed. So this labeled number 1, this is most probable speed. Even higher temperature, we have even higher most probable speed. What about number 2, number 3? Later we'll see. Number 2 is the so-called average speed, and this number 3 is the root mean squared speed. So root mean squared speed is over here. It's close to 600 meters per second at this low temperature, 100 Kelvin. When it's 1200 Kelvin, the root mean squared speed goes up. Again, it tells you at a higher temperature, the molecules in general move faster, but they do not have the same speed. There is a distribution of the speed. Chapter 1, Fundamentals of Thermodynamics. Section 1.2, the zeroth law of thermodynamics. It states that if two systems are both in thermal equilibrium with a third system, then these two systems are also in thermal equilibrium. For example, in this diagram, if A and B are in thermal equilibrium and B and C are also in thermal equilibrium, we can conclude that A and C are in thermal equilibrium. Let's define thermal equilibrium. A and B are in thermal equilibrium only if first A and B have the same temperature And 2, A and B are in thermal contact. That means A and B can exchange energy freely via the form of heat. Heat can flow between A and B. The zeroth law of thermodynamics may be extended as follows. If two systems are both in thermodynamic equilibrium, then with a third system, then these two systems are also in thermodynamic equilibrium. What's the difference between a thermal equilibrium and thermodynamic equilibrium? So in a thermodynamic equilibrium, the two systems must have the same temperature, pressure, and compositions. These two systems can exchange both matter and energy freely. In the end, if two systems can freely exchange matter and energy, they will eventually reach thermodynamic equilibrium. And this is dictated by the second law of thermodynamics. Chapter 1. Fundamentals of Thermodynamics. Section 1.3. The first law of thermodynamics. It states that energy cannot be created or destroyed. A misconception many students have is that energy decrease of the system is the driving force of the reactions or physical changes of the system. And this is wrong, because first, energy cannot be created or destroyed. So energy can be transformed, but there's a law for the conservation of energy, and that's the first law of thermodynamics. There's another reason. Both exothermic and endothermic reactions may proceed. Both exothermic and endothermic physical change may proceed spontaneously. For example, when the temperature is above 0 degrees Celsius, ice melts spontaneously. When the temperature is below 0 degrees Celsius, well, water freezes into ice spontaneously. So these two physical changes, one is endothermic, the other is exothermic. Both can proceed spontaneously under different conditions. So in summary, the natural direction or the spontaneity of a chemical reaction or physical change has nothing to do with the energy decrease of the system or the energy decrease of the surroundings. After all, energy cannot be created or destroyed. This is dictated by the first law: energy must be conserved. So what's the driving force of the chemical reactions or physical changes? Well, it's entropy. And entropy is the measure of the dispersal of energy. Chapter 1. Fundamentals of Thermodynamics. Section 1.4. The second law of thermodynamics. It states that the entropy of an isolated system always increases until it reaches maximum. Because the universe is viewed as an isolated system, we say the entropy of the universe always increases until it reaches the maximum. What's entropy? The simplest definition of entropy is the measure of the dispersal of energy. There are many alternative expressions of the second law. For example, heat cannot flow from a lower temperature object to a higher temperature object spontaneously. Another expression is this: a heat engine that converts heat to work cannot achieve 100% efficiency. There are more different expressions in terms of thermodynamic properties: Gibbs energy, Helmholtz energy, internal energy, and enthalpy. For example, the Gibbs energy of a system always decreases until it reaches minimum under the constant temperature and pressure condition. We need to pay attention to the condition now. The Helmholtz energy of a system always decreases until it reaches minimum under constant temperature and volume condition. We can also use the internal energy and enthalpy of the system as the criteria for determining whether a reaction will proceed spontaneously or not. For example, the internal energy U of a system always decreases until it reaches the minimum under the constant entropy and volume condition. What about enthalpy? The enthalpy of a system always decreases until it reaches the minimum under the constant entropy and pressure condition. Again, we can use G, A, U, or H as the criteria for determining if a reaction or a physical change can proceed spontaneously, but we need to pay attention to the conditions. If you use G, it's gotta be constant temperature and pressure condition. If you want to use A, it's gotta be the constant temperature and volume condition. If you want to use U, it has to be constant entropy and volume condition. If you want to use H, it has to be constant entropy and pressure condition. So we can eventually prove all those statements are equivalent to each other. But in the end, we just need to remember the essence of entropy first. It's the measure of the dispersal of energy. And number two, we just need to remember the original form of the second law of thermodynamics. The entropy of an isolated system always increases until it reaches maximum. Chapter 1, Fundamentals of Thermodynamics, Section 1.5, the third law of thermodynamics. The third law of thermodynamics states that the entropy of a perfect crystal at 0K is 0. There is a slightly different expression. The entropy of a system is minimized at 0K. These two expressions are slightly different. Let me use an example. If you have a diamond at 0K, its entropy is 0 based on the first expression. But based on the second expression, we can only say its entropy is minimized at 0K. But we do not know the absolute value of the entropy of this diamond at 0K. The first expression is more commonly used because it provides a zero reference. We know the entropy value is 0 for this diamond at 0K, and we can use this information to calculate the entropy of the same diamond at room temperature or other temperatures. So it's more convenient in physical chemistry. But Heisenberg told us we do not know the positions and momenta of the nuclei and electrons in a system exactly at the same time. So there's always some disorder associated even with a perfect crystal, even at 0K. So can we say for sure its entropy is exactly 0? I don't know. But it's common to choose a zero reference for convenience in thermodynamics. So it's more convenient to just say, well, the entropy of diamond is 0 at 0K. And let me give you two other examples about zero references. We learned enthalpy, we learned Gibbs energy, but we will never know the absolute value of enthalpy or Gibbs energy of any object in this universe. Because they are relative quantities, we have to set some zero references first. So for convenience, we say this: at room temperature, the standard enthalpy of formation and the standard Gibbs energy of formation of pure elements in their most stable states of aggregation are set to 0. For example, if you have 1 mole helium gas, 1 bar pressure, and it's pure, and then at room temperature we say its standard enthalpy of formation is 0, its standard Gibbs energy of formation is also 0. And based on this information, we can even calculate the standard entropy of formation for helium at room temperature. This is because H is equal to G plus Ts. That's the definition of Gibbs energy. Gibbs energy is enthalpy minus temperature times entropy. So we can use this derivation to get this standard enthalpy of formation is equal to the standard Gibbs energy of formation plus the temperature times the standard entropy of formation. At room temperature, T is 298 K, and for this pure helium gas at 1 bar pressure, its enthalpy of formation is 0, its enthalpy of Gibbs energy is 0, therefore its entropy of formation is also 0. But again, based on the third law, we say, well, if you have a perfect helium crystal at 0K is 0, but over here it says, well, the entropy of formation of a helium gas at room temperature is 0. Which one is correct? Actually, both are correct. It's just because we used a different zero reference. Over here we say the helium crystal at 0K. That's the zero reference. When we talk about the entropy of formation, the standard entropy of formation, we actually use pure elements in their most stable state of aggregation. We use room temperature. We use this as zero reference. But again, I mean, no matter which zero reference you choose in your calculations, in your derivations, please make it consistent. You just choose one set of zero references and stick to it. Again, the third law of thermodynamics states that the entropy of a perfect crystal at 0K is exactly 0. Again, this is more commonly used in thermodynamics. So for now, we'll stick to this expression. Now here's an example problem. Determine the entropy difference between 1 mole diamond and 1 mole graphite at 0K. So first I want to show you the structure of graphite. So those are carbon atoms. This is a graphene sheet, and there's another graphene sheet. There's a distance between the two sheets, about 3.6 angstroms. Over here, this is the structure, molecular structure of diamond. They look quite different, and these two have different density values. They have different molar volumes. The density of diamond is higher than the density of graphite, so that means the molar volume of graphite is greater than the molar volume of diamond. Can we just say, well, in this case, can we say the energy is more dispersed in graphite, and then graphite has a higher entropy than diamond? Well, the answer is no, because both diamond and graphite, they have a zero entropy at 0K, and therefore the difference is 0. Chapter 1, Fundamentals of Thermodynamics, Section 1.6, Pure Gases, Liquids, and Solids. In the ideal gas model, particles do not interact with each other. There is no attraction or repulsion between gas particles. However, real gas particles, they do interact with each other. They attract and repel each other simultaneously. For example, two helium atoms may repel each other and attract each other at the same time. How is that possible? Let's look at two helium atoms. We have a helium atom on the left, a helium atom on the right. They both have a positively charged nucleus and two negatively charged electrons. Now we can tell this nucleus and this nucleus repel each other. There are 4 electrons, they repel each other. At the same time, this nucleus is attracted not only by these 2 electrons, but also by these 2 electrons from the other helium atom. Therefore, we have attraction, we have repulsion. They both depend on the distance between these 2 helium atoms. When the distance is shorter, we have stronger attraction and repulsion. At the same time, when the distance is longer, we have weaker attraction and weaker repulsion. And because atoms repel each other, and this repulsion is due to the repulsion between the nuclei and also the repulsion between the electrons. If we try to squeeze 2 helium atoms toward each other, there's going to be a huge repulsion. That means each helium atom will have to occupy a certain space. And now we're going to use a numerical example to estimate the space a helium, but in this case, an argon atom occupies. We're going to estimate the volume of an argon atom given its van der Waals radius. R is 1.88 angstroms from literature, and we're going to estimate the density of solid argon with a face-centered cubic crystalline structure. So first, let's calculate the volume of one argon atom. We're going to assume this argon atom has a spherical shape. The formula is, well, 4 over 3 times pi r to the power of 3, and we plug in the value of r, 1.88 angstrom is 1.88 times 10 to the power of negative 10 meters. We do the calculation, the result is roughly 3 times 10 to the power of negative 30 cubic meters. Now if we imagine compressing 1 mole argon gas particles into the solid phase with a face-centered cubic crystalline structure with 74% closest packing efficiency, then we can calculate the volume. So first we have the volume of one argon atom, which is a sphere, multiplied by the Avogadro constant, and then divided by the packing efficiency. We'll be able to get the total volume of 1 mole argon in the solid phase. We got 22.6 milliliter. The density of solid argon can be calculated because we know the mass of 1 mole argon, we know the volume of 1 mole argon based on this calculation, and then we get the density 1.77 gram per liter. Let's compare this with literature value 1.68. These two values are really close to each other. Another numerical example, let's say we know the density of solid xenon 3.64 gram per milliliter, and now we're going to estimate the van der Waals radius of the xenon atom. So first, the volume of 1 mole solid xenon with the face-centered cubic crystal structure with this much packing efficiency is over here. So we have, this is the molar mass. It's from the molar mass of xenon. We're assuming 1 mole of xenon, so it's 131 grams, and we have the density of xenon. And now we have the volume of 1 mole xenon, 36 milliliters. Or we can say the molar volume of solid xenon is 36 milliliters per mole. And now we can compute the average volume of an individual xenon atom. So first we have this packing efficiency. So we have the molar volume times the packing efficiency, and then divided by the Avogadro constant, we get the volume of one single xenon atom. Now we assume this atom is spherical, and then we use this equation for the volume of a sphere. 4/3 times pi times the radius to the power of 3. We set it to be this volume. We can compute the radius of a xenon atom. It's 2.2 angstroms. For comparison, the literature value is 2.16 angstroms. Again, these two values are really close to each other. Another example, this time we'll estimate the van der Waals radius of water molecules. So obviously a water molecule is not spherical. It does not have a spherical shape. But still we can estimate its van der Waals radius as if it were spherical. For example, we can estimate the van der Waals radius of water is estimated to be 1.4 angstroms given the density of ice. How do we get this number? How do we calculate the van der Waals radius of water? Again, it's pretty simple. If we know the density of ice is 0.92 gram per milliliter, and we know the molar mass of water is 18 grams per mole. From these two pieces of data, we can get the molar volume of water. It's roughly 20 milliliters. And then 20 milliliters for 1 mole water molecule multiplied by this 34%, we get 6.8 milliliters. And this number divided by the Avogadro constant, we will be able to get the volume of one individual water molecule. Now we're going to assume it's spherical. Again, we're going to use this equation. 4/3 times pi r to the power 3 is equal to the volume of one water molecule. From this equation, we'll be able to calculate the van der Waals radius. Over here, if you click this, it's gonna bring you to a Wolfram Alpha page that shows you the whole calculation. And also you can just go to this wolframalpha.com and type up this equation. Again, this is a molar mass, this is density, this is packing efficiency. And why do we have this? Well, this is for unit conversion, and this is Avogadro constant, and this comes from the equation for the volume of a sphere. Again, this is just an estimate of the van der Waals radius for a non-spherical molecule such as water. Chapter 1, Fundamentals of Thermodynamics, Section 1.6, Pure Gases, Liquids, and Solids. In the previous video, we calculated the finite size of one xenon atom and one water molecule. And because of the finite sizes of those atoms and molecules, we need to modify the ideal gas equation, PV equals nRT. We need to replace this V to V minus MB. This MB takes account the finite size taken up by the atoms or molecules. V is the volume of the container. MB will give us the space being taken up by those gas particles. B is the size of one individual atom or molecule multiplied by Avogadro constant. So B is approximately the molar volume of the solidified gas. For example, if we solidify water vapor, it's just ice, and we know the molar volume of ice is roughly 20 milliliters per mole. Therefore, this parameter B for water is roughly 20 milliliter per mole, or 0.02 liters per mole. The modified equation will become this: P is nRT over V minus MB. And we divide the numerator and denominator by N, we get RT over molar volume minus B. And this equation shows that when B is larger, the pressure is larger. When B is smaller, the pressure is smaller. When the molar volume and B are close to each other, P becomes infinity. And that indicates the repulsive force when we try to squeeze two gas particles together. Now here's an example problem, 1.6.4. Rank the parameter B for helium, neon, argon, and xenon. Well, B is the measure of the size of the gas particles, and therefore the value of B of helium is the smallest. The value of B of xenon is largest. Now we rank methane, ethane, and propane. We can tell propane is larger than ethane, ethane is larger than methane. Again, B is a measure of the size of the gas particles. B also is a measure of the repulsive force when we try to squeeze two such gas particles together. Now, let's review this. When we take the finite size of an atom or molecule into account, we need to modify the PV equals nRT equation to this. P is now nRT over V minus MB. This equation often overestimates the pressure of the real gases, because between real gas particles there is not only repulsion but also attraction. If we introduce attraction into this equation of gas, it becomes P is equal to RT over molar volume minus B, and then minus, over here we have a attraction term A divided by molar volume squared. Also, we can rewrite this equation to be nRT over V minus MB, and then we subtract AN squared over V squared. the values of A and B are always positive. Again, B is the measure of the size of the molecule, and also B is the measure of the repulsion. And A, on the other hand, is a measure of the attraction between the gas particles. When A is larger, P is smaller. When A is smaller, P is larger. This is because the attraction between gas particles reduces the momentum change of the gas particles during collisions. Now let's rank the van der Waals parameters A for these four different atoms: helium, neon, argon, and xenon. Although they are all noble gases, xenon has the largest A due to the so-called dispersion force. It's just because xenon is larger than argon is larger than neon and helium, and since we have a larger radius in xenon, that means the valence electrons in xenon is farther away from the nucleus. It's easier to distort the shape of those valence electrons to create a so-called instantaneous dipole moment in xenon. And this instantaneous dipole moment can induce another dipole moment in another xenon atom nearby, and these two dipole moments may have attraction. Therefore, xenon has a larger A than the other three noble gases. For the same reason, propane has a larger A than ethane than methane. Now let's look at one numerical example, 1.6.6. We will use the van der Waals equation to determine which gas has a higher pressure, helium or argon. Remember, argon has a larger B than helium, and also argon has a larger A than helium. Well, this simply means the size of an argon atom is larger than the size of a helium atom, and also the attraction between two argon atoms is larger than the attraction between two helium atoms. These two gases, let's assume, have the same molar volume, 25 liters per mole. Let's assume the temperature is 25 degrees Celsius. We can easily calculate the ideal gas pressure, so I usually just use Wolfram alpha, and I actually type up the equation PV equals RT to get this ideal gas pressure. Now we're going to use this van der Waals equation. Again, we need to plug in the values of the van der Waals parameters A and B. So now, this is the van der Waals equation. Pressure is RT over the molar volume minus B minus A over molar volume squared. And then we plug in the values of A and B. For helium, the value of A is 0.03 bar liter squared over mole squared. The value of B is 0.0238 liter per mole. Again, this number, this parameter B, is actually the size of one helium atom multiplied by the Avogadro constant. We set up the same equation but different values of A and B. If you compare this B and this B, you can see argon has a larger B than helium, and also argon has a larger attraction than helium. So after plugging numbers, we got two different pressures: 0.9925 for helium, 0.9907 for argon. So for helium, its van der Waals pressure is greater than the ideal gas pressure. For argon, it's a little smaller. This is a little smaller than the ideal gas pressure, mainly because of the large attraction between argon atoms. Example problem 1.6.7. Use the van der Waals equation to determine which gas has a higher pressure, helium or argon. This time we have a different molar volume than example problem 1.6.6. So we have a larger molar volume here, and the ideal gas pressure, again, it's 0.09916. It's very close to this value, except this is just 10 times smaller, because this molar volume is 10 times larger. Now let's think about this. If we have a larger molar volume, those gas particles are farther away from each other than the previous example. That means we have smaller attraction and a small repulsion. So we predict the van der Waals pressures of helium and argon in this example should be really close to the ideal gas pressure. But again, let's just plug in the numbers. Pay attention to the units. For helium, we get 0.09917, just slightly above this ideal gas pressure. And for this argon gas, it's 0.09915 bar, slightly smaller than ideal gas. Again, all three numbers are very close to each other. It's just because although helium and argon are real gases, due to this very large molar volume, those gas particles are really far away from each other, and they have much smaller repulsion and much smaller attraction in this example problem than in the previous one. That's why the van der Waals pressure is really close to the ideal gas pressure. Also, we can look at the formula. So when this Vm is really large, B compared to molar volume can be neglected. And also, when this molar volume is really large, this A over molar volume squared can be neglected. That's why, when we have a large molar volume, the gases behave more ideally. Now another numerical example, problem 1.6.8. This time we'll look at HCl. And we put 2 moles of HCl in 50-liter container at room temperature. And now we're going to use the ideal gas law, PV equals nRT, and the more realistic van der Waals equation to calculate the pressure. We have the parameters A and B for HCl. You can get those values from the appendices, chapter 00, table of content and appendices. We have the molar volume here. We can easily calculate the ideal gas pressure, 0.9916 bars, using this formula. We can also calculate the van der Waals gas pressure by introducing parameters A and B in the equation. Again, it's RT over Vm minus B. So again, B take the finite size of the molecules into account, and A takes the attraction between HCl molecules into account. After we plug in the numbers, we get 0.9873 bars. So if we compare these two numbers, I think this van der Waals gas pressure is a little smaller than the ideal gas pressure, mostly due to the attraction between the HCl molecules. And now we can see the percent error of the ideal gas calculation is 0.44%. It depends on your goal. I mean, sometimes we say this is really small. We view this HCl as an ideal gas. But if you need a higher level of accuracy, we can look up the values of those van der Waals parameters A and B and calculate the van der Waals pressure of HCl, and this number 0.9873 is closer to the actual pressure of this real gas. Another numerical problem, still HCl, but this time we have 2 moles of HCl inside a smaller container. This time it's only 5 liters. And we still do the numerical calculation. Over here, if you click this, you'll get to this Wolfram Alpha page. You get ideal gas pressure 9.916 bars. It's just 10 times larger than the previous calculation when we have 50 liters. Okay, 50 liters, and now this one is 5 liters. And we also calculate the van der Waals gas pressure. Over here we get 9.486. This is the setup of the calculation, but I used Wolfram Alpha to do the calculation. You can see the real gas pressure is lower. That's because the attraction term overweighs the repulsion term. And when this molar volume is smaller, HCl molecules get closer to each other. That means we have larger attraction and also larger repulsion. And in this case, still, the attractive force is predominant. That's why the real gas pressure is smaller. Actually, in this case, it's significantly smaller. 9.5 is significantly smaller than 9.9. In rare cases, the attractive force and repulsive force may cancel each other, and then in that case, the van der Waals equation and the ideal gas equation result in the same number by coincidence. Chapter 1, Fundamentals of Thermodynamics, Section 1.6, Pure Gases, Liquids, and Solids. So first, let's talk about gases. What's the difference between a real gas and an ideal gas? Actually, there are three differences. In ideal gas, the atoms or molecules do not attract or repel each other. The size of individual gas particles is 0. All collisions between the ideal gas particles are elastic collisions. That means the total kinetic energy is conserved. But in a real gas, the atoms or molecules do attract and repel each other at the same time. The size of individual atoms or molecules is non-zero. For example, if we are looking at a helium atom, we can use its van der Waals radius to calculate the size of one helium atom. Also, we can estimate the size of one water molecule. This is pretty easy. As long as we know the density of water, we can compute the volume, the molar volume of ice, and then we use that molar volume of ice divided by the Avogadro constant. We get a rough estimate of the size of a water molecule. Number 3, the collisions between real gas particles are non-elastic. That means the total kinetic energy is not conserved. It might be transformed into potential energy or some other particles. Real gases can be condensed into a liquid or solid due to the attraction between those gas particles. Ideal gases cannot be liquefied because there is just no attraction between ideal gas particles. Over here we have a diagram of a gas, a liquid, and a solid. Over here it can be any diatomic molecule, but let's say this is a nitrogen 2 molecule. So we have a nitrogen gas. Under low enough temperature, we can make liquid nitrogen like this, and if we slowly lower the temperature for the liquid nitrogen, it can become a solid. This is nitrogen solid with a perfect crystalline structure. Now, what are the differences between the gas phase, liquid phase, and solid phase of a substance? So we look at these properties: the shape, volume, density, molar volume, net, intermolecular attraction, and kinetic energy. The first 3 entries are pretty simple. Molar volume, that's just the volume of the substance per mole. Usually, the molar volume of a gas is approximately 1,000 times larger than the molar volume of a liquid or solid, but it does depend on the temperature and pressure of the gas. At room temperature, 1 bar pressure, the molar volume of water vapor is about 1,000 or 2,000 times the molar volume of ice or liquid water. Now let's look at this intermolecular attraction. The attraction between atoms and molecules is usually strong in the solid phase and in the liquid phase, but it can be really weak in the gas phase. It's just because atoms and molecules are usually only 1 or 2 angstroms away from each other. but in the gas phase, the distance between two gas particles can be 10 angstroms or even longer. With a very long distance, gas particles, well, they still attract or repel each other, but the attraction and repulsion can be really small. Now, kinetic energy. Well, atoms and molecules do move even in the solid phase, but the motion is slow, the speed is slow, therefore they have smaller kinetic energy. In the liquid phase, well, they can move a little bit faster. In the gas phase, they usually move a lot faster than in the solid or liquid phases. For example, at room temperature, oxygen molecules, nitrogen molecules, they typically move at a speed of several hundred meters per second. Now let's look at one example: ice, liquid water, and water vapor. And if you look at the density of ice and liquid water are very close to each other. It's about 1 gram per milliliter. But if you look at the density of water vapor at room temperature, assuming 1 bar pressure, it's only about 0.7 milligrams per milliliter. It's a very small number. Again, this is 1,000 times smaller than this number or this number. Now let's look at the attraction between water molecules in the solid phase and liquid phase. They are about 40 kilojoule per mole. I put a negative sign here to emphasize its attraction. Usually we use a negative sign for attraction and a positive sign for repulsion. And this is net attraction, so that means it's attraction minus repulsion. Now let's look at the water vapor. The attraction is really small. It's only negative 0.04 kilojoule per mole under standard conditions. Chapter 1, Fundamentals of Thermodynamics, Section 1.7, Mixtures of Gases, Liquids, and Solids. First, let's look at a mixture of two ideal gases. For example, if we have two ideal gases, A and B, or helium and argon, we can mix them. And then we can use the ideal gas equation. P sub A is equal to N sub A times RT over V. P sub A is the partial pressure of A, N sub A is the number of moles of A. We have the same equation for B. And then we can calculate the total pressure. P total is simply P sub A plus P sub B. Therefore, it's actually N subtotal times RT over V. N subtotal is the sum of N sub A and N sub B. Note that A and B share the same container, they have the same volume, and also they have the same temperature. Now we can look at the mole fraction of these two components. X of A is the mole fraction of A. It's simply N sub A over N total. X of B is N of B over N total. XA plus XB is equal to 1. What if you have three components, A, B, and C? Still, the sum of the three mole fractions should be 100%. Now let's look at the partial pressure again, and this time we'll relate the partial pressure to mole fraction. So the partial pressure of A divided by the total pressure, you can see it's N sub A RT over V divided by N sub total RT over V. RT over V cancel, and then we have N sub A over N total. We have the mole fraction of A. Similarly, the partial pressure of B over the total pressure is equal to the mole fraction of B, and therefore we have these two equations. P sub A is simply X sub A times P total. P sub B is equal to X sub B times P total. P total is the sum of the partial pressures of A and B. Now let's look at a few numerical examples. 1.7.1. Calculate the partial pressures of nitrogen and oxygen in dry air at sea level. At sea level, the air pressure is 1 atm. For dry air, the mole fractions of nitrogen and oxygen is approximately 0.78 and 0.21, and therefore the partial pressures are simply 0.78 atm and 0.21 atm at sea level. Example problem 1.7.2. Calculate the partial pressures of nitrogen and oxygen in dry air that's compressed to 2 bars. So once it's compressed to 2 bars, we have an increase of the partial pressure for both gases, and we can still calculate the partial pressure by using the total pressure multiplied by the mole fraction. The total pressure is 2 bars. The mole fraction of nitrogen is 0.78. After the multiplication, we get the partial pressure for nitrogen, which is 1.56 bars. Similarly, we can calculate the partial pressure for oxygen. Example problem 1.7.3, calculate the partial pressures and mole fractions of N2O4 and NO2 at 100 degrees Celsius. Let's say the total pressure is 2.00 bars. The equilibrium constant for this reaction is 15. So we'll need to use this information. The equilibrium constant of pressures is 15, and we can set 2 variables. We say, well, the partial pressure of N2O4 is X bars. The partial pressure of NO2 is Y bars. Therefore, X plus Y is equal to 2. Now we know the equilibrium constant, 15. Therefore, Y squared over X is 15. The reason we need to square Y is because of the coefficient 2 over here. And we have 2 equations. We can solve these 2 equations because they contain only 2 variables. The solution is X is equal to 0.213, Y is simply 2 minus X, 1.787. And then we get the partial pressures for these 2 gases. Now, in general, for a mixture of many types ideal gases, for example, what if we have 100 different ideal gases? Then still the total pressure is the sum of partial pressures, and the partial pressure is the mole fraction times the total pressure. For species I, P sub I is simply X sub I times P total. And based on this equation, we can actually tell the sum of all mole fractions is 1. And also the sum of the number of moles of all species is N sub total. A gas mixture is always homogeneous. Well, we cannot say the same for liquids or solids. For example, if you mix water and oil, it's not homogeneous. If you mix gold and sand, it's not homogeneous. But sometimes we do have homogeneous solutions or even homogeneous alloy. For example, if we mix water and methanol, it's homogeneous. And if we actually melt sodium and potassium and then allow it cool down to be a solid again, this alloy is homogeneous. For homogeneous liquids and solid mixture, again, we can simply calculate their mole fractions by using the number of moles of sodium divided by the total number of moles, or we can use the number of water divided by the sum of water plus ethanol to get the mole fraction of each component. Now let's look at one example here. Example problem 1.7.4. Calculate the mole fraction of lauric acid and myristic acid in a mixture that contains 3 grams of La and 0.3 grams of Ma. I'm going to assume this is homogeneous mixture. You can actually heat up this mixture, 3 grams of La, 0.3 grams of Ma. You can melt them and then you can form a homogeneous liquid. Now let's do the calculation. What are the mole fractions? If you want to calculate the mole fractions, the first step is always to get the number of moles for each component. Over here we have 3 grams of La. We look up the molar mass of La, lauric acid, it's 200.3, and also we can just calculate the number of moles for Ma by looking up the molar mass of Ma. The calculation is straightforward. It's just mass over molar mass. We get the number of moles. Now the mole fraction of La is the number of moles of La divided by the total number of moles. We get 0.918. The number of moles, the mole fraction of Ma is simply 1 minus this because we have a two-component system. Now finally, what are this lauric acid and myristic acid? Those are just long carbon chain carboxylic acids. Chapter 1, Fundamentals of Thermodynamics, Section 1.8, Extensive and Intensive Functions. Extensive functions are proportional to the amount of the system. For example, mass, volume, energy, kinetic energy, potential energy, and the number of moles. So let's look at one example. If you have 2 bottles of water versus 1 bottle of water, the mass of 2 bottles of water is twice the mass of 1 bottle of water. The volume of 2 bottles of water is twice the volume of 1 bottle of water. Therefore, mass and volume depend on the size of the system. It's a little hard to imagine, but the energy of 2 bottles of water is also twice that of 1 bottle of water. How about number of moles? Same thing. Those extensive properties are proportional to the amount of the system, or you can say they are proportional to the size of the system, or you can say they are proportional to the number of moles of the substances in the system. Now, what about intensive properties? Intensive properties do not depend on the size of the system. For example, molar mass. Whether you are talking about 1 milligram of water or 1 kilogram of water, the molar mass is the same, 18 grams per mole. Also, you can talk about molar volume, molar energy, kinetic energy per atom, potential energy per atom, and density. They are all intensive properties. Again, another example, the density of water, it does not depend on the amount of water. Temperature, pressure, they are both intensive properties. How about concentration? It also depends on, it also does not depend on the size of the system. Let's say if you have, for example, 1% ethanol in water, all right, and then you have 2 cups of those 1% ethanol in water. You combine these two, what's the final concentration? It's still 1%. What if you have 100 such beakers? In each beaker, you have 1% ethanol in water. You combine 100 beakers. What's the concentration? It's still going to be 1%. Concentration does not depend on the amount of the system. So again, we can sometimes just compare 2 moles of water with 1 mole of water for a function. If the value of the function is different for 2 moles of water versus 1 mole of water, well, then it's very likely an extensive property. If the property does not depend on the amount of water, then it's very likely an intensive property. For example, concentration. Here's a numerical example, 1.8.1. We can calculate the molar concentration of pure water, assuming its density is 1 gram per milliliter. So we did not give the amount of water. It can be 1 milliliter, it can be 1,000 milliliters. It does not matter. If it's 1 milliliter, then the water weighs 1 gram. We can convert 1 gram to moles, and then we use moles divided by 1 milliliter. Work out the concentration, 55.5 molar. Or you can assume the amount of water is 1 liter. If you have 1 liter of water, you have 1,000 grams. You can convert 1,000 grams to the number of moles and then divide by 1 liter. You'll get the same concentration. The detail of the calculations can be found here if you click this wolframalpha.com webpage. Again, it's the molar concentration or density of 2 moles of water twice the concentration or the density of 1 mole of water. No, the answer is no. Whether you have 2 moles, 1 mole, or 1,000 moles of water, the concentration is the same, the density is the same. So in summary, extensive and intensive functions have this kind of relationships. You can sum up or you can subtract one extensive property from another. Extensive plus minus extensive is still extensive. For example, if you have 5 grams, 10 grams of water together, you have 15 grams of water. Mass plus minus mass, you get mass. It's extensive. And then you can do intensive properties plus minus intensive properties. The result is still intensive. But never add extensive property and intensive property together, because the units won't even match. For example, density is intensive, mass is extensive. Can you add 5 grams and 3 grams per milliliter? You cannot do that. Again, the units won't even match. What if you have extensive divided by extensive? The result is going to be intensive. This is because both the numerator and denominator are proportional to the amount of the system. But when you do division, they cancel. What if you have extensive divided by intensive? The result is extensive, because on the top it's proportional to the number of moles. On the bottom it does not depend on the number of moles. Therefore the result is extensive. What about intensive divided by intensive? It's going to be intensive. For example, let's look at the ideal gas law. PV equals nRT. What about pressure divided by temperature? P over T is nR over V. Actually, nR over V is intensive. It does not depend on the amount of system. You might say, wait, doesn't this N, the number of moles, depend on the amount? But also V depends on the amount. So if you think about this, if you have nR over V, both the numerator and denominator are proportional to the amount of the substances. So nR over V is actually intensive. Also, nR over V is actually R over the molar volume. Molar volume is an intensive property. And finally, intensive times intensive is gonna be intensive. In thermodynamics, the most important thermodynamic functions are internal energy, enthalpy, Gibbs energy, and Helmholtz energy. U, H, G, and A, they are all extensive properties. They depend on pressure, volume, temperature, and entropy. Among these 4 variables, pressure and temperature are intensive. Volume and entropy are extensive. So if you have 2 moles of helium gas versus 1 mole helium gas under the same condition, well, the entropy of 2 moles of helium is twice the entropy of 1 mole helium. Over here we have a wheel of thermodynamics that shows you the relationship between U, H, and A and G. So those equations are pretty much the definition of those thermodynamic functions. H is just defined to be U plus PV, and G is defined to be H minus TS, and A is defined to be U minus TS. We can derive the other equations. So again, this is the wheel of thermodynamics that illustrates the relationships between UH and AG. So now let's look at one equation over here. P is intensive, V is extensive, so P times V is extensive. It does depend on the amount of the system. It's proportional to the amount of the system. U is also extensive. Now we have extensive plus extensive, therefore H is extensive. So again, U, H, G, and A are extensive. Pressure and temperature are intensive. Volume and entropy are extensive. Now more of those thermodynamic functions. This time we're going to look at molar internal energy, molar enthalpy, molar Gibbs energy, and a molar Helmholtz energy, molar volume, molar entropy. All of these are intensive properties, because whenever we say molar, we have to divide the property by the number of moles. For example, U sub m is the internal energy over the number of moles. Both U and the number of moles are extensive properties. So after we do the division, the result does not depend on the amount. So in this wheel of thermodynamics, you see molar internal energy, molar enthalpy, molar Gibbs energy, and molar Helmholtz energy. They are all intensive properties. And also look at one of the equations. H sub m is equal to U sub m plus P times V sub m. So every single variable in this equation is intensive. Molar enthalpy is intensive. Molar internal energy is intensive. Molar volume is intensive. And we mentioned this pressure and temperature are both intensive. If you have two beakers of water, both 50 degrees Celsius, if you mix them, you're not going to get 100 degrees Celsius. Alright, the mixture is still 50 degrees Celsius. Also, if you have two balloons, in each balloon you have 1 bar air. If you put these two balloons together and then ask you, is the pressure doubled? The answer is no. You still have just 1 bar pressure in the balloons. Chapter 2, Internal Energy, Work, Heat, and Enthalpy. Section 2.1, Internal Energy. How would you calculate the potential energy and kinetic energy of your cell phone? There are simple equations. For potential energy, well, you can say it's gravitational force multiplied by the height. For kinetic energy, you can say it's 1/2 mv squared. But if you take your cell phone and board an airplane, how would the potential energy and the kinetic energy of your cell phone change? And don't forget, you and your cell phone are rotating about the center of Earth. You and your cell phone are also rotating about the sun at 30,000 meters per second. So relative to the sun, the kinetic energy of your cell phone is about 90 million joules. The gravitational potential energy of your phone relative to the sun is twice its kinetic energy. It's 180 million joules. But don't forget this. The entire solar system is moving at 200,000 meters per second. And then how would you calculate the kinetic energy of your cell phone now? How would you calculate its potential energy? In the gravitational field of the Earth, the Sun, the Moon, the many other astronomical objects. Well, kinetic energy and potential energy are both relative quantities. In thermodynamics, we do not take the kinetic energy or potential energy of the system relative to the external groundings into account. They are just set to 0. Again, the kinetic energy and the potential energy of a system relative to its external surroundings are simply set to 0. Even if your phone is rotating about the sun, we do not care about that kinetic energy. And only the internal energy of the system is of interest. U denotes internal energy. Another example, if you have a gas canister of HCl molecules, the internal energy of the gas remains constant. Even if you put this canister in a rocket and the rocket is flying at 1,000 meters per second and 100 kilometers above the ground, it just makes no difference. The internal energy of this HCl gas remains unchanged. In thermodynamics, the internal energy of a system includes the attraction and repulsion between the charged particles inside the system. The internal energy also includes the kinetic energy of these particles within the system. And you may ask, what if I have only neutral molecules and neutral atoms? Well, any atom or molecule consists of nuclei and electrons. So in the end, we have charged particles in this thermodynamic system. If we look at potential energy, it can be attraction, it can be repulsion. Attraction is due to the electrostatic interaction between opposite charges. Repulsion is the electrostatic interaction between like charges. What about kinetic energy? Again, we only worry about the motion of those particles inside the system. The first law of thermodynamics tells us the internal energy of an isolated system remains constant because energy cannot be created or destroyed. In this case, we write delta U is 0 for an isolated system because U is equal to PE plus KE. Therefore, the change of the sum of PE and KE is always 0 for an isolated system. Any increase of PE is accompanied by a decrease of KE, and vice versa in an isolated system. For example, if there's a reaction taking place in an isolated system, such as H2 plus F2, you get 2HF. This is a exothermic reaction. Heat is released from the reaction, but however, the change of the kinetic energy and the change of the potential energy cancel each other in this isolated system. Again, energy cannot be created or destroyed. The universe is an isolated system. Therefore, the internal energy of the universe is a constant. It's possible to have transformation from PE to KE or from KE to PE, but overall, the internal energy of the universe never changes. A thermodynamic system can be open, closed, or isolated. Let me give you 3 examples. Water puddle, well, it's an open system because there can be matter exchange and energy transfer between this water puddle and its surroundings. What about a capped bottle? Well, it's a closed system. There's no matter exchange between the water inside the bottle and its surroundings. What about energy transfer? It is possible if the water temperature is different from the temperature of its surroundings. Isolated systems cannot have any matter exchange or energy transfer. One example is the universe. We consider the universe an isolated system. Therefore, delta U for the universe is 0. The internal energy of an open system may change due to matter exchange. Here's an example. If you add 1 milliliter water into another system that consists of 1 milliliter of water, then the internal energy of the system is doubled, going from 1 mil to 2 mils. An open system can also undergo energy exchange via heat or work. So can a closed system. When work is done on a closed system, its internal energy increases. If work is done by a closed system to its surroundings, the internal energy of the system decreases. When heat flows into a system, its internal energy increases. When heat flows out of a system, its internal energy decreases. So for a closed system, we have an equation over here. Delta U is equal to Q plus W. That means the change of the internal energy is due to either heat or work or both. Again, heat denotes the amount of heat that flows into the system. But what if heat flows out of the system? We still use Q, but Q is now negative. Work is the amount of work done on the system. What if work is done by the system to its surroundings? Then W is negative. Sometimes we write delta U subsystem for the internal energy change of the system, but it's not very convenient. So we simplify this notation to delta U without any subscript. If there's no subscript, usually we say this is about the system. It's just convention. The system subscripts for Q and W can also be omitted for the system. as well as many other thermodynamic functions. Finally, I want to say this: if you have a closed system, its internal energy can also remain constant. If by coincidence Q is equal to negative W, we plug in Q is equal to negative W here, delta U is just 0, only because Q and W cancel. Chapter 2: Internal Energy, Work, Heat, and Enthalpy. Section 2.2: Work. There are many types of work, but in thermodynamics, we will focus on the expansion/compression work. In the last two chapters of thermodynamics, we will briefly introduce the electric work. So now let's get back to the expansion/compression work. For convenience, we usually call this expansion work. Expansion work can be calculated using this formula: negative integral external pressure dV. The proof is as follows. Let's look at a system over here in blue color with a pressure P and volume V. And this is a piston. We're exerting a external force F to the piston, and this is going to compress the system. Now if we move this piston for a distance of dx, then the amount of work is F dx. If we move a finite distance delta x, then the amount of work is simply F times delta x, if this F is constant. But what if the force changes during the displacement? Then we'll have to resort to calculus. Work is the integral of force times dx, and this allows this force to change when x changes. Now let's look at this system in blue color with the pressure P and a volume V. When this is compressed, work again is the integral of force times dx, and force is the external pressure times this area A. That's by the definition of pressure. And then we can replace force with P external times A. We got this equation. And remember, A times dx happens to be the volume of this displacement, and this is simply dV. This is the change of volume. And then we have a nice equation. Work is equal to the integral of P external dV. Now you may ask why there's a negative sign here. This is because when we define expansion work, if work is done on the system, we say work is positive. If work is done by the system to its surroundings, we say work is negative. We add this negative sign to emphasize that expansion work is positive if work is done to the system, and W is negative if work is done by the system. Again, the equation for expansion work is negative integral P external dV. So there are two things we need to pay attention to. The first is the sign. We have this negative sign here. The second thing is the subscript. P sub ext is the external pressure, not the system pressure. So it's possible for the system pressure to be different from the external pressure. In that case, well, we'll have to use the external pressure to calculate the amount of work. Work is transitory. That means it's not associated with the state of the system, but associated with the entire process that results in the change of the state of the system. So that means if you go from state 1 to state 2, and if you know everything about the initial state, state 1, and everything about state 2, the final state of the system, it's still impossible for us to calculate the amount of expansion work. We'll have to know the more information about the process that connects state 1 and state 2. So again, given only the initial state and final state of the system, we cannot calculate the amount of work. Let me give you an analogy. The analogy is this, what's the number of steps you have walked today? Now I'm going to give you some information. So initially you are in your dormitory. At the end, your final state is also in your dormitory. Now my question is, how many steps have you walked in this day? You know the initial state, you know the final state. Actually, they're the same, but you cannot we cannot tell how many steps you have walked, between the initial state and final state. You could have just stayed in the dormitory for the whole day, and you just lie on the bed, and then the number of steps is just 0. Or you can just walk like 6,000 steps to somewhere else and then come back with 6,000 steps. Then you have walked a total of 12,000 steps in that day between the initial state and the final state. All right. If work is done, it's always between two objects. If we're talking about the work of the system, we have to understand this equation. The work done to the surroundings is the opposite of the work done to the system. So W surroundings plus W system is always 0. And over here there's a animation of a so-called isothermal expansion of ideal gas. This isothermal means the temperature is constant. I'm gonna just play this isothermal expansion over here. So we heat it up, the gas expands. So you can see the PV curve here. But the temperature is constant. You may want to, how can this temperature to be constant? Let me explain. When we have ideal gas, that means there's no attraction, no repulsion between gas particles. The potential energy is always 0. And we know temperature is a measure of kinetic energy. So somehow if the kinetic energy is constant, then temperature is constant. So how can we have a constant kinetic energy situation here? Well, when we heat it up, yes, energy flows into this system in the form of heat. But at the same time, the system expands, right? So when the system expands, it can do work to its surroundings. It's pushing its surroundings. So the system loses energy in the form of work. In summary, it gains energy in the form of heat. It loses energy in the form of work. And it's possible for the amount of work and the amount of heat cancel. In that case, the internal energy of the system remains constant. And because internal energy is equal to potential energy plus kinetic energy, that means the kinetic energy remains constant. There's no temperature change. So again, in the isothermal expansion of an ideal gas, delta U is actually 0. That doesn't mean Q is 0 or W is 0. It simply means Q and W cancel each other. And when we heat it up, Q is greater than 0, and then we know W is less than 0. Also, we can see in this animation, the system expands against its surroundings. That means work is done by the system to the surroundings. Therefore, work is negative. Now let's look at several numerical examples to see how expansion work can be calculated. Example problem 2.2.1. Calculate the work involved in the following 3 isothermal processes, and then compare the results. A follow-up question is, how can we maximize or minimize work? Now let's look at A. A 20-liter ideal gas with full bar pressure expands to 80 liters against a external pressure of 1 bar. So if the gas expands against 1 bar, in the end the system pressure will drop from 4 bars to 1 bar. 1 bar is going to be the final pressure of the system. Now let's compute work. Work is negative integral P external dV. Again, two things. First, you need to remember this negative sign. Two, it has to be external pressure, not the system pressure. What's the external pressure? It's 1 bar. We plug in the numbers. We have the lower limit and upper limit for the integral. We do the calculation. It's negative 60 bar liter. This is negative because the system expands. It does work to the surroundings. B, a 20 liter ideal gas with 4 bar pressure first expands to 40 liters against 2 bar external pressure, and then it further expands to 80 liters against 1 bar external pressure. So remember, there are two steps. In the first step, external pressure is 2 bar. The second step, the external pressure is only 1 bar. So we have to compute the amount of work for each of the two steps. In step 1, the system expands from 20 liters to 40 liters. The external pressure is 2 bar. We evaluate this integral, we get negative 40 bar liter. In step 2, similarly, we use this equation, negative integral P external dV. What's the initial volume in this step 2? It's 40 liters. Final 80 liters. And this time, the external pressure is only 1 bar. Evaluating this integral, we get negative 40 bar liters. And we can sum it up. This work is additive. So the amount of work done by the system is 40 bar liter in the first step. And it happens to be also 40 bar liter in the second step. We add them up, we get negative 80 bar liters done by the system to the surroundings. So in the first example, this is a one-step process. Work is done to the surroundings. The amount is 60 bar liter. In the second, this is B example. This is a two-step process. The system does 80 bar liters to the surroundings. So now we wonder if we have more and more steps, should this number keep increasing? Well, we'll see. Again, we examined two different processes of the expansion of ideal gas. A one-step process versus a two-step process. In the one-step process, we get negative 60. In the two-step process, we get negative 40 plus negative 40. Now let's use a graph to visualize these two different processes. Alright, so what I'm going to do is I'm going to plot this P external versus V. Again, this is P external versus V, not system pressure versus V. So if you have some other copies of PChem textbooks, so occasionally you can see P versus V when they are trying to visualize expansion work, and that's inaccurate or incorrect. So again, it has to be P external if you are interested in the expansion work. Now the system expands from 20 liters to 80 liters, and the external pressure is a constant 1 bar. So you can see I'm gonna go from 20 liters to 80 liters with a constant 1 bar pressure. And the integral is simply this area, and it's pretty simple. The height is 1 bar, well the width is 80 minus 20, 60 liters. So this area is 80 bar liters. And remember, the system does work to its surroundings, so it should be negative 60 bar liters. Alright, now let's visualize the two-step process. So in the two-step process, we first expand this gas from 20 liters to 40 liters against a 2 bar external pressure. So this 2 bar external pressure. So we are looking at this rectangle in the first step. In the second step, the expansion is against 1 bar pressure. The volume change is from 40 to 80. So this is the second step. Again, there are two rectangles. The first rectangle is here. The second rectangle is here. And if you sum up the areas of these two rectangles, you will get negative 80, considering the sign for the work done by the system. Now let's compare these two graphs. What's the difference? Okay, if you look at the two-step process, you can see we have some additional area. So this does not appear here. It's here. So that's why in this two-step process, the system does more work to the surroundings. So this part is 20. All right, so we have 60 here, we have 20 here, and then we have a total of 80. And again, we wonder if we have more and more steps, can we just, get more and more work? So here's another example. In this example, again, a 20-liter ideal gas expands from 20 liters to 80 liters. The system pressure is 4 bars, but now over here, this is kind of strange. The system expands against a P external, and we're going to assume P external is equal to P. The external pressure is equal to the system pressure, also in an isothermal process. Now let's look at the integral for the expansion work. Negative integral P external dV. Given this condition, P external is equal to P, we can replace this P external with P. So we're going to just integrate this, and remember, it's an isothermal process. If it's an isothermal process, when we integrate this, we can just express pressure as a function of volume easily. Its pressure is just nRT over V, and then T is a constant. So that's why we take this nRT out of the integral. We just need to integrate 1 over V dV. That's the logarithm of V. So in the end, we get a interesting formula here that involves the logarithm. It's negative nRT times the logarithm of final volume over initial volume. We do not know the temperature, but we can calculate nRT by using PV equals nRT, and it's isothermal, so we can use initial PV or final PV. So nRT is equal to initial PV or final PV. It does not matter. Let's use initial PV. It's 20 liters times 4 bar, so that's 80 bar liters. Therefore, we can replace nRT with 80 bar liters. Work is negative 80 times ln4. 80 over 20, that's 4. So bar liters. And we just calculate the logarithm of 4. I think it's roughly 1.4. We do the calculation, we get negative 111 bar liters. And later you'll see this is the maximum amount of work the system can do to its surroundings. Remember, in the previous examples, we had 60, we had 80, and now it's 111, and this is the maximum amount of work the system can do to its surroundings given this initial condition and also final condition. Now you may wonder, if the external pressure is equal to the system pressure, they cancel. How can the system expand? It's just because you can somehow imagine, they are not exactly the same. What if the system pressure is equal to external pressure plus 10 to the power of negative 1,000 times P external? Then if you have this equation, you can see the system pressure is slightly greater than the external pressure, so that the system can expand. Meanwhile, P external is roughly equal to P. So it seems contradictory, but hopefully using this example, you can see P is greater than P external. At the same time, P is about the same as P external. So we can still use this equation to compute the amount of work. Now we have worked on 3 numerical examples. If we have just one step process, P external equals 1 bar, we get negative 60. If P external is equal to 2 bar in the first step, 1 bar in the second step, we get negative 80. We can set P external to be P in this entire process, and then we get negative 111 bar liters. And later we'll see this is the maximum amount of work that can be done by the system given the same initial and final states. Now let's look at more numerical examples. This time still isothermal, but now let's look at compression. Alright, we'll look at compression. So the initial state of the ideal gas is 80 liters, 1 bar pressure. We are going to compress it to 4 bars and 20 liters. We need to know what is the external pressure, because again, in the formula for work, we need to use negative integral P external dV. Now we plug in the initial volume, final volume, and also external pressure. The result is 240 bar liters. Now we're going to do a two-step process. First, we compress this system against a external pressure of 2 bars, and then the final system pressure in this step is going to be 2 bar. We're not done yet. In the second step, we increase the external pressure to 4 bars. We keep compressing the system until its final pressure reaches 4 bar, and the final volume is going to be 20 liters. Because there are 2 steps, we'll have to calculate the amount of work in step 1 and then step 2. In step 1, P external is 2 bars. The initial and final volumes are 80 liters and 40 liters. Evaluating this integral, we get 80 bar liters. In the step 2, again, we use the same formula, but the external pressure is actually higher. It's 4 bars. The initial and final volumes are 40 liters and 20 liters. And solving this integral, we get also 80 bar liters. The total amount of work is W1 plus W2. The result is 160 bar liters. So you can see in step 1, we have 240 bar liters. In step 2, we have 160 bar liters. It seems that if we increase the number of steps, we get less and less amount of work. So is there a minimum for this compression work? Now again, let's visualize these 2 processes. In the one-step process, the external pressure is 4 bars. So I'm going to plot this P external over V. The initial volume is 80. The final volume is 20 liters. So it goes from 80 to 20. The external pressure is 4 bar. So I'm making this rectangle. The height is 4 bars. The width is 80 minus 20, which is 60. And we can easily see the area of this rectangle is 4 bars times 60 liters. Therefore, it's actually 240 bar liters. The surroundings does this amount of work to the system. Now, what if we use a 2-step process? So in the first step, we use only 2 bar pressure to compress the system from 80 bars to 40 bars. We get a rectangle with an area of 80 bar liters. And then in the second step, we use a 4 bar external pressure to compress the system from 40 to 20. Again, we get 80. If we sum it up, you get 160. This is smaller than 240 because you can see this part is missing. Okay, this part is missing. How much is this? It's simply just 240 minus 160, so this part is missing. This part is 80. Now let's look at another compression process. This time, still we have the same initial and final states for the system. The initial state is 80 liters in 1 bar. The final state is 20 liters and 4 bars. But this time, we're going to compress the system in a process that P external is equal to P. So again, we use this formula and we can replace P external with P. Alright, and then pressure is nRT over V. This is an isothermal process, so temperature is constant. We take nRT out of the integral and we need to evaluate the integral of 1 over V dV. That's the logarithm of V. So we have logarithm of 20 minus the logarithm of 80. It's just the logarithm of 20 over 80. So we know how to compute nRT because PV equals nRT. We'll just use initial state. PI is 1 bar. VI is 80 liters. So nRT is 80 bar liters. And throughout the entire compression process, nRT remains constant because this is an isothermal process. Now we just plug in 80 here. We'll have to evaluate 80 times the logarithm of 4. We get 111 bar liters. Alright, so again, you know, we get this same number when we do the expansion of the gas. If P external is equal to B, we get 111. Now we're doing compression. If P external is equal to P, we still get 111. Again, how can we compress the system if P external is equal to P? Well, somehow you can just imagine P is slightly smaller than P external. For example, P is just P external minus a very small number times P external. Then this way we have P smaller than P external. The system can be compressed. At the same time, we can say P is equal to P external because this term, 10 to the power of negative 1,000, it's negligible. So we studied 3 numerical examples for the compression process: 1 step, 2 step, and then the third one is P external equals P. So in the 1 step process, when we compress the system against a 4 bar external pressure, the amount of work done to the system is 240 bar liters. What if we use 2 bar external pressure first, going from 80 liters to 40 liters, and then we use 4 bar pressure, going from 40 liters to 20 liters? Overall, we get 160. So these two numbers are different. And then finally, we say, well, why don't we just make sure P external equals P, and then we have 111 bars, and this number is actually the minimum amount of work that is done to the system given the same initial state and final state. The initial state is 80 liters 1 bar, final state 20 liters 4 bars. So this is just a summary. There are 2 tables. One is for expansion, one is for compression. So if we look at expansion, we studied the 1-step process, 2-step processes, and over here we have P external is equal to P. Over here, same thing, 1 step, 2 step, P external equals to P. So over here you can see negative 60, negative 80, and then negative 111. Over here 240, 160, 111. So a couple things we need to kind of just mention. One is work is transitory. The amount of work depends on the process. So if you are given the initial and final state of the system, it's impossible to compute the amount of work unless you know more information about the process. What information? This P external. So for this process, we know P external is just 1 bar. Over here, we know there are 2 steps. In the first step, P external is 2 bars. In the second step, it's 1 bar. Over here, we also know P external is equal to P. And then we know ideal gas law, so P is nRT over V. So somehow we know the information about the external pressure. Alright, that's the first thing we need to know. Like, we cannot determine the amount of work unless we know more information about the process other than the initial and final states. And also, if we do this, P external equals to P for expansion, we get the maximum amount of work that can be done by the system, 111. So same here, if we use P external is equal to P, we get the minimum amount of work that can be done to the system. That's also 111. This is not a coincidence. It's just because when we integrate the amount of work, in both cases, here and here, we have P external is equal to P, and basically we're just integrating negative integral P dV, and the upper limit and lower limit of volume over here are 20 to 80 liters. Over here it's 80 to 20 liters. That's why these two numbers are the same. They just differ by the sign. One more numerical example about some cyclic processes. So we're gonna do, like, for example, we're gonna do expansion and compression so that the system gets back to this its original state. Now let's look at one example. The initial state is 20 liters 4 bar. We first expand to 80 liters and 1 bar, and then compressed back to 20 liters and 4 bar. The expansion is 1 step, the compression is also 1 step. So we did this calculation before, it's negative 60. We did this 1 step compression before, it's positive 240. So when the system gets back to the original state, well, there's a total amount of 180 bar liters. This amount of work done to the system. It's kind of strange. The system gets back to its original state. How can this amount of work, be done to the system? Well, it's simple. When a system gets back to its original state, Well, it should have the same energy. The initial and final internal energy should be the same. And how can this amount of work done to the system? Well, the system must have lost energy in the form of heat. So at the same time, it must have lost this amount of heat. Now let's look at another example. So again, the ideal gas first expands and then being compressed. 20-liter ideal gas 4-bar pressure expands to 40 liters and 2-bar against 2-bar external pressure, and then expands to 80 liters and 1-bar against 1-bar external pressure. So 2-step expansion followed by 2-step compression. So what's the total amount of work? Actually, we computed this 2-step expansion. It's -80. We computed the amount of work in this 2-step compression, which is 160. So together, it's 80. So in this B example, we had 2-step expansion followed by 2-step compression. Overall work is done to the system. The amount is 80 bar liters, and we know this system must have lost the same amount of energy in the form of heat. One more cyclic process example over here. Still 20-liter ideal gas, 4-bar pressure expands to 80 liters and 1-bar. But we're going to ensure this condition, P external is equal to P, and then followed by the compression, P external is still equal to P. So we learned in this first step it's -111. In the second step it's +111. They cancel. So overall the amount of work is 0. So Q is also 0 in this cyclic process. So in summary, we covered 3 different cyclic processes. In the first 2, net work is done on the system. I want to show you in A, this amount of work is done to the system, 180. In B, 80 bar liter is done to the system. Alright, but in C, it's just 0. And I want to remind you that internal energy is a so-called state function. It only depends on the state of the system. So that means when a system undergoes a series of steps and gets back to the original state, the internal energy should be the same, right? Same state, same internal energy. However, work and heat are not state functions. They depend on the processes. So in this 3 different cyclic processes, we get 3 different numbers for work. Alright, and finally I want to just talk about this process C a bit more. The net work is 0. The net heat is also 0. And overall there's no net change to the system or its surroundings. So we want to say this. You will learn later. The in this C cyclic process, the entropy of the universe remains constant because there's no change to the system. There's no change to the entropy of the system, and there's no change to the surroundings. Therefore, there's no change to the entropy of the surroundings. Overall, the entropy of the universe remains constant. And later we'll say this process is a reversible process because if the entropy of the universe increases, well, we cannot reverse it because the reversal will result in the entropy decrease of the universe, which is in violation to the second law of thermodynamics. And later we'll see, as long as we hold this equation, P external is equal to P in expansion and compression, we say, well, this kind of processes, whether expansion or compression, we call that reversible. Again, if P external is equal to P, we're not going to increase the entropy of the universe so that we can reverse it without violating the second law of thermodynamics. Chapter 2, Internal Energy, Work, Heat, and Enthalpy. Section 2.3, Heat. Heat flows from a higher temperature region to a lower temperature region. Heat is transitory. That means heat is not associated with the state of the system. Heat is associated with how the state of the system changes. If we are given the initial and final states of a system, there's no way for us to calculate the amount of heat, Q, until more information is provided for the entire process. And in practice, we often need to calculate work and the change of internal energy delta U first, and then we use this equation to calculate Q. Delta U is equal to Q plus W for a closed system. Now let's look at example problem 2.3.1, where calculate Q involved in three different processes. A 20-liter ideal gas with 4 bar pressure expands to 80 liters against 1 bar external pressure. Let's assume the process is isothermal. If the process is isothermal, that means there's no temperature change. And temperature is a measure of the average kinetic energy for a closed system. If the temperature is constant, that means the average kinetic energy is constant. There's no change in kinetic energy. And also, for an ideal gas, its potential energy is always zero. Based on the analysis of the kinetic energy and the potential energy, we know delta U is zero. There's no change in the internal energy of this ideal gas. Therefore, we can compute W first, and then Q is equal to negative W. W is negative integral P external dV. Plugging all the numbers, work is negative 60 bar liters. Therefore, for this ideal gas in an isothermal process, Q is negative W is 60 bar liters. Also, we know what's Q surroundings. Q surroundings is always negative Q. Now let's look at another process. A 20-liter ideal gas expands to 40 liters against a 2 bar external pressure, and then it further expands from 40 liters to 80 liters against 1 bar external pressure. There are 2 steps, so we can compute the work in step 1 and the work in step 2, and then we can sum it up. Work is negative 80 bar liters, and because the kinetic energy of this ideal gas remains unchanged in this isothermal process, the potential energy of an ideal gas is always zero. We have delta U is equal to 0. Therefore, Q is delta U minus W, and we get 80 bar liters because, again, delta U is 0 because there's no change in its potential energy or its kinetic energy. The third process, this gas expands against 80 liters. Under this condition, P external is equal to P in the entire process. And again, we can compute W. W is equal to negative 111 bar liters. Therefore, Q is positive 111 bar liters. And also, we can get the amount of work done on the surroundings, which is 111 bar liters. And also, we can compute Q for the surroundings, which is just negative 111 bar liters. After 20-liter ideal gas expands to 80 liters against 1 bar external pressure, followed by the compression, isothermal compression against a P external of 4 bars, the system returns to its original state. After this cyclic process, the initial state is 20 liters and 4 bar pressure. The final state is also 20 liters and 4 bar pressure. So since this is a cyclic process, we know delta U is going to be 0. However, neither W nor Q is 0. We can compute W. For this 2-step cyclic process, it's 100 bar liters. And then we can compute Q. Q is delta U minus W, which is negative 180 bar liters. Actually, we do not have to analyze the kinetic energy change and potential energy change for this gas, because if a process is a cyclic process and because U is a state function, the system returns to its original state after a cyclic process. Therefore, delta U is always 0 for any cyclic process. So we can just simply say Q is negative W. Alright, the net effect of this cyclic process is that the surroundings does some work to the system and it loses energy in the form of heat. Heat and work cancel, so that delta U is 0. After the cyclic process, the system returns to its original state. And because pressure, volume, temperature, entropy, internal energy, enthalpy, Helmholtz energy, Gibbs energy, are all state functions, their values should remain unchanged after this cyclic process. The initial value and the final value of all those state functions should be exactly same. But there might be something done to the surroundings. Later we'll see the entropy of the surroundings increases in these two-step processes. Therefore, this process is called an irreversible process. If we maintain P external is equal to P in the entire process, then this process is called a reversible process. The entropy of the system and the entropy of the surroundings remain constant. So after this cyclic process, W is 0, Q is 0, delta U is 0, nothing has changed. There's no net change in the system nor in its surroundings, and such a cyclic process is called a reversible cyclic process. Again, I want to mention the condition for this cyclic process. You have to maintain this equation. P external is equal to P. Again, if P external is equal to P in the entire cyclic process of expansion and compression, both the system and the surroundings return to their original state after such a cycle. And also, the entropy of the system and the entropy of the surroundings remain unchanged. Therefore, the entropy of the entire universe remains unchanged. That's the basis of the reversibility of any process. In theory, a reversible expansion or compression is achieved only when P external is equal to P. And when P external is equal to P, there's no net force. So somehow we need to imagine during the expansion, the system pressure is just slightly greater than the external pressure. During compression, the system pressure is slightly smaller than the external pressure. The difference between the system pressure and the external pressure is infinitesimal. So sometimes we use delta P to denote this infinitesimal difference. Now we're going to use two graphs to depict the irreversible isothermal expansion and compression. So over here, this is irreversible expansion. So again, we have a initial volume of 20 liters, a final volume of 80 liters. This is a irreversible expansion. P external is not equal to P in the entire process. So if we go from left to right, we can see the volume increases. The P external is a constant. The system pressure, however, changes. So again, P external is different from P. And we can compute the amount of work using the equation negative integral P external dV, and Q is equal to negative W, because again, this is a isothermal process for an ideal gas. Therefore, the kinetic energy change is 0. The potential energy change is 0. Therefore, delta U is 0. Q is equal to negative W. Over here, this is a graph for irreversible compression. P external is set to be 4 bars. We are compressing this system with a constant 4 bar external pressure. We can compute the amount of work easily using this equation, negative integral P external dV. And again, Q is equal to negative W, only because delta U is 0. Delta U is 0 only because there's no potential energy change. There's no kinetic energy change.
Chapter 2: Internal Energy, Work, Heat, and Enthalpy. Section 2.4: Heat and Work at Quantum Level. Quantum mechanics predicts that the atoms or molecules inside a system occupy discrete energy levels. Here is an example. We have 3 energy levels and we have 4 particles occupying the lowest energy level, 1 particle in the second lowest energy level, 0 particles in this energy level. The occupation numbers are 4, 1, and 0. When a system is compressed, work is done on the system. In this case, all quantum energy levels shift up, but the occupation numbers of these energy levels remain unchanged. It's still 4, 1, 0. However, again, the energy levels are shifted up, and therefore the internal energy of the system increases. Now let's look at a numerical example. Let's say over here this energy level is 1 septojoule, or 10 to the power of negative 21 joule. And this second lowest energy level is 2 septojoule. And after work is done to the system, these energy levels are shifted up. Let's say this is 2 septojoule and this is 4 septojoule. And then from here to here, we can compute the amount of work. It's 2 times 4 over here, plus 1 times 4. It's over here, minus the original energy of these particles. The result is 6 septojoule. It's just a numerical example. What if more work is done on the system and those energy levels are further shifted up? I did not draw this energy level. It's probably somewhere here, and then it shifted up over here. When 5 particles are distributed as depicted in this diagram, the number of possible arrangements is 5. Just imagine if you have, for example, 5 apples in 2 baskets, and you know there's 1 apple in one of the 2 baskets and 4 apples in the other basket. There are 5 different arrangements. So one of the 5 apples can be in a bucket and the other 4 should be in the other. So each of these possible arrangements is called a microstate. And later in part 4 of the book, Statistical Thermodynamics, we will learn the definition of Boltzmann entropy. It's K sub B times the logarithm of W. K sub B is the Boltzmann constant. W is the number of possible arrangements of those particles in various energy levels. There is one official name for this W, the number of accessible microstates. Each arrangement is a microstate. When work is done on the system, the total energy of the system changes. It increases. It's only because all those energy levels are shifted up. However, when work is done on the system, it does not change the occupation numbers in those energy levels. Therefore, this W remains constant. The entropy of the system remains constant. But when heat flows into a system and increases its internal energy, it's actually different from work at the quantum mechanical level. When heat flows into the system, actually all energy levels remain unchanged. What's changed is the occupation number. So here's one example. Again, at the beginning, we have 4 particles in the lowest energy level, 1 particle in the second energy level. After heat flows into the system, it's possible for us to have more molecules in the higher energy level. For example, in this case, the occupation numbers become 3 and 2. One particle jumps from the lowest energy level to the second lowest energy level. And also, we can look at one numerical example. So let's say, well, this is 1 septojoule. The second lowest energy level is 2 septojoule. We can compute the amount of the energy change. It's just 3 times 1 plus 2 times 2 minus 4 times 1 plus 1 times 2. The result is 1 septojoule. The internal energy of the system increases due to heat. Again, the energy levels remain unchanged. The occupation numbers are changed. If more heat flows into the system, again, we keep all those energy levels at the same level and we change the number of particles in those energy levels. The occupation numbers are changed. When heat flows into a system under isochoric condition, that means there's no compression, no expansion. That means no expansion work. So heat flows into the system that increases the energy of the system. However, all energy levels remain unchanged. So what has caused the total energy increase? Well, it's pretty simple. Some molecules or atoms move from the lower energy levels to higher energy levels. Again, in this diagram over here, one particle moves from the lowest energy level to the second lowest energy level. And now let's count the number of arrangements. So if we look at this diagram on the right hand side, on the left hand side, we have 4 particles in the lowest energy level and 1 particle in the second lowest energy level. There are 5 arrangements because we can select one of the 5 particles and put it in the second energy level. What is the number of arrangements? It's actually 5 factorial divided by 4 factorial divided by 1 factorial. This is just a standard equation. The result is 5. 5 possible arrangements or 5 microstates. And the entropy is simply Boltzmann constant times the natural logarithm of 5. Now, after heat flows into the system, it's possible that one particle jumps from the lowest energy level to the second lowest energy level. Now we have occupation numbers 3 and 2. What's the number of arrangements? The standard equation is the total number of particles, 5 factorial on top. And on the bottom, we look at the individual occupation numbers. We have 3 and 2. Therefore, it's going to be 5 factorial over 3 factorial over 2 factorial. It's going to be 10 arrangements or 10 microstates. And again, this is just to select 2 apples out of 5. How many possible arrangements? Well, if we label those 5 apples A, B, C, D, E, well, you can get A, B, A, C, A, D, A, E. You can get B, C, B, D, B, E. You can get C, D, C, E, and finally D, E. A total of 10 possible ways to choose 2 apples to put into a bucket. Same here. We get 10 arrangements, 10 microstates, and the entropy has increased from here to here because now the entropy is the Boltzmann constant, case of B, times the natural logarithm of 10. What if more heat flows into the system? Now it's possible for us to have different occupation numbers like 2, 2, and 1. What's the number of arrangements? Again, we'll use the standard equation 5 factorial over 2 factorial over 2 factorial over 1 factorial. We get 30. Entropy is further increased. Chapter 2. Internal energy, work, heat, and enthalpy. Section 2.5. State and path functions. State functions depend on the state of the system. For example, pressure, volume, temperature, and entropy are state functions. Internal energy, enthalpy, Helmholtz energy, and Gibbs energy are also state functions. The number of moles is also a state function. The differential of a state function is an exact differential. Exact differentials can be integrated given the lower and upper limits of the integral. The cyclic integral of an exact differential is always zero. For example, internal energy U is a state function, and we can calculate delta U, the change of internal energy, as the integral of du from the initial state to the final state. And this integral is equal to the final internal energy minus the initial internal energy. The cyclic integral of du is always zero because u is a state function. As long as a system returns to its original state, then the final internal energy is equal to the initial internal energy. Delta U is zero for any cyclic process. We can replace U with any other state function in these two equations. For example, we can examine the pressure. We know the change of the pressure is just the integral of dP from initial to the final, or it's simply final pressure minus initial pressure. We do not have to know how the pressure changes from 1 bar to 2 bars. We just know delta P is 2 bars minus 1 bar. That's it. The cyclic integral of dP is zero. It's just because after the system undergoes a cyclic process, the system returns to its original state. Therefore, the final pressure is the same as the initial pressure in a cyclic process. The change of a state function depends only on the initial and final states of the system. It does not depend on the path this system undergoes between the initial and final states. Path functions depend on the entire path of a process. That means the value of a path function does not only depend on the initial and final states of the system, it also depends on the path that connects the initial and final states. Two examples are heat and work. They are both path functions. The differential of a path function is an inexact differential. When we write out inexact differential, we need to have a bar through this differential operator d. So you always see this d with a strike through. An inexact differential cannot be integrated given only the initial and final values of the variable. We have to know the information about the entire integral path. For example, there's an equation for expansion work, negative integral p external dv. If we only know the initial and final states of the system, we cannot compute the value of work. We have to know how this external pressure changes through the entire compression or expansion process. This P external can be a constant. Well, it can be like two different constants. In step 1, you have a constant P external. In step 2, you have another P external. Also, P external may change in the entire process. The cyclic integral of an inexact differential is often non-zero. Even if it's zero, usually it's just due to coincidence. Here's an example. After 1 mole helium undergoes a series of steps of expansion and compression and returns to its original state. That means the initial PVT are the same as the final PVT. The cyclic integral of dq with a bar and dw also with a bar through this d, they are often non-zero, even though the cyclic integral of du is always zero. We do know du is equal to dw plus dq. Then how can the sum of two path functions be a state function? Well, here's a simple example. The integral of y dx and the integral of x dy are both path functions. Their values cannot be determined given only the initial and final values of x and y. Here's the example. If I tell you the initial values of x and y are 1 and the final values of x and y are 2, how can you integrate this y dx? We don't know because y may change between 1 and 2. It may be a function of x, it may be a constant. We do not know. Therefore, we need more information to calculate this integral of y dx. For the same reason, we need more information to calculate the value of the integral of x dy. However, if we sum up these two path functions, the integral of y dx plus the integral of x dy is actually the integral of dxy. This is based on a rule, the product rule in calculus. dxy is y dx plus x dy. Therefore, the sum is simply the integral of dxy. Therefore, it's simply xy plus a constant. Now, if we have the initial values and final values of x and y, we should be able to get the value of the integral. It's simply 2 times 2 minus 1 times 1. We get 3. Now let's look at a graph. So now, if we have a curve over here, let's say this is the function of x, y is the function of x, and this curve represents that function. Then how do we integrate y dx? We do need to know how y changes with x when x goes from 1 to 2. So the integral of y dx is this area under the curve, and the integral of x dy is this area, okay, to the left of the curve. We do not know this integral or this integral. However, we can calculate the sum of these two integrals. Well, it's pretty simple. The sum of these two integrals, if you look at it, it's this larger square, 2 by 2 square, minus this smaller 1 by 1 square. Therefore, it's simply 3. Again, this integral is a path function. This integral is a path function. But the sum of these two path functions is a state function. Y dx by itself is inexact differential. X dy is another inexact differential. But x dy plus y dx, we get dxy, the exact differential of xy. So it's possible for the sum of two inexact differentials to be an exact differential. For the same reason, du is equal to dq plus dw. du is an exact differential, but dq and dw are both inexact differentials. And also we know delta u is equal to q plus w. Although q and w are path functions, they depend on the path of the process. However, delta u depends only on the initial and final state of the system.
Chapter 2. Internal energy, work, heat, and enthalpy. Section 2.6. Isochoric and isobaric processes. The first law of thermodynamics states that energy cannot be created or destroyed. Therefore, in a closed system, delta U is equal to Q plus W. The differential form is du equals dq plus dw. So we have a bar through this differential operator d. So is this one. Because dq and dw are inexact differentials. dw is negative p external dv. We need to know the information about this p external to calculate work. Although du by itself is an exact differential, both dq and dw are inexact differentials. The sum of two inexact differentials can be an exact differential. When an ideal gas undergoes an isothermal process, du is 0. This is because we have two components to consider: the potential energy of the system and the kinetic energy of the system. Now we have an ideal gas. We're going to assume the potential energy is always 0 for an ideal gas, because there's no attraction nor repulsion between ideal gas particles. Now let's look at the kinetic energy. In an isothermal process, temperature remains constant, and temperature is the measure of the average kinetic energy of all particles. Therefore, if temperature is constant, the kinetic energy should be a constant. Then du is 0. The internal energy of an ideal gas solely depends on temperature. Now, if it's an isothermal process, again we have this equations. dt is 0, therefore dke is 0. There's no change in kinetic energy. du is the sum of dpe and dke. P is potential energy, K is kinetic energy, and there's no change in potential energy, there's no change in kinetic energy, therefore du is just 0. Later we'll learn that an isothermal process can be reversible or irreversible. When P external is always equal to P, the process is reversible. When P external is different from P, the process is irreversible. Later we'll learn that a reversible process does not involve any change in the entropy of the universe. And if a system undergoes an irreversible process, it is irreversible only because this process increases the entropy of the universe. Therefore, it cannot be reversed, because the reversal will violate the second law of thermodynamics. Now in this section 2.6, we will only study the isochoric and isobaric processes. Isochoric means constant volume, isobaric means constant pressure. In an isochoric process, there is no expansion or compression. Therefore, the expansion work is just 0. In an isobaric process, we'll just assume, because the system pressure is a constant, we're going to assume the system pressure is always equal to the constant external pressure. Again, du is equal to dq plus dw, and dw is equal to negative p external dv. Therefore, in the isochoric process, dv is 0 and dw has to be 0. Again, there's no expansion or compression. There is simply no expansion work. Therefore, du is equal to dq. To specify this isochoric condition, we add v in the subscript. So du sub v is equal to dq sub v. This equation means dq under the isochoric condition is equal to dq under isochoric condition. Note here I removed the bar because now this dqv can be integrated given only the initial and final states. Why? It's simple. Look at this equation. U is a state function, so we can always integrate du given the lower and upper limit of the integral. Therefore, we can also integrate this dq sub v. dq by itself is an inexact differential, but now we specify the condition here. It's constant volume. We know the path. We can integrate this dqv, and qv is equivalent to delta u under the constant volume condition. In this equation, we say delta u sub v is equal to q sub v. Note that we put delta in front of u, but not in front of q. This is because, again, u is a state function. Delta u is the change of u. This is the final u minus initial u. But we do not need to add delta in front of q, because q is associated with the entire process. Q is the amount of heat that flows into the system between the initial state and the final state. Q is a transitory property. Q sub V itself accounts for the internal energy change of this system under the constant volume condition. For most substances, within a small or even moderate temperature change, a small temperature change may be a few kelvins, moderate temperature change may be tens of kelvins. Usually Q sub V is proportional to delta T, or approximately proportional to delta T. Well, it does make sense. If you provide more heat to the system under the constant volume condition, you have larger delta T. And this proportionality is called isochoric heat capacity. It's written as C sub V. C sub V denotes isochoric heat capacity. C sub V is dQV over dt. Well, in general chemistry, you probably see C sub V is equal to Q sub V over delta T, the finite change of temperature on the bottom, the finite amount of heat on top. But now we learn the calculus. It's the exact differential here for Q sub V over the exact differential of temperature. Again, dq is inexact, but now with this V, it becomes exact or behaves like an exact differential. And also, we know dq sub V is du sub V, so we have this partial integral. Delta U over delta T under constant volume condition is C sub V. Alright, we have a bunch of equations here. CVM is simply the isochoric molar heat capacity. You just need to divide the isochoric heat capacity by the number of moles. You'll get this isochoric molar heat capacity. Note that CV is an extensive property, but CVM is intensive. Alright, because if you look at this division, CV is proportional to the amount, N is proportional to the amount. So this proportionality cancels. CVM is usually a constant or approximately constant within a small or even moderate temperature range. Again, from a few kelvins to even tens of kelvins. The temperature dependence of CVM is often negligible unless you have a very large temperature change, and then CVM may have a significant change. Now we're examining the essence of CVM and the values of CVM for a few substances. The value of isochoric molar heat capacity is equal to the amount of heat used to increase the temperature of 1 mole pure substance by 1 Kelvin in an isochoric process. So a few things. This V stands for isochoric, this M stands for molar, and heat capacity is dQV over dt. Therefore, we have to say per unit temperature here. When heat flows into an ensemble of molecules, this just means a bunch of molecules, usually a large number of molecules. Some molecules may be promoted to higher energy level because molecules can have translational motion, rotational motion, and vibrational motion. Then we have translational, rotational, and vibrational energy levels. With enough heat, a molecule may be even promoted to an electronic excited level. For example, if you heat up a molecule, you can even break a bond in the molecule, well, providing high enough temperature. Therefore, the isochoric molar heat capacity includes 4 components: the translational, rotational, vibrational, and electronic molar heat capacity. The first 3 terms are referring to the motions of the heavier nuclei of the molecule. For example, if we're talking about a water molecule, it can do translational motion. It just moves in the x, y, and z directions in space in a concerted manner. It can do rotation about its own axis. There are x, y, and z axes that cross at the center of mass of this water molecule. This water molecule may also undergo vibrations. For example, oxygen and hydrogen stretching, and also there's a bending motion. Now we have this electronic term. This is about electrons. This is a little bit more complicated. We need to study quantum chemistry before we get back to this electronic molar heat capacity. But for now, I just want to say this is usually small. Electronic molar heat capacity is usually small because it's very hard to promote a molecule from the lowest electronic energy level to even the second lowest energy level. Alright, again, there are four components. The last two are often negligible because it's hard to promote electron electronically or even vibrationally. For example, we have a water molecule, it does vibration, and can we somehow promote this water molecule into a higher vibration energy level? Well, the answer is yes, but you need a lot of heat. So this kind of promotion is very unlikely. It's very common to see the translational and rotational promotion. Alright, for atomic gases such as helium and argon, we do not have molecules, we have only atoms. Atoms do not undergo rotation or vibration. So the CVM of atoms is simply the sum of translation and electronic. Alright, so there are only two terms. In a solid or liquid, molecules cannot translate. They cannot rotate freely. So if we have ice, there's no translation, there's no rotation of water molecule. If we have liquid water, there's not much translation at all because each water is surrounded by other water molecules. It's hard for water to kind of move around. They can still rotate, but the rotation is not free rotation. It's called a partial rotation. So the molar heat capacity is the sum of three terms only: partial rotation, vibration, and electronic. And again, usually the last two are negligible. Each translational or rotational motion contributes 0.5 R, or 1/2 of the ideal gas constant, to the CVM of gas at the room temperature. At room temperature, the three-dimensional translational molar heat capacity, isochoric heat capacity of an atom or molecule is 1.5 R. Why? 3 dimensions. The molecule can translate in the x, y, and z directions, and in each direction it's 0.5 R. 3 directions, 1.5 R. What about the rotational isochoric molar heat capacity? Well, it depends. If you have a non-linear molecule such as water, there are 3 different rotations. Well, again, you can just find the center of mass for the molecule, and then you can have 3 axes perpendicular to each other, or crossing the center of mass, and then the molecule can rotate about these 3 axes. Therefore, there are 3 different rotational motions. Each rotational motion contributes 0.5 R. 3 of them, 1.5 R. But if you have a linear molecule, well, the rotation of such a molecule is considered 2-dimensional rotation. Here are examples: HCl, HCN, C2H2. They are linear. There are only 2 rotational motions. This is only because there are only 2 rotational axes. The molecular axis that contains all atoms is not considered a rotational axis, because if you try to rotate the molecule about this molecular axis of a linear molecule, well, there's not really any change of the position of the nuclei. Alright, so now if we look at a linear molecule, it can undergo 2-dimensional rotations. Therefore, its rotational isochoric molar heat capacity is just R. If you have atoms, they do not have rotational motions. They do not have rotational CVM. Over here in this graph, it shows you, well, 3 different rotational motions of water. Again, you need to somehow find the center of mass. It's right here. And then there's an axis passing through the center and perpendicular to the screen. So you have this kind of rotation. Also, you can have this kind of rotation or this kind of rotation. So for water, it's rotational molar heat capacity is 0.5 R times 3. The vibrational CVM is typically much smaller than R because it's very hard to promote molecules vibrationally. So they do not easily absorb heat and jump to the higher vibrational energy levels. The electronic molar heat capacity is even smaller. So we usually neglect the vibrational and electronic molar heat capacity. But if the temperature is high enough, molecules can be promoted from the lower vibrational energy level to higher vibrational energy level. Well, in this case, the vibrational molar heat capacity can become more significant. And there are also exceptions to electronic molar heat capacity. Occasionally, we have a molecule with some excited states very close to the ground electronic state. Well, we see some transition metal complexes with this kind of feature, and then their electronic molar heat capacity may become significant because just by heating up this kind of molecules, well, electrons can be promoted to the second lowest electronic state. For the argon gas at a typical temperature, for example, room temperature, just or kind of just even between like 50 Kelvin to 1000 Kelvin, its translational CVM is just 1.5 R. Well, it's just because there are 3 dimensions, and then 0.5 R times 3 is 1.5 R. Argon atoms do not have any rotational or vibrational motions. We neglect those. Its electronic molar heat capacity, it's negligible. It's very hard to promote an electron in the argon gas to a higher energy level. Therefore, we just predict the numerical value of the molar isochoric heat capacity of argon is 1.5 R. R is 8.3. Roughly 8.3 joule mole Kelvin, so we do the multiplication, we get 12.5. And the experimental value is also 12.5, so a really good agreement here. For nitrogen, more complicated, it's a molecule. So we have to look at the rotation and translation. The translation is still 1.5 R, so just imagine this nitrogen molecule moving in the X, Y, or Z direction in space in a straight line. So 1.5 R for 3 dimensions. It's a linear molecule, so it has only 2 rotational modes. We're going to predict its rotational molar heat capacity is just R. Alright, and then we sum it up. We predict the total molar heat capacity of nitrogen 2 is 2.5 R. Oh, I forgot to mention isochoric. Now R is roughly 8.3. If we do the math, it's going to be 20.8. What's the experimental value at room temperature? 20.6. Good enough. At a very high temperature, well, this value may exceed 2.5 R. Only because at very high temperature, well, it's possible for some nitrogen molecules to be promoted to higher vibrational energy level. Now we have a triatomic gas. It's H2S. Hydrogen sulfide. It has a translational molar isochoric molar heat capacity 1.5 R. Because it's nonlinear, we have 3 rotation modes, so the rotational CVM is also 1.5 R. And we're going to just estimate the total CVM is 3R. 3R is roughly 24.9, and then the experimental value is 25.4, so not too bad. If you compare this to, the difference is about 2%, I guess. But still, I just want to say this experimental value is 0.5 higher, mostly because in H2S, there's some vibrational modes that can be more easily changed. For example, the bending, I think it's just mostly the bending. You have a HSH bond angle, and if you change the bond angle, it's called a bending motion. It's also considered a vibration. and this molecule can bend faster at a higher temperature. That means it absorbs heat and the temperature goes higher. That means we have a little bit molar vibrational heat capacity. It's about 0.5. So that accounts for the difference between our prediction, 3R, and the experimental value. Triatomic and polyatomic molecules sometimes have notably different isochloric molar heat capacity. Another example, SO2, sulfur dioxide. Its literature value is 31.3 joule per mole Kelvin. It's much greater than like 25.4 for this hydrogen sulfide. So both are triatomic. They both are nonlinear. How come this one has much larger value than this one? Well, it's simply because in SO2 atoms are heavier, so they usually have smaller vibrational energy spacings. It's just a little easier to promote this heavier molecule SO2 from the lowest vibrational energy level to the higher vibrational energy level. We have more vibrational heat capacity, so that's why this is larger. Alright, so yeah, if you have a really heavy molecules with heavy atoms, they may have a larger molar heat capacity. Then lighter ones, over here you have hydrogens, you have hydrogens. Alright, so there are always exceptions. And if you have polyatomic molecules, for example, if you have a large molecule with 50 atoms, and there are approximately 144 vibration modes. So even if each vibration mode contributes a very little amount molar heat capacity, and if you add up 144 such vibration modes, it can still be significant, and they still have a larger isochloric molar heat capacity than those smaller molecules. In summary, at room temperature, atomic gases have a CVM of 1.5 R, only because they have only 3 translational modes. The atomic molecules usually 2.5 R because we have 3 translational modes and 2 rotational modes. Now if you have a linear triatomic or linear polyatomic molecules, well, it's just 2.5 R plus their vibrational CVM. It's very often small, but again, if you have really heavy atoms, this can become larger. If you have many atoms and therefore many vibrational modes, you might have larger CVM. What about the CVM of non-linear triatomic and polyatomic molecules? Well, it's going to be 3R at least. Why 3R? 3 translation, 3 rotations. Together, you have 0.5 R times 6, you get 3R. And then we need to take this into account. The vibrational isochloric molar heat capacity. It depends on the situation. Again, if you have heavy atoms in the molecule, or if you have many atoms, and then its CVM might be significantly greater than 3R. Later in section 2.9, we can prove CPM is simply CVM plus R for ideal gases. What is this CPM? It's actually isobaric molar heat capacity. It's different from molar isochloric molar heat capacity. What does that mean? It tells you if we heat up a substance, and increase its temperature by 1 Kelvin, actually we cannot compute the amount of heat unless we know the condition. For example, it can be isochloric, it can be isobaric, and they actually differ by R if your substance is an ideal gas. Alright? For real gases, well, this equation holds approximately CPM is approximately CVM plus R. For liquid or solid, never use this equation. Again, this equation is for ideal gases exactly, and for real gases approximately. This equation is almost never correct for a liquid or a solid. Okay, even if it's correct, it's just coincidence. Okay, Now for a liquid or solid, well, it can be as small as 0. For water at 4 degrees Celsius, CPM is equal to CVM. Okay, that's mind-boggling already. And then for some other liquid like benzene, the difference can be as large as 5R. But in the end, CPM can never be less than CVM. I wrote a paper on this topic because I saw in several PChem textbooks they've got a wrong statement. They asked students about under what conditions CPM can be less than CVM, and usually they use water at for example 1 degree Celsius as the example. Okay, that's actually wrong. For water at 1 degree Celsius, CPM is still greater than CVM. So I wrote a paper on this and published the paper in ACS Omega, and you can click this website to see the proof. And also you can just search for my papers. For example, can CPM be less than CVM? And you probably will find this paper. Over here we have a table of the isochloric molar capacity of selected gases at 15 degrees Celsius and 1 atm. This is not 25 degrees Celsius, but as I mentioned, isochloric molar heat capacity is roughly constant within a small or even moderate temperature range. So between 15 and 25 degrees Celsius, those numbers are pretty much just the same. Now let's look at monatomic gases, argon and helium. The CVM is just 12.5 R. It's just 12.5 joule per mole Kelvin. It's just 1.5 R. From the 3 translational modes, diatomic, you have the values here, and you have the values of molar heat capacity divided by R. It's roughly 2.5. Okay, from this 2.49, 2.45 all the way to here 2.8. If you look at chlorine, chlorine is 2.98, a bit more than 2.5. Why is that? Chlorine atoms are just heavier, than all those other atoms. When you have heavy atoms, the vibrational energy spacings are small, so it's actually a little easier to heat up chlorine gas so that these chlorine molecules can occupy some higher vibrational energy levels. Therefore, vibrationally, chlorine may absorb some heat. Therefore, I think the difference between 2.98 and 2.5 R, well, usually it's just vibrational of chlorine too. Triatomic, again, there are 2 different triatomic molecules, linear versus nonlinear. I think CO2 is linear, and then if it's linear, it should be what? It should be 2.5 R. But over here we have 3.4 R. This is because, look, we have CO2, carbon dioxide. There are actually 2 bending motions. The carbon-oxygen bond angle is, well, supposed to be 180 degrees, but if you heat it up, CO2, a linear CO2 may undergo like bending motions, and the CO2 molecules can absorb heat to speed up the bending motion. So it needs to kind of absorb more heat. Therefore, this is more than 2.5 R. Now let's look at some nonlinear molecule like H2S, hydrogen sulfide. It's about 3R, a bit more than 3R. This is nonlinear, so we have 3 translations, 3 rotations. Our prediction is just 3R. And why 3.06? Well, just a little bit from vibration. And we mentioned SO2, a lot more than 3, N2O, significantly more than 3. Alright, what about CS2, carbon disulfide? I think this is much greater than 2.5 because of the very small vibrational spacing. I think I didn't do the actual calculations for this molecule, but this is just a very large number actually. So that usually tells you this molecule has very small vibrational energy spacing. Alright, Now get back to this equation. du is dq plus dw, and dw is negative p external dv. We're going to use this equation and this equation to analyze an isobaric process. In an isobaric process, dp is 0. There's no change in pressure. It actually indicates P external is equal to P, because if it's different, if P external is greater than P, well, the system pressure will change until it increases to P external. If P external is smaller than P, and the system, I think, will just expand until its pressure decreases until it reaches this low level. Therefore, for an isobaric process, usually we just assume P external is equal to P. Alright, and then it's easier for us to get the expression for work, actually, because dW is negative P external dV, and we can replace P external with P. So dW is negative P dV, and du is just negative P dV plus dq. And also this dq can be rewritten as dqp now, because we know the pressure is constant. It's an isobaric process. dq itself is an inexact differential, but if we know it's isobaric, we can actually integrate dq now. This becomes exact differential. Alright, now to specify the isobaric condition, du sub p is negative p dv plus dq sub p. And we have this equation. dq sub p is du sub p plus p dv. We just move this p dv to the left hand side. Because pressure is constant, so we can move this p back into the differential. So it's du sub pressure plus dpv sub pressure. Alright, and we can actually sum up u and pv. So this two, remember dx plus dy is just the exact differential of x plus y. So you can do the same thing here. It's just the exact differential of the sum here under constant barrier condition, u plus pv. So it's neat. You know, if we have isobaric condition, the change of u plus pv is simply the amount of heat. Alright, for convenience, you know, we just define enthalpy H to be u plus pv, because if you measure the amount of heat under isobaric condition, let's say you get like 5 joules, you can say, well, the change of u plus pv is 5 joule. Or you can say the change of H is 5 joule. You know, the latter is more convenient. You don't have to say, well, the change of internal energy plus the product of P and V is 5 joule. You just say the change of enthalpy is 5 joule. And backward is more convenient. For a chemical reaction, if you know the enthalpy of the products and the enthalpy of reactants, you take the difference, you know how much heat can be released or absorbed by this reaction under constant barrier condition easily. Right? So you just need to know those enthalpy values. Or you can know, well, what's U and then what's PV for the chemicals, and then you can still do the calculation, but it's less convenient. Alright, again, for convenience, we define H to be U plus PV, and D sub dQp is DHP. And QP is just delta H under constant barrier condition. So that's neat. And also under isobaric condition, for most substances within a small or even moderate temperature change, so a few kelvins or even tens of kelvins, Q sub P is proportional to delta T as well. So we have some proportionality. It's called isobaric heat capacity. C sub P is just dQp over dt. And because dQp is equal to dHp, again, the change of enthalpy is equal to the amount of heat for the isobaric process, we can write Cp is delta H over delta T under constant pressure. Cpm is just Cp over N. It's isobaric molar heat capacity. Cp is extensive, Cpm is intensive. Cpm does not depend on the amount of the substance. The temperature dependence of Cpm is often negligible within a small or moderate temperature range. They may differ by, for example, 1% if the temperature changes by 10 Kelvin. So 1% is often considered negligible in thermodynamics. unless you need a really accurate data. For ideal gases, CPM is equal to CPM is equal to CVM plus R. For real gases, we still have this equation, but well, this equation holds approximately. Again, for liquids and solids, never use this equation. Alright, for a liquid or a solid, the difference between CPM and CVM can be as small as 0 for water at 4 degrees Celsius, and it can be as large as 5R for benzene, liquid benzene, under certain conditions. But in the end, CPM can never be less than CVM. Now we'll look at two numerical examples. One is isochoric, one is isobaric. In these two examples, we will calculate delta H, delta U, Q, and W. Alright, so example problem 2.6.1. Calculate delta U, delta H, Q, and W when the temperature of 0.2 mole argon increases from 20 to 40 degrees Celsius in an isochoric process. The CVM of argon is given. Alright, so if it's isochoric and we know CVM, well, it's easy to compute Q sub V. Alright, we'll do that. And again, CPM is equal to CVM plus R because we assume this is ideal gas. Now for isochoric process, there's no volume change. dW is negative P, external dV is 0. So work is 0. So whenever you see an isochoric process, the first thing is you write down dV is 0 and also work is 0. There's no expansion or compression work. And therefore du sub V is dQ sub V, and dQ sub V is just CV dt. This is the definition of heat capacity. Alright, for the isochoric condition. Now we can integrate both sides. Delta U sub V is Q sub V is integral of CV dt. CV is N times CVM. We plug in all the numbers, we get 50 joule. How do we get delta H? H is U plus PV, so delta H is delta U plus delta PV. We know delta U is 50 joule. Now we calculate delta PV. It's an ideal gas. So delta PV is delta nRT. And how do we get delta nRT? Well, plug in numbers. We get delta H is 83 joule. So these two numbers differ. Alright, because actually PV changes. This PV changes. Why does this PV change? Because the temperature changes. When the temperature changes, nRT changes, and PV is equal to nRT. Although this is not an isobaric process, but we can still compute delta H by integrating Cp dt directly. How is that possible? Because, again, this is ideal gas. For ideal gas, H only depends on temperature. And why is that? We mentioned U only depends on temperature for ideal gas. H and U differ by PV or nRT. Alright? And it's an ideal gas, right? So, and U depends only on temperature, and then PV is equal to RT, which only depends on temperature. So we conclude H only depends on temperature, right? And then delta H is simply over here, we just look at the temperature change. We get 83 joules. So these two calculations are both correct. And also we can imagine this. Let's somehow change the state of the system. In the isochoric process that consists of two steps, we can do isobaric first and then do isothermal. Alright, so if you look at the initial state and the final state, okay, from 20 degrees Celsius to 40 degrees Celsius, and it's isochoric. From V initial to V initial, that's isochoric. But because enthalpy is a state function, I can break down this isochoric process into two steps. First isobaric and then isothermal. In the isobaric process, I hold the pressure constant. Only the temperature changes. So obviously we can use this equation. Delta H is Q sub P and then it's integral of Cp dt. What about isothermal process? We know for the ideal gas, H only depends on temperature. And there's no change in temperature. Therefore delta H is 0. So we can sum up the change in enthalpy in these two steps. The result is just the integral of Cp dt. That's why we can just use this equation. Delta H is the integral of Cp dt directly, even though it's not an isobaric process. Again, my argument is simple. It's not isobaric, but I can break down this isochoric process into two steps. One step is isobaric, so I can use this equation. In the other step, delta H is 0 anyways. Now example problem 2.6.2. Calculate delta H, delta U, Q, and W. In an isobaric process, the temperature changes from 20 to 40. The CVM is 1.5 R, the CPM is CVM plus R. Because it's isobaric, dP is 0, we have dQp is equal to dHp, so we integrate both sides, plug in all the numbers, we get 83 joules. Delta U is delta H minus delta PV, and delta PV is just delta nRT. And we know the temperature change, we know delta H, we get 50 joules for delta U. Alright, how about work? Work is delta U minus Q. Delta U is 50, and in this isobaric process, Q is not 0. Alright, Q actually is 83. So we get W is negative 33. It's negative. That means the system expands and does work to its surroundings. Alright, so if you look at these two numbers, 50 and 83, these two numbers, 50 and 83, well, it's just because the system is ideal gas, and for the ideal gas, U and H only depend on temperature. And if we look at the temperature, it's from 20 to 40. Over here it's 20 to 40 in this isochoric process, 20 to 40 to the isobaric process. And because U and H only depends on temperature, so whether it's isochoric or isobaric, we'll get the same values for U and H. However, we get different values for Q and W. Alright? In the previous example, it's isochoric, W is simply 0. Over here, W is negative 33. Why is that? Q and W are path functions, and Q and W really depend on the process. So even if delta U and delta H are the same between these two examples, Q and W can be different. Again, I want to emphasize the definition of enthalpy. Enthalpy is U plus PV. For an ideal gas, you can rewrite PV to nRT. Alright, only for ideal gas. For PV, for a real gas, PV is approximately nRT. For a liquid or solid, never write PV equals nRT. Again, Q is a path function. When the process is isochoric, USdQ is equal to CVdT. Okay, for isochoric process. What if the condition is isobaric? If it's isobaric, dQ is Cp dt. Alright, and Cp and Cv are often different. They are almost always different. Cp is almost always greater than Cv. Chapter 2. Internal energy, work, heat, and enthalpy. Section 2.7. Reversible and irreversible processes. In an isothermal expansion process, when the difference between P and P external is infinitesimal, this process is called a reversible process. We can assume P equals P external and P is greater than P external in the reversible expansion, only because we can assume the difference between P and P external is negligible. For simplicity, we simply just use P is equal to P external in all numerical calculations for a reversible process. But if it's expansion, we can say P is greater than P external at the same time by an infinitesimal amount. Reversible processes cannot be achieved in the real world because the pressure difference is infinitesimal, and therefore the expansion or compression can be infinitely slow. However, reversible processes provide us a theoretical limit to the amount of work that can be done on the system or by the system, and therefore reversible processes are frequently studied in thermodynamics. Later, we will prove that the entropy of the universe remains unchanged in a reversible process. Any irreversible processes would result in the entropy increase of the universe and therefore it cannot be reversed. This is because the reversal of an irreversible process would result in the entropy decrease of the universe. While the entropy decrease of the universe is in violation of the second law of thermodynamics. In summary, when we see reversible processes, we may assume P is equal to P external. Or you can say the difference between P and P external is infinitesimal. A process is considered irreversible if any part of this process involves expansion or compression due to the finite difference between pressure and external pressure. Chapter 2, Internal Energy, Work, Heat, and Enthalpy, Section 2.8, Isothermal Processes. Reversible and irreversible isothermal expansion and compression were studied in a previous section. Therefore, we will just briefly review these processes here. Example problem 2.8.1. Calculate the amount of work and heat involved in the following irreversible versus reversible isothermal processes. A. A 80-liter ideal gas with 1 bar pressure is compressed to 20 liters and 4 bar pressure by an external pressure of 4 bars. This is an irreversible process because the difference between P external and P is finite. W is negative integral P external dV. We plug in all the numbers, we get positive 240 bar liters. Because this is compression, the surroundings does work to the system. B. The same 80-liter ideal gas with the same 1 bar pressure is compressed to 20 liters and 4 bar. This time by P external is equal to P. This is a reversible process. Still, work is negative integral P external dV, but this time in a reversible process P external is equal to P. So we replace P external with P, and pressure is nRT over V because it's an ideal gas. We integrate 1 over V dV, which is the natural logarithm of V, and then multiply by negative nRT. The result is negative nRT times the natural logarithm of 4. We do not know the temperature, but we do know it's an isothermal process. So PV is equal to nRT throughout the entire process for the ideal gas. We still plug in all the numbers. We get 111 bar liters. So we have 240 bar liters in the irreversible process, 111 bar liter in the reversible process. Note that the system cannot be compressed if P external is less than P. So P external, has to be either P or slightly greater than P. Therefore, the lower limit of the compression work is achieved in this reversible process in which P external is equal to P. But again, they actually differ by a infinitesimal amount. When the system expands, the lower limit or the most negative of the expansion work is also achieved in a reversible process. So the reversible processes always provide a lower limit for the expansion work. At the same time, they provide an upper limit for heat in an isothermal process of ideal gas, because we know Q is delta U minus W, and delta U is delta PV plus delta KE. For an ideal gas, delta PV is always 0. For the isothermal process, the kinetic energy of the ideal gas only depends on temperature. When temperature remains unchanged, KE remains unchanged. Therefore, we have Q is equal to negative W. So in a reversible process, we get the lower limit for W, and then an upper limit for Q. Chapter 2, Internal Energy, Work, Heat, and Enthalpy, Section 2.9, Adiabatic Processes. A system may be surrounded by an adiabatic wall or a diathermal wall. A diabatic wall does not allow energy transfer. Q is 0. A diathermal wall allows energy transfer, so Q is very likely non-zero. DIA is a prefix that means across. For example, in the words diameter, diagonal, and over here diathermal. In an adiabatic process, Q is 0. There's no heat transfer. And there are two subtypes of adiabatic processes: reversible or irreversible. In a reversible process, P is equal to P external. In an irreversible process, there is a finite difference between the system pressure P and the external pressure. Now, how do pressure, volume, and temperature of an ideal gas change in a reversible adiabatic expansion or adiabatic compression? We have this derivation. First, Q is 0 for the adiabatic process. Therefore, dQ is also 0. du is equal to dW. dW is negative P external dV. For a reversible process, P is equal to P external. Therefore, du is equal to negative PdV. The internal energy of an ideal gas depends only on its temperature. Again, this is just because the potential energy of an ideal gas is always 0, and the kinetic energy can be determined by its temperature. Therefore, we have this equation: du sub T is equal to 0. If temperature is held constant, then du is 0. And therefore, du can be separated into two components. It's du sub V and du sub T. It means the internal energy depends on volume and temperature. You may ask, does this internal energy depend on pressure? The answer might be surprising. Yes, the internal energy does depend on pressure, but we do not write a third component here. This is because pressure depends on V and T. Out of PVT, there are only two independent variables. So you can write U as a function of VT or PT or PV, but you do not write this U as a function of three variables at the same time. That's going to be misleading. So again, we can assume this U depends on volume and temperature. And because dUT is just 0, so du is just dUV. dUV, that means the internal energy change in an isochoric condition. And therefore, dUV is dQV, and dQV is CVDT. So for a adiabatic reversible process, we have du is equal to CVDT. It sounds strange because in this process, volume is not held constant. But still, we can write du is equal to CVDT because the system is an ideal gas. Again, for an ideal gas, well, the internal energy only depends on temperature. Therefore, we can write this. And therefore, CVDT is equal to du, and du is equal to negative PdV. We can put these two together. And the pressure is nRT over V for ideal gas. So we have this equation. And do not integrate both sides yet, because if you look at the right hand side, it contains two variables. It contains V, it contains T. On the left hand side, well, it contains only one variable, but just because on the right hand side there are two variables, we have to solve this issue first. The simplest way is to divide both sides by temperature. And then we have CVDT over T is equal to negative nR over V dV. Now if you examine both sides, on the left hand side it contains only T. On the right hand side it contains only V. And we can integrate both sides, and we can have the lower limit and upper limit of the left integral to be from Ti to T final. And over here it's from Vi to V final. In a reversible adiabatic expansion or compression, we have this equation: CVDT over T is equal to nR dV over V. Now we integrate both sides. And the integral of dt over T is the logarithm of T. The integral of dV over V is the logarithm of V. Therefore, we have this equation after integration: Cv times the difference between LNT final minus LNT initial is equal to negative nR times LNV final minus LNV initial. We need to know how to deal with logarithms. The difference between two logarithms is the logarithm of a division. So we have this here, and we have Ln V final over V initial on the right hand side. Both sides divided by CV, and then we have this equation. And now again, if we raise e to the power of this logarithm and e to the power of this logarithm, we get this equation. T final over T initial is equal to V final over V initial to the power of negative NR over CV. NR over CV can be written as R over CVM if we divide both the top and the bottom by the number of moles N. So again, the temperature ratio is equal to the volume ratio raised to the power of negative NR over V. Therefore, given the volume ratio between the final and the initial state, which is V final over initial, we can somehow calculate the temperature ratio. Now, very often we're given both the initial volume and the final volume, or sometimes the problem tells us this information: the volume of the system is doubled in a reversible adiabatic process, and then this ratio is just 2. Or some people can just simply tell you the volume is tripled, the volume is quadrupled, and then you know what the ratio is. When the volume decreases, we call that a compression, and when the volume decreases, the internal energy increases. This is just because we're talking about an adiabatic process, so Q is 0, and then the system is compressed, so work is positive. Therefore, Q plus work is greater than 0. Delta U is greater than 0. And if delta U is greater than 0, the internal energy increases. And because the potential energy is always 0 for an ideal gas, that means the kinetic energy increases in the compression process. If the kinetic energy increases, we know the temperature increases. On the other hand, if the volume increases, its expansion, the system does work to its surroundings, work is negative, and Q is 0 for this adiabatic process. So overall, the internal energy decreases, the kinetic energy decreases, the temperature decreases. That explains this negative sign over here. If V final is greater than V initial, and then this is less than 1, TF is less than TI. If VF is smaller than VI, well, it's compression, and by looking at this equation, this value is going to be greater than 1. Temperature is going to increase. In a reversible adiabatic expansion or compression, we have this equation. The temperature ratio is equal to the volume ratio to the power of negative NR over CV. And also, NR over CV is simply R over CVM. For ideal gas, Cp minus Cv equals NR. We'll prove this. When PVT of an ideal gas change, we may assume the internal energy and enthalpy of the system depend on only 2 of the 3 variables. Again, PVT, there are 3 variables, but only 2 are independent variables. The third one is treated as a dependent variable. So we can write this formula: du is equal to du sub v plus du sub t. So when we write this, we assume internal energy is a function of 2 variables, volume and temperature. So over here, we hold volume constant. We allow temperature to change, and we get the internal energy change based on temperature change. Here, temperature is constant. This is how internal energy change when the volume changes. So we have these 2 together, but remember, when temperature is constant, the internal energy of an ideal gas remains constant. So this part is simply 0. Therefore, du is simply du sub v for an ideal gas. And du sub v is dq sub v. And dq sub v is cv dt. Now we'll do similar analysis to dh. We're going to assume h is a function of 2 variables, pressure and temperature. Again, h also depends on volume, but that dependence is included in these 2 terms implicitly already. And now we can expand this. This h is just u plus pv, so we have 3 terms now. It's dh with constant pressure, and du over sub t, and dpv sub t. Remember, this du sub t is just 0 for the ideal gas, because if you have an ideal gas, the potential energy is always 0, and if the temperature is constant, the kinetic energy remains unchanged. So this du sub t is 0. dpv sub t is also 0 for ideal gas. It's just because pv equals over t, and if temperature is constant, pv is constant. So actually, the last two of the three components are both 0. dH is just dH sub P for an ideal gas. Therefore, for an ideal gas, we have this equation: dH is dH sub P is equal to dQ sub P is equal to Cp dt. Now we can take the difference between these two equations. Cp dt minus Cv dt is simply dH minus du. dH minus du, based on the definition of H, is simply dPV. dPV is dnRT because it's an ideal gas, and dnRT is nR times dt because n and r are constant. And both sides divided by dt, we have Cp minus Cv is equal to nR. And now we can rewrite this equation for the adiabatic reversible process. The temperature ratio is the volume ratio to the power of negative nR over Cv. And nR is actually Cp minus Cv. So we can rewrite this to be Vf over Vi to the power of 1 minus gamma. What is gamma? Gamma is just defined to be Cp over Cv. So this is just for convenience. For some gases, some solids, liquids, if you are given the value of gamma, you know what Cp over Cv is. Gamma is always greater than 1. Except one rare exception, which is water at 4 degrees Celsius, and then gamma is 1. Gamma is never less than 1. Gamma is always greater than 1. Because Cp is n times Cpm, Cv is n times Cvm, so gamma is also Cpm over Cvm. Now let me give you one example. If you have a helium gas, Cvm is 1.5 R, Cpm is then 2.5 R. So the value of gamma is 2.5 over 1.5, which is 5 over 3. In a reversible adiabatic expansion or compression process of an ideal gas, the temperature ratio is the volume ratio to the power of 1 minus gamma. And again, gamma is Cp over Cv. Gamma is Cpm over Cvm. What if you have a molecule, for example, a diatomic molecule, and usually Cvm is 2.5 R, Cpm is 2.5 plus 1, 3.5 R, and gamma is then 7 over 5, which is 1.4 for many diatomic molecules in the gas phase. And this equation is often used to calculate the final temperature given the initial temperature, as long as we know the ratio between V final over V initial. So if I'm telling you it's a helium gas, then gamma is 5 over 3, and I tell you the volume is doubled in this adiabatic reversible expansion or compression, well, then you just plug in all the numbers. If the volume ratio is 2, just plug in 2 here. If gamma is 5 over 3, just plug in 1 minus 5 over 3 on top. And then you'll be able to get the ratio between T final and T initial. If you know what the value of T initial is, you can easily compute T final. Again, this equation applies to an ideal gas that undergoes reversible adiabatic expansion or compression. Now, if we know T final, T initial, it's very simple to get the change of the internal energy, because du is Cv dt for an ideal gas. dH is Cp dt for an ideal gas. So delta U is just Cv times delta T. Delta H is just Cp times delta T. Again, the difference between delta U and delta H is delta PV. By definition, delta PV is simply delta nRT. Delta nRT is simply nR delta T. And also Cp and Cv differ by nR for an ideal gas. And again, Q is 0, so if you have the value of delta U, it's also the value of work, because work is delta U minus Q, and Q is 0 for this adiabatic process. Again, in a reversible adiabatic expansion or compression, we have the temperature ratio is equal to the volume ratio to the power of 1 minus gamma. Gamma is Cpm over Cvm. It's always greater than 1 except one case, which is water at 4 degrees Celsius. As the volume increases, the system loses energy. Since the P is always 0, then we lose kinetic energy. The kinetic energy of the system decreases in this adiabatic expansion. On the other hand, if it's compression, then the kinetic energy and temperature of the system both increase. We can also compute the pressure ratio. How do we do this? Well, we go from here, the ratio between V final and V initial to the power of 1 gamma over here. is equal to T final over T initial, right? And the temperature is simply PV over NR. So T final is P final, V final over NR. T initial is P initial, V initial over NR. And we can cancel NR and NR, and we have P final, V final on top, P initial, V initial on the bottom. And somehow we can just move this V final over V initial to the left hand side. For example, we can divide both sides by V final and multiply both sides by V initial. Alright, and then we have P final over P initial is equal to V final over V initial to the power of negative gamma. Again, gamma is usually just greater than 1. So that means the rate of the decrease of pressure is faster than the increase of volume, right? By just looking at this equation, because this gamma is greater than 1. Also, we can relate the temperature ratio to the pressure ratio. That's just algebra, because from this equation we can just have left and right to the power of negative 1 over gamma. So this part to the power of negative 1 over gamma, we get just V final over V initial, we put it here. And this part to the power of negative 1 over gamma, we put it over here. Alright, so we get this equation. And again, T final over T initial is V final over V initial to the 1 power of gamma, and we can express the volume ratio in terms of pressure ratio, and we put everything together. We relate the temperature ratio with the pressure ratio. It looks a little complicated. Alright, it looks a little complicated. It's PF over PI to the power of 1 minus 1 over gamma. So again, pay attention to this negative sign here. That's why you have negative 1 over gamma and you have positive 1 over here. Pay attention to the signs. Now some numerical examples. Let's look at 2.9.1. Ideal monatomic gas expands until its volume doubles in a reversible adiabatic process. The initial temperature is 300 Kelvin. Calculate its final temperature first, and then calculate delta U, delta H, Q, and W. So if we have a ideal monatomic gas, there's no rotational motions, no vibrational motions. So we just need to look at the translation. In each dimension, the molar heat capacity is 0.5 R. 3 dimensions, 1.5 R. So CPM is equal to 1.5 R plus R. We get 2.5 R. What's the value of gamma? It's just 2.5 over 1.5. That's 5 over 3. Now we have the temperature ratio is equal to the volume ratio to the power of 1 minus gamma. We plug in the value of gamma. Well, it's 5 over 3. 1 minus 5 over 3 is negative 2/3. And we got this number 0.63. So T final over T initial is 0.63. Plug in the value of the initial temperature. T final is 189 K. This temperature is lower than the initial temperature only because the system did expansion. It loses energy that way. Now for an ideal gas, the internal energy and enthalpy only depend on temperature. Delta U is integral of Cv dt. We get this number. Delta H is Cp dt. We get this number. Alright, or you can say delta H is delta U plus delta PV. So given delta U over here, negative 277, and then delta PV is simply just delta nRT. Delta nRT is nR delta T. And you can compute delta T easily. We get this number. What about Q? Q is just 0 because it's adiabatic. W is just delta U because Q is 0. Now let's look at the irreversible adiabatic process. Okay, it's a little bit more tricky. Let's look at an adiabatic process. That means Q is 0, and let's assume the process is irreversible. P is different from P external. For convenience, we'll just say, how about we're just use a constant external pressure. All right, a constant external pressure. Again, we'll just derive first. Q is 0 because it's adiabatic. Delta U is Q plus W, and because Q is 0, so delta U is just equal to W. And W is negative P external dV. And over here we need to have this equation. Why is that? Because usually the system expands until its pressure is equal to the external pressure. So we can assume P final is P external. Okay, this is when the expansion or compression stops. So negative P external delta V is negative P final delta V. And P final, we'll just copy that. Delta V is V final minus V initial. And then over here you can see, well, clearly it's just P final times V initial minus P final times V final. Alright, I'm going to use P final, V final as the common factor. I put it here. And it's going to be the P final times V final times this VI over VF minus 1. Alright? Where does this come from? So if you multiply this P final, V final, and VI over V final, well, you get P final times V initial. P final times V initial, right? Over here. There are two negative signs that cancel. Also, we have negative P final, V final, so it's right here. Negative 1 times P final, V final. The reason I put it this way is just because P final, V final can be written as nRT final. And over here, very often we will be given the ratio between the initial and final volumes. Alright, we can calculate delta U in this way because it's an ideal gas. For ideal gas, delta U is always integral of CV dt, so it's just CV delta T times CV, it's just CV times T final minus T initial. Now we have delta U, we have W. Alright, W is here, delta U is here. And we know delta U is W because Q is 0. So over here, this is delta U is equal to W plus Q, and Q is 0. Alright, so we have this equation. So if you look at this equation, if we are given the value of CV or molar CV, we have this. And if we're given the initial temperature and the ratio between the initial and final volumes, we'll be able to solve for TF. Because in this equation, if we're given this ratio, this becomes a number. NR usually are provided, and then if CV is also provided, this equation contains only one variable, which is T final. We just solve for T final. Alright, once we have T final, we'll just get delta U, right, or get W. We can also get delta H, right? Delta H is the integral of Cp dt for ideal gas. So we'll get this formula. So it's easy enough to get delta U, delta H, and W. What about Q? Q is just 0 because it's adiabatic. Oh, just remember, we're talking about the irreversible process. So the difference between the system pressure and external pressure is finite. And also, for convenience, we'll just say this external pressure is a constant. It's easier to calculate that way. Now, another numerical example for an adiabatic process, but this time it's irreversible with a constant external pressure. So we're going to just use this equation right away from the previous page over here. We derived this. So I'm not going to derive this again. I just want to show you the rough idea. The rough idea is this. Q is 0, so delta U is W. Delta U is the integral of CV dt. And W is simply negative P final times delta V. Why is that? It's just because at the end of the expansion of compression, the P final should be equal to P external. Otherwise, the expansion or compression should continue. Alright, get back to this. I'm going to just use this equation. Now let's read the question again to get the information. The volume is doubled, so therefore VI over V initial is 1 over 2 because, you know, after this process the volume is doubled. V final is 2 times V initial, so we have this information. We do not know final temperature. We do have the initial temperature. I think it's 300 Kelvin over here. And we have the molar isochloric heat capacity for this ideal diatomic gas, roughly 2.5 R. So we're plugging 2.5 NR here because this is CV. CV is N times CVM. And if you look at these two sides of the equation, we see N here, they cancel. I see R and R, they cancel. We get this equation. And then we plug in T initial is 300 Kelvin. We solve the equation, we get 250 Kelvin. Now for ideal gas, its internal energy change is simply the integral of CV dt. And then we plug in the numbers, so we get this number. Q is 0, W is delta U minus Q, so W is equal to delta U. Delta H is just delta U plus delta PV. Delta PV is just NR delta T. So we get this number. Or you can simply calculate this delta H in this matter. It's the integral of Cp dt, and it's just NCPM dt. So we have N here. We have CPM here. CPM is CVM plus R. We have delta T here, T final minus T initial. And we get the same value for delta H. So there are two different ways to compute the enthalpy change. They both result in the same value, negative 291 joule, for this numerical problem. Again, this is not isochoric, this is not isobaric. However, we can still, do this calculation. We can still say du is CVDT, dH is CPDT, because our system is an ideal gas. When you have an ideal gas, the internal energy and enthalpy only depend on temperature, and therefore for the calculation of the change in internal energy, we can always divide the process into two steps. The first step, make sure it's isochoric, and then we can use integral of CVDT. The second step, make sure it's isothermal, and then the internal energy change is just 0. How do we compute the change in enthalpy? Again, two steps. The first step has to be isobaric, and then you can calculate delta H. Delta H is simply Q sub pressure, Q sub P. That's just the integral of Cp dt. Alright, we just calculate that step, isobaric. The second step, make sure it's isothermal. If it's isothermal, delta H is just 0. So overall, delta H is still the integral of Cp dt. So this is a trick to compute delta H and delta U for an ideal gas. Do not do that for solids and liquids. Chapter 3, Internal Energy and Enthalpy. Section 3.1, U and H depend on PVT. The internal energy and enthalpy of the system depend on the pressure, volume, and temperature of the system. For a fixed amount of pure substance, out of pressure, volume, and temperature, there are only two independent variables. For ideal gas, because PV equals RT, then we can easily determine temperature given PV, or determine P given VT, or determine V given PT. For real gas, there are also only two independent variables out of PVT. If we look at the Reynolds equation, you can see pressure depends on volume and temperature. And also, if you want to determine the volume, we just need to know the pressure and temperature of this Reynolds gas. For liquids and solids, it's not obvious, but still, out of PVT, there are only two independent variables. It's just the equations that connect PVT are much more complex for liquids and solids. Now let's look at three equations that shows how PVT depends on each other. dV is delta V over delta T times dt plus delta V over delta P times dP. Pay attention to the subscripts over here. This means pressure is held constant. Over here, temperature is held constant. So we can examine this equation. When pressure is constant, dP is 0. When pressure is constant, we simply have dV is equal to delta V over delta T times dt. That makes sense. What if temperature is constant? When temperature is constant, dt is 0. So dV is equal to delta V over delta P times dP. It also makes sense. Similarly, we can express dP in terms of dt and dV. We can express dt in terms of dP and dV. For solids and liquids, delta V over delta T under constant pressure condition and delta V over delta P under constant temperature condition are roughly proportional to the volume of the liquid or solid of interest. And therefore, we define two parameters, alpha and kappa, as follows. We say delta V over delta T under constant pressure condition is approximately alpha V. Alpha is roughly a constant for a liquid or solid within a moderate temperature range, a moderate pressure range. And similarly, we say delta V over delta P under constant temperature condition is equal to negative kappa V. This kappa is also roughly a constant within a moderate temperature range and a moderate pressure range. Again, it just shows you delta V over delta P is proportional to the volume of the liquid or solid. Why do we need a negative sign here? It's just because when a liquid or solid undergoes a higher pressure, its volume decreases. So on the left hand side, we have delta V over delta P under constant temperature condition, and it's always negative. So by having this negative sign here, we can ensure the value of kappa is always positive. That's just for convenience. It's just because if you want to tabulate the values of kappa for 200 different substances, it's too tedious to just simply write this negative sign in front of every single value. Now kappa is always positive by having this definition instead. Alpha is the isobaric thermal expansion coefficient. Well, it's denoted by beta in some other physical chemistry textbooks, but UPAC use alpha. ACS officially use alpha, but occasionally use beta, unfortunately. And kappa is the isothermal compressibility. This is a little too long, isobaric thermal expansion coefficient alpha, so sometimes we'll just say thermal expansion coefficient. And when we mention kappa, usually we just say compressibility, and that indicates isothermal compressibility. Alpha is 1 over V times delta V over delta T under constant pressure condition. Kappa is negative 1 over V times delta V over delta P under constant temperature condition. Kappa is always positive. Alpha is almost always positive, except for water at 4 degrees Celsius. The physical meaning of alpha is the temperature dependence of the relative change of volume. Well, why did I say relative change of volume? Because we have delta V over V. Delta V over V is the relative change of volume. Alright, so really we are looking at delta V over V and then divided by delta T. The physical meaning of negative kappa is the pressure dependence of the relative change of volume. The SI units of alpha and kappa are Kelvin to the power of negative 1 and Pascal to the power of negative 1. Well, we can just look at the formula here. The unit of V cancels the unit of V, so really we have 1 over Kelvin here. In the expression of kappa, the unit of V cancels the unit of V, and then it's just 1 over the unit of pressure. So the SI unit for kappa is Pascal to the power of negative 1. The values of alpha and kappa of liquids and solids are approximately constant within a moderate temperature range or pressure range, sometimes even within a wide temperature and pressure range. So they can be treated as constant. And if alpha and kappa are constant, we can approximately say alpha is roughly delta V over V and then divided by delta T. Again, on top we have the relative change of the volume. On the bottom we have just the change of temperature. If we look at kappa, on top we have delta V over V, that's the relative change of the volume. On the bottom, that's the change of pressure. Just don't forget about this negative sign for kappa, and don't forget about the conditions. Alpha is determined when pressure is held constant. Kappa is determined when temperature is held constant. For an ideal gas, alpha is simply 1 over the temperature of the gas, and kappa is 1 over the pressure of the gas. we can easily derive this. Alpha is 1 over V times delta V over delta T under constant pressure condition. For an ideal gas, PV equals nRT. Delta V over delta T is simply nR over P. Now let's look at this. nR over PV, that's just nR over nRT. That's 1 over T. Right? Because PV equals nRT. Kappa is negative 1 over V times delta V over delta P. And over here, we need to take the first derivative of volume with respect to pressure. Volume is nRT over P. So its first derivative is nRT over negative P squared. And we have negative 1 over V over here. You can see kappa is simply 1 over the pressure of the ideal gas. What about real gases? We know that real gases differ from ideal gases, but approximately you can still say alpha is approximately 1 over T, kappa is approximately 1 over P. Given the van der Waals equation, you can evaluate delta V over delta T analytically and also delta V over delta P analytically, and plug in those expressions to get the more accurate expression for alpha and kappa, but that's unnecessary unless you're really interested in doing a lot of tedious derivations. The values of alpha and kappa of gases are much larger than those of liquids and solids, simply because it's easier to change the volume of a gas than to change the volume of a liquid or a solid. Therefore, the alpha of a gas is much greater than the alpha of a liquid. And also, the alpha of a liquid is greater than the alpha of solid. We see the same trend for kappa. Kappa of a gas is much greater than the kappa of a liquid, which is much greater than kappa of a solid. Remember, it's possible to compress a gas with a high pressure, but it's much more difficult to compress a liquid with a high pressure or a solid. For liquids and solids, alpha and kappa are approximately constant within a wide temperature range and a wide pressure range. And also kappa and alpha are pretty small. The reason we introduce these two concepts, alpha and kappa, is to just make it easier to analyze how the internal energy U and enthalpy H of a liquid or solid depend on pressure, volume, and temperature. We'll see that later. For a fixed amount of substances, we have the three equations. They are all correct for du, the exact differential of internal energy. This is just because out of PVT there are only two independent variables, and U depends on the state of the system. So if you are given PV or VT or PT, somehow the value of U is determined. Therefore, you can say U is a function of TV, U is a function of TP, U is a function of PV. Either way is correct. If we say U is a function of TV, then du is delta U over delta T, constant volume times dt, plus delta U over delta V, constant temperature times dV. Also, you can express du in terms of dt and dp. You can express the expression of du in terms of dp and dv. But I would say forget about the last two equations. We will almost never use these two equations. We will almost always use the first equation. It's just because the first equation allows for more convenient derivations and numerical calculations. By looking at this, delta U over delta T under constant volume condition. Constant volume, that means work is zero, then delta U is simply dq. dq over dt under constant volume, that's simply C sub V. This part is simply the isochoric heat capacity. So we have a familiar thermodynamic function over here. And we can worry about this later. How does delta U depend on delta V? And actually for an ideal gas, this part is simply zero, because for an ideal gas, U only depends on temperature. Now let's look at this a little bit more closely. Delta U over delta V. What is this? Delta U over delta V on a constant temperature condition. It's called internal pressure. Why is it called internal pressure? First, this U is internal energy, and it's delta internal energy over delta V, so it's called internal something. And also, if you look at the unit over here, this delta U is in joule, delta V is in cubic meter. So if you have 1 joule divided by 1 cubic meter, you get 1 Pascal. That's the SI unit for pressure. That's why this is called internal pressure. We can prove this delta U over delta V under constant temperature is simply T times delta P over delta T under constant volume minus P later in chapter 5. But why do we need this? Well, it's just because it's very hard to measure how this internal energy changes with volume. It's a lot easier to measure how pressure changes with temperature under isochoric condition. So this is easy to measure. It's also easy to measure temperature and pressure, so it's easy to obtain the value of delta U over delta V experimentally by doing this indirect measurement on how delta P changes with delta T. And also, for ideal gas, we can easily derive this. For a real gas, we probably can derive this as well. Even for a liquid or solid, if we can look up the values of alpha and kappa for the solid or liquid, we can compute delta P over delta T easily. So again, it's just for convenience. We want to do this. And also, I mean, it's just a lot easier for us to just, again, imagine, if we somehow have a gas, in a constant volume container, and then we change its temperature and then measure its pressure. It's just very easy to do this part. Unfortunately, we cannot prove this until chapter 5, so we're gonna just wait. Now let's just assume this equation is correct, and the du is simply cv dt, so this part is cv and this part is delta u over delta v. We are replacing this delta u over delta v with this part, T times delta P over delta T minus P. For a fixed amount of substances, H depends on 2 out of these 3 variables, PVT. You can say enthalpy depends on temperature and pressure. You can say H depends on TV. You can say H depends on PV. So either way, you can write out a equation of the exact differential of enthalpy. So dH depends on dt and dP, dH depends on dt and dV, dH depends on dP and dV. Again, we almost always use one of the 3 equations, this one in the bold font. We almost always say, well, H depends on temperature and pressure for convenience. And dH is delta H over delta T under constant pressure condition times dt plus delta H over delta P under constant temperature condition times dP. So over here, you can imagine we have a isobaric process. When it's isobaric, we proved that dH is just dQp. So really, you're looking at dQ over dt on a constant pressure condition. Isn't that just heat capacity under constant pressure condition, also called isobaric heat capacity over here? And delta H over delta P is more like complex, but we can prove this later in chapter 5. Delta H over delta P is simply volume minus temperature times delta V over delta T under constant pressure condition. Experimentally, it's easy to maintain a constant pressure condition, and then you can somehow heat up the substance and measure its volume change. And then we get this part. It's easy to measure temperature and volume, and then we get delta H over delta P for this substance. And for an ideal gas, delta H over delta P under constant temperature condition is anyway 0, because for an ideal gas, the internal energy and enthalpy only depend on temperature, and we are holding temperature constant here. This is just one line derivation of delta H over delta T under constant pressure condition. H is just U plus PV, so delta H is just delta U over here plus delta PV. Delta PV is P delta V plus V delta P. Delta U is delta Q plus delta W, which is work. And because pressure is constant, so V delta P is just 0. And delta P is just negative P delta V, so these two also cancel. We just have delta Q left on top, so it's just Cp. It's the definition of heat capacity. Again, we can only prove this later in chapter 5 after the introduction of Helmholtz energy and Gibbs energy. So we're going to just use this equation without proving it yet. And we can see dH is Cp dt plus this expression times dP. Again, we do this because this is really easy to measure experimentally. And somehow it's really easy to derive delta V over delta T for an ideal gas. Even for a liquid or solid, somehow this delta V over delta T is related to this thermal expansion coefficient, alpha. It's convenient to express U as a function of temperature and volume. It's convenient to express H as a function of temperature and pressure. Again, it's just because du can be expressed as Cv dt plus this times dV, and dH can be expressed as Cp dt plus this expression times dP. The isochloric heat capacity and isobaric heat capacity can be easily measured. So these two can be measured. So are these two partial derivatives. This one, you can just hold the volume constant and measure the change of temperature and the change of pressure. Over here, you hold pressure constant and then measure the change of temperature and the change of volume. So we get everything then. For an ideal gas, we can even derive this easily. It's just because for an ideal gas, we know delta P over delta T is simply nR over V. So we just replace this with nR over V. We do some derivation, nRT over V, that's just pressure, it's going to be 0. And then we can derive this as well. Delta H over delta P is V minus T times delta V over delta T. For ideal gas, delta V over delta T is simply nR over P. Now we have V minus nRT over P, that's just 0 as well. So really for an ideal gas, we just show that delta U over delta V is 0 if temperature is constant. Delta H over delta P is also 0 if temperature is constant. And remember, in thermodynamics, it's awfully important to have a subscript here, alright, and here. This is just because even for an ideal gas, if you ask me about delta U over delta V, but under constant pressure condition, I'm going to say that derivative is not 0. Delta H over delta P under constant volume condition is also non-zero. So it's awfully important for us to keep track of the subscripts. Again, the internal energy and the enthalpy of an ideal gas depend only on temperature. We will just further prove this for ideal gases. Delta U over delta P is also 0. Delta H over delta V is also 0 if the temperature is held constant. The derivation is very easy because first we have this two. We have delta U over delta V is 0. Delta H over delta P is 0 if the temperature is constant for ideal gas. And then we know this, H is U plus PV. And for ideal gas, PV is an RT. So if you really want to do delta U over delta P, you can just change this U to H minus PV. And you'll do delta H over delta P first, that's just 0. And then you'll do delta PV over delta P, it's also 0. Why is that? I mean, it's just a little confusing. So why is delta PV over delta P 0? Well, it's an ideal gas, right? So PV equals RT, right? PV is equal to RT. And temperature over here, look at the subscript. The temperature is held constant. Therefore, PV is a constant. And that's why this PV does not depend on pressure. Alright, so we get 0. And similarly, delta H over delta V, well, under constant temperature condition, H is U plus PV. And PV is a constant since we're holding temperature constant. So again, we get 0 over here. The internal energy and enthalpy of an ideal gas depend only on temperature. Another way to prove this in words is this. The potential energy of an ideal gas is always 0. Alright? So we don't have to worry about the potential energy. And energy is either potential energy that depends on the positions, or kinetic energy, that depends on the motions of the particles. All right. So if the temperature is constant, then the kinetic energy of the gas is also constant. That means, well, the internal energy is constant. If there's no temperature change, there's no internal energy change. And also H is U plus PV, and PV equals nRT for an ideal gas. There's no change in nRT if temperature is constant. Therefore, in the end, if temperature is a constant, well, there's no change in internal energy. There's no change in enthalpy. Therefore, the internal energy and enthalpy of an ideal gas only depend on temperature. Now, what about real gas? Well, for a real gas, we'll just say approximately delta U over delta V is 0. Approximately delta H over delta P is 0 if the temperature is constant. And we can say the internal energy and the enthalpy of a real gas mostly depends on temperature. Well, they slightly depend on volume or pressure actually, but those dependence is much smaller than the temperature dependence. Alright, there are multiple models that we can use to describe a real gas. The most famous one is the Van der Waals equation or the Van der Waals model. It's this. Let's review this. For ideal gas, P is just RT over molar volume. Why do we minus B? Well, B accounts for the finite size of the gas particles. B also has another meaning, which is the repulsion between the gas particles. A denotes the attraction between the gas particles. So we have two additional parameters. And also we can multiply the top and bottom by n over here, and also for this term we multiply the top and bottom by n squared. So we have this. Now using this Van der Waals equation, we can again evaluate delta U over delta V. It's just T times delta P over delta T minus P. How do we evaluate this? This is just the calculus. What's the first derivative of this term? With respect to temperature, it's just nR over V minus NB. Just plug it in here. What about this term? This term does not depend on temperature at all, so ignore this. And therefore we have this expression. And P is this minus this. Plug in the expression of P here. You can see this term and this term cancel. So delta U over delta V is simply AN squared over V squared for this Van der Waals gas. Alright, so how does the internal energy depend on the volume when the temperature is constant? Well, it's just the attraction term in the Van der Waals equation. Actually, it is a flaw of the Van der Waals model, because supposedly when you change the volume, both attraction and repulsion should change. But over here it seems that we have only attraction in the expression here. Alright, so this is actually a flaw of the Van der Waals equation. But why do we still use Van der Waals equation? Actually, this is the simplest model for the real gas. It's just for convenience. We can have more complex models that can be used to describe real gases more accurately. And we can have a repulsion term over here. How does internal energy depend on volume? Actually, if you change the volume, you change the average distance between the gas particles. Supposedly, we need to have both attraction term and repulsion term here. Alright? Again, the Van der Waals equation is used for convenience because it's the simplest equation that can be used to describe a real gas. The Van der Waals parameter A for most gases are typically small because, you know, it's a gas. There's not much interaction between those gas particles. Alright? It's also possible to evaluate delta H over delta P on a constant temperature condition. It's a bit more difficult than this. There are many steps, but we can still prove this. Delta H over delta P is roughly NB minus 2AN over RT. So over here, it's nice that we have the attraction parameter. We also have the repulsion parameter. It does make more sense. And also, you can see these two may cancel, right? If you have the right temperature. If you just set NP is equal to 2AN RT, somehow you can solve this equation and get a temperature to cancel this two. Alright, so that means, well, delta H over delta P, well, it depends on two things. the repulsion terms and the attraction terms. Sometimes the repulsive term is predominant, and then this is positive. Sometimes the attraction term is predominant, and we have a negative dependence over here. For a liquid or solid, the variation of U with volume and the variation of H with pressure can be calculated given the values of alpha and kappa. Actually, that's why we introduced alpha and kappa in the first place. Again, alpha is the thermal expansion coefficient. Kappa is the compressibility. These two are the definitions of alpha and beta, okay, in the form of equations. Alpha is viewed as the relative volume change over the temperature change. Kappa is negative relative volume change over the pressure change. Using the reciprocal rule and the triple product rule, we can prove alpha over kappa is delta P over delta T on a constant volume condition. How do we do that? This is just purely calculus derivation. Alright, let's do it. Alpha over kappa is just, this is alpha, this is kappa, right? And then in calculus, we have learned this, the reciprocal of delta V over delta P. It's just delta P over delta V. You just flip this two. As long as these two derivatives have the same subscripts, exactly same subscripts, alright? So the temperature is constant here, the temperature is constant here. So this is called the reciprocal rule. And there's also a triple product rule. Alright, if you look at three variables, so you just write it down, V over T, and then P over V, and then T over P. So the product of these three derivatives should be -1. I think you can find the proof of this reciprocal rule and triple product rule on the wiki page of the triple product rule. Alright, you can see the derivation. But right now we'll just use this triple product rule. Alright, so again, if you have three variables and delta x over delta y times y over z times z over x, you know, you have the product of three derivatives. It's just -1. There's a negative sign here, okay? And that's why we have negative delta v over delta t, delta p over delta v is equal to 1 over this. It's just because this times this times this is -1. Pay attention to the subscripts. So right here you see three different subscripts. So if you want to do v over t, make sure p is constant. When you do p over v, t is constant. Delta t over delta p, v is constant. And then finally, we're going to use the reciprocal rule again. So make sure these two subscripts are the same. Then we can flip this. It's going to be delta p over delta t. So over here, alpha over kappa, it's just delta p over delta t on a constant volume condition. Now we have delta p over delta t. It's just alpha over kappa. This derivation is correct for all substances. So for a liquid or solid, we can still use this equation. We just need to look up the values of kappa and alpha for the liquid or solid. We plug those in, and then for given temperature and pressure, plug in those values. We know how U depends on volume for liquid or solid on a constant temperature condition. Alright, what about delta H over delta P? So it's this. We can only prove this after chapter 5. Now we're going to just use this, and if you pay attention to this guy, delta V over delta T, it's simply V times alpha. It's just alpha is defined to be this derivative divided by V. So V times alpha is just this derivative. So we have this equation. Again, if you have the value of alpha for the liquid or solid of interest, it's a constant over a moderate temperature range and pressure range. Plug it in. Plug in the temperature, volume, and then you get how the enthalpy of the liquid or solid depend on pressure. In summary, if we know the values of alpha and kappa, you know, alpha here, somehow we can calculate how U depends on V and how H depends on P for a liquid or solid on a constant temperature condition. Now let's look at one numerical example. We'll calculate the internal energy change of 1 mole copper, a solid, At room temperature, when its pressure changes from 1 bar to 2 bars. Here's the information about copper. We have the density, about 9 grams per milliliter. We have the value of kappa and alpha. For kappa, sometimes we use this reciprocal bar. Sometimes we use reciprocal Pascal. This is the SI unit. Pascal is the SI unit. 1 bar is just 100,000 pascals. Now let's look at this equation. This is how U depends on volume. It's T times alpha over kappa minus P. You should be able to derive this. The derivation, I think, is showing somewhere here. So this is a derivation for, this is derivation for the real gas. This is the derivation for the liquid and solid. Delta P over delta T is simply alpha over kappa. So we have the derivation of alpha over kappa right here. Alright, we just plug in numbers now. We have temperature, room temperature. We have the value of alpha and kappa, and we have the pressure. So I'm going to use bars as the unit for pressure and Kelvin as the unit for temperature. We get delta U over delta V over here. And now we need to know how much the volume changes. The temperature is constant, room temperature. The pressure changes. So I think the volume change should be negative. Alright, so we're going to use this equation for kappa. Kappa is negative 1 over V times delta V over delta P. And it's approximately delta V over delta P. So it's this much. And then we can get the relative volume change. Delta V over V is negative kappa times delta P. Well, it comes from this equation. And we just plug in numbers. We get this number without a unit for the relative change. Alright, this is negative. We can compute the volume of 1 mole copper. It's this much. 1 mole copper weighs 63.5 grams, and we have the density, and then we have the volume of 1 mole copper. Given 1 mole copper, its volume is this. Therefore, the change of the volume is the relative change times V. We get this much in cubic meter. When the temperature is constant, we have this equation. du is delta U over delta V times dV. We'll integrate both sides. Delta U over delta V is this many bars, 20,000 bars, somewhere here. This is huge, but volume change is so tiny that the product is very small. It's negative 0.0112. This is very, very small. Numerical example 3.1.2. Calculate the internal energy change of 1 mole copper under 1 bar pressure when its temperature increases by Kelvin, 1 Kelvin. Alright, so we're given the density of copper. We have alpha and kappa, and we have the isochoric molar heat capacity, etc., etc. Now, first, we have the internal pressure over here. We computed this. It's about 20,000 bars. All right, and we can use this equation to compute the volume change, because we are holding pressure constant, so the volume depends on the temperature only, and this equation comes from the definition of alpha. Alright, alpha is actually delta V over delta T and then divided by volume. So if alpha is roughly a constant for a solid, the alpha times delta T is roughly delta V over V. Alright, and we have the value of alpha, we have the temperature change. We multiply alpha and delta T, we get this relative change. We have the volume of 1 mole copper, 7 milliliters, and then we have delta V, also a very small change. Now, the internal energy is a state function. So That means we can compute delta U in 2 steps. It does not matter how we change the process, as long as the process connects the same initial state and the same final state. All right, because U is a state function. So now we're gonna just look at how internal energy change with temperature here, and over here this is how internal energy changes with small volume. So when you see T here, that means T is held constant. Now we have 2 terms, two terms, 2 integrals. Over here, this is CV. We have the value of CVM. All right, so we're gonna calculate this, and delta U over delta V. We have the value here. All right, now what's CV? CV is CVM times the number of moles. All right, over here, and then times delta T, which is 1 Kelvin. Now let's look at the second integral. Delta U over delta V, it's this many pascals. Alright, I'm just using as a unit here. And times delta V, what's the volume change? Well, it's this much, very small. Now we have 2 terms. This is how internal energy depends on temperature. This is the internal energy change due to the temperature change. This is the internal energy change due to the volume change. Alright, so we have 2 numbers. We can see the internal energy depends much more on temperature than on the volume. Well, but we can also sum it up. We get this 24.44 joule. Alright, and this is the change in internal energy. Alright, for this problem. It's a little complex. Alright, the internal energy change is decomposed into 2 parts. Over here we hold volume constant. Over here we hold the temperature constant. The last numerical example in this section. This time we will calculate the enthalpy change of 1 mole copper. Room temperature will change the pressure. We have the density of copper. We have alpha and beta. So first, delta H over delta P is V minus T times delta V over delta T under constant pressure condition. This equation holds for all substances. Alright, this equation. We cannot prove this until chapter 5. So we'll just use this for all substances. And delta V over delta T is simply alpha times V, based on the definition of alpha. Alright, it's also going from here to here, it's also exact for all substances. It's just for an ideal guess, this alpha is a variable. I think this alpha is actually 1 over temperature. For a solid and a liquid, this alpha is roughly constant. So we're gonna do this. Copper is a solid, so alpha is going to be a constant. We look it up. We have the value of alpha here. We have T alpha, very small. 1 minus T alpha is close to 1. We also have the volume of 1 mole copper. We can do this calculation. Molar mass over density is molar volume. And then we have delta H over delta P. Roughly is 7 milliliters, or this much cubic meter. Now, when temperature is constant, dH is simply delta H over delta P times dP. Alright, over here. We can integrate both sides. We know this part is calculated already over here. And then we just need to integrate this delta H over delta P times dP. And this is a constant, roughly a constant. So over here, the integral of dP is delta P. Delta P is just 2 minus 1, final minus initial. I'm using SI units because when I use SI units, I know 1 cubic meter times 1 Pascal is just 1 joule. Feel free to use liters, ATM, PSI. It's just a little bit more tedious to do unit conversions. So right now I just get 0.7 joule. We know the isobaric molar heat capacity of copper is about 24.4. You can look it up. When temperature increases by 1 Kelvin, the enthalpy of this copper increases this much. Again, when temperature changes by only 1 Kelvin. However, if you change the pressure from 1 bar to 2 bars, well, the enthalpy changes only by 0.7. Compare these two numbers, 24.7. So we're going to say enthalpy depends more on temperature than on pressure for copper. In general, both internal energy and enthalpy depend more on temperature than on pressure for solids and liquids. How about real gases? Well, still, internal energy and enthalpy depend much more on temperature than on the volume or pressure. What about ideal gases? Well, that's the extreme case. Internal energy and enthalpy of an ideal gas only depend on temperature. They do not depend on pressure or volume at all for the ideal gases. Chapter 3: Internal Energy and Enthalpy. Section 3.2: Isochoric heat capacity versus isobaric heat capacity. First, we prove Cp minus Cv is equal to T times delta P over delta T under isochoric condition times delta V over delta T under isobaric condition. So first, based on the definition of enthalpy, we have dH is equal to du plus dPV. dPV is PdV plus VdP. Using H as a function of temperature and pressure, dH is delta H over delta T times dt plus delta H over delta P times dP. Assuming U is a function of temperature and volume, we have du is equal to delta U over delta T times dt plus delta U over delta V times dV. We need to pay attention to this subscripts. Delta H over delta T under constant pressure condition is Cp. Delta H over delta P is V minus T times delta V over delta T. We can prove this after learning Helmholtz energy and Gibbs energy. Delta U over delta T under constant volume condition is Cv. Delta U over delta V under constant temperature condition is T times delta P over delta T minus P. We can prove this after learning Helmholtz energy and Gibbs energy. And then we copy PdV and VdP. Now let's cancel a few terms, and also let's move the dt terms to the left hand side. So we have Cp dt minus Cv dt here and here. And then this VdP cancels this VdP. This negative PdV and PdV cancel. And we can move this term to the right hand side, and also this term stays on the right hand side. Therefore, we have only 4 terms in this equation. Cp dt minus Cv dt is equal to T times delta V over delta T times dP plus T times delta P over delta T times dV. Now we're gonna expand this dV. dV is delta V over delta T times dt plus delta V over delta P times dP. This is based on V being a function of temperature and pressure. So we expand this dV. Once we expand the dV, we have actually more terms. This dV becomes delta V over delta T times dt plus delta V over delta P times dP. So we have more terms in this equation. And then we copy this term here, this term go here, and this term times this term go here. It looks very complicated, but if you look at our goal is this. We try to prove Cp minus Cv is T times delta P over delta T times delta V over delta T. So we can see that pretty much here, T times delta P over delta T, delta V over delta T. And if this is equal to this, we can divide both sides by dt, and we get the we achieve the goal. The only thing we need to do is we need to prove the first term here and the third term here cancel. Actually, they do cancel because we're about to use the triple product rule to show you this is simply the opposite of this. Again, we have this equation. We have Cp minus Cv times dt is equal to the sum of 3 terms. Eventually, we will cancel the first term and the third term. Because of this triple product rule, we have delta P over delta T times delta V over delta P is simply negative delta V over delta T. So you look at this is delta V over delta T, and this is going to be negative delta V over delta T. And therefore, the first and the third terms, they do cancel. Oh, by the way, we need to use both the triple product rule and also the reciprocal rule in calculus to prove this. Now we have this simple equation, both sides divided by dt. We have Cp minus Cv is equal to T times delta P over delta T times delta V over delta T. And pay attention to the subscripts. And again, we'll use triple product rule. Delta P over delta T is negative delta P over delta V times delta V over delta T. And pay attention to the subscripts. If you see PT in the parentheses, V is in the subscript. Same here. When PV are in the parentheses, T is in the subscript. When VT are in the parentheses, P is in the subscript. And now we copy this delta V over delta T here, negative sign goes here, and over here, this one, we're going to use the reciprocal rule. So it becomes delta V over delta P on the bottom. On top, this is simply alpha times V. Now what is alpha? Alpha is the thermal expansion coefficient. So alpha is actually delta V over delta T, and then divided by V. So alpha times V is this. How about this one? This one is actually kappa V, because the definition of kappa is negative delta V over delta P and then divided by V. Therefore, this term is simply kappa V. We have alpha V over kappa V. Therefore, delta P over delta T is equal to alpha over kappa. This equation holds for all substances, but it's often very convenient to use this equation for liquids and solids, because for liquids and solids, alpha and kappa are often a constant within a moderate or even wide temperature range or pressure range. So what we need to do is we just need to plug in the values of alpha and kappa. We know how delta P changes with delta T under isochoric condition for a liquid or a solid. For an ideal gas, alpha is 1 over T, kappa is 1 over P. So kappa over alpha over kappa is just 1 over T divided by 1 over P. It happens to be just P over T. Okay, now let's look at this equation, because delta P over delta T is shown to be alpha over kappa. So this is just alpha over kappa. Delta V over delta T is simply alpha times V. So we analyzed that here. And then Cp minus Cv is equal to Tv alpha squared over kappa. Cpm minus Cvm is Tvm times alpha squared over kappa. This expression is pretty important. Based on this expression, we know Cpm can never be less than Cvm. This is because temperature is always positive. Molar volume is always positive. Alpha squared is always positive, except for one case, water at 4 degrees Celsius. And kappa, the compressibility is always positive. Now we have this equation. Cp minus Cv is T times delta P over delta T times delta V over delta T. Again, delta P over delta T is equal to alpha over kappa. Rigorously, delta V over delta T is alpha times V by definition. So we have T times alpha over kappa times alpha V, and then the result is just Tv alpha squared over kappa. For ideal gas, we can evaluate delta P over delta T. It's actually P over T. Delta V over delta T is V over T for ideal gas. And then the final result is just NR. We have just proven that Cp minus Cv is NR for ideal gas, or Cpm minus Cvm is R. For real gases, Cpm minus Cvm is approximately R. This is approximately true within a really wide temperature and pressure range. So very often we'll just assume Cpm is greater than Cvm by R, even for a real gas. For liquids and solids, Cpm and Cvm can be calculated given the values of isobaric, isothermal expansion coefficient, and also this isothermal compressibility. Alpha is the isobaric thermal expansion coefficient. Kappa is the isothermal compressibility. Given these two values, we'll be able to calculate CPM minus CVM. Well, it's simply over here, T times V times alpha squared over kappa. If we're talking about CPM minus CVM, it's just T times the molar volume times alpha squared over kappa. We need to know what the temperature is and what's the molar volume, and then the values of alpha and kappa. Now let's look at one example problem, 3.2.1. Calculate CPM minus CVM of copper at room temperature. Alpha is this, kappa is this. Now we still have to get the molar volume. The molar volume of copper is this much. I think we computed this before. We just need to use the molar mass divided by density. We get the molar volume. Because mass over density is volume, so molar mass over density is molar volume. We have temperature here, we have molar volume here, we have alpha squared here, we have kappa on the bottom. A Pascal is the SI unit. So after we do this calculation, whatever number we have, it's going to be in the SI unit. We got 0.76, and if you actually have the PowerPoint file and click this, it's going to bring you to a Wolfram Alpha page that shows you the calculations. And then the unit is joule over Kelvin over mole, because joule, Kelvin, mole are SI units or SI derived units. We can look up the isobaric molar heat capacity of copper. It's 24.44 joule per mole per K. And therefore, the isochoric molar heat capacity is this CPM minus 0.76. We have 23.68 joule per Kelvin per mole. It's actually difficult to measure the isochoric molar heat capacity because it's kind of hard to keep its volume constant. It's a little easier to keep the pressure constant, but more difficult to keep the volume constant. CPM minus CVM may range from 0 to 5R for most liquids and solids. CPM is equal to CVM for liquid water at around 4 degrees Celsius. CPM is greater than CVM by 5R for benzene. But in the end, CPM minus CVM cannot be negative. So if you click this, you can see my paper on CP minus CV. Example problem 3.2.2. Calculate CPM minus CVM for water at 0.01 degrees Celsius and 1 bar. We have the alpha value and kappa value here. The molar volume of water is roughly 18 milliliters per mole. Again, it's from the molar mass divided by the density. The molar mass is 18 grams per mole. The density is 1 gram per milliliter. So we get this easily. Now we just plug in numbers. Temperature, molar volume, alpha and kappa, everything included. We get 0.044 joule per mole K. The isobaric molar heat capacity of water at 0.01 degrees Celsius can be looked up easily because it's easy to maintain a constant pressure condition, and then we can measure its heat capacity. It's 75.4. Now we can get CVM. Look at this number and this number. 75.4 minus this is still 75.4 if you keep the correct number of figures. Alright, so CPM minus CVM is negligible at this temperature and also at many other temperatures. So for water, when we talk about heat capacity, well, we don't have to worry too much about the condition. Whether it's isochoric or isobaric, well, it's roughly 75.4 joule per Kelvin per mole. Again, CPM minus CVM of liquids is not always much smaller than that of gases. Two examples. Methanol, well, the difference is 22. For benzene, the difference is 41. The unit is joule per mole K. So both of these numbers are much larger than R. And if we look at the equation here, T times molar volume times alpha squared over kappa. So if we have a large molar volume, so what that means? That means if you have a larger molar mass and small density, and then you have a larger molar volume, and then large alpha, small k, or small kappa, you will get a large difference between CPM and CVM. So just based on this equation, we can see this molar volume of benzene and also methanol, they are also greater than the molar volume of water. And also, if they have larger alpha or small kappa or both, and then they will have a large difference between CPM and CVM. Again, water at 4 degrees Celsius and 1 bar is special. It has a 0 alpha value. Plugging alpha equals 0 here, CPM is equal to CVM exactly under this condition. Chapter 3, Internal Energy and Enthalpy. Section 3.3, the Joule Experiment. Joule designed this experiment to study how the internal energy of a real gas depends on its volume under constant temperature condition. So over here we have the experimental apparatus. There are two compartments separated by a valve. Right now we have a real gas on the left hand side, vacuum on the right hand side. We have thermometers to monitor the temperature and the temperature change. And this system is well insulated. Therefore, we know Q is 0 and dQ is 0. There's no heat exchange between the system and the surroundings. And of course, because it's vacuum, there's no energy transfer between a system and vacuum. A vacuum cannot give energy. A vacuum cannot accept energy either. And now we open this valve. The gas will fill both compartments. The volume changes. And Joule looked at the thermometers. He found that there's no temperature change. And then he did some derivations. First, dQ is 0. There's no heat exchange because the entire system, both containers, are well insulated. And also, there's no work. This system did expand against vacuum, but if you look at the equation for expansion work is negative integral P external dV. This time P external is exactly 0. Expansion against vacuum means work is 0. Well, you cannot do work to a vacuum because a vacuum cannot either give energy or accept energy. Therefore, dW is 0. Since dQ is 0, dW is 0, we have du is equal to 0. And also, we can express du in terms of dt and dV, assuming u is a function of temperature and volume. Therefore, du is delta u over delta t times dt plus delta u over delta v times dV. We also need to pay attention to the subscripts. Over here, we hold volume constant. Here, we hold temperature constant. And again, Joule looked at the thermometers and found no temperature change. Therefore, dt is 0. Also, we have du is 0. Then 0 is equal to 0 plus this. Therefore, this has to be 0. Now we know dV is non-zero because the volume changes. Therefore, dV cannot be 0. The conclusion is delta U over delta V on a constant temperature condition has to be 0 based on this Joule experiment. However, the conclusion is wrong. Joule later used a more accurate thermometer and actually detected a very small temperature change when this real gas expanded against vacuum. So if we look at this equation again, this part later was found to be non-zero. du is still 0, but since this dt term is non-zero, then this part is also non-zero. He later concluded that the internal energy of a real gas did depend on its volume. The dependence is small, almost negligible, but it's there. And there's a reason. There's a theoretical basis for that, because if we change the volume of a gas, for example in this situation, on average the distance between gas particles is longer here than here. When we have a larger volume, we have a longer average distance. And when the distance between gas particles becomes longer, both the attraction and repulsion between gas particles gets smaller. Therefore, the potential energy changes. The internal energy changes when the volume changes. Again, in this experiment, the system is well insulated, so we have dq equals 0. dW is 0 because the system expands against the vacuum. And that means the external pressure is 0. And the work is negative integral p external dv, therefore it's also 0. du is 0. And also u is a function of temperature and volume. So we can express du in terms of dt and dv, two terms. Over here, delta U over delta T under constant volume condition is simply CV. It's just because when volume is constant, delta U is just delta Q. Delta Q over delta T, that's just heat capacity C. So we have C sub V here. And this term, we'll keep it. This is called the internal pressure. When the temperature change is very small, we can make approximations. So delta U is simply the integral of du, and then it becomes the integral of CV dt and the integral of delta U over delta V dV. So we have two terms. Again, when the temperature change is small, we can say, well, the first integral is CV times delta T. Delta T is T final minus T initial. And we're going to assume this delta U over delta V is roughly a constant as long as the volume doesn't change by much. So we copy it here and we have delta V here. Okay, this is an approximation for us to have a semi-quantitative understanding on how U depends on V. Now again, delta U is 0 because Q is 0, work is 0, so this plus this is 0. Now we can compute this delta U over delta V. It's simply negative CV delta T over delta V. So we get this expression. Somehow, if we measure the temperature change, the volume change, and if we know the molar heat capacity of the substance, we can compute this. We can compute delta U over delta V, and it's non-zero for a real gas. By the way, this is 0 for an ideal gas. So if we do the same experiments for an ideal gas, after expansion, there's no temperature change. But if we're doing this experiment on a real gas, the temperature will likely change. Again, in the Joule experiments, somehow we can determine delta U over delta V on a constant temperature condition. It's negative CV times delta T over delta V. For a real gas, delta T is very likely non-zero, so this is non-zero. For ideal gas, well, delta T is predicted to be 0, and then delta U over delta V is 0. It's just because for ideal gas, U only depends on temperature. We're holding temperature constant here, so this has to be 0. Now let's derive the exact expression for this delta U over delta V. We will use the triple product rule again in calculus. In the triple product rule, we need three variables, U, V, and T. So now we have UV, VT, TU, and then pay attention to the three subscripts. The product of these three terms is -1. And therefore, this delta U over delta V under constant temperature condition is -1 divided by these two terms. So right here. And now we're going to use the reciprocal rule. This delta T over delta U on a constant volume condition is the reciprocal of C sub V. isochloric heat capacity. So we put C sub V here, and over here we can flip this as well, as long as we have the same subscript U here. So the reciprocal of this is delta T over delta V under constant internal energy condition. For an ideal gas, delta U over delta V is 0, so this is 0. And therefore we have this is 0 for ideal gas. Well, what does this mean? If we somehow can hold the internal energy of an ideal gas constant, then its temperature is constant. It does make sense. If the internal energy is constant, then its kinetic energy must be constant, and therefore its temperature must be constant. Again, this is the Joule experiment. The exact duration of delta U over delta V results in this expression. It's negative CV times delta T over delta V under constant internal energy condition. For all matters, we can prove this. Delta U over delta V under constant temperature condition is T times delta P over delta T under constant volume condition minus P. We will prove this in chapter 5. For a Van der Waals gas, that means we can use Van der Waals equation. We can evaluate delta P over delta T. It's NR over V minus MB. Alright, we can plug it in and we can simplify this expression. So this is T times delta P over delta T, and this is just P. So we get AN squared over V squared. That means for a Van der Waals gas, its internal energy does depend on volume, and the dependence is positive. It's AN squared over V squared. Actually, it reveals a flaw of the Van der Waals equation. It's just because if you think about the internal energy, there's got to be attraction and repulsion. So over here we see only the attraction term. Now let's still use this expression from the Van der Waals equation. Alright, we just plug this in, AN squared over V squared here. So negative C sub V times delta T over delta V is equal to AN squared over V squared. When the internal energy is held constant, we have simply dt over dV is equal to negative AN squared over CV times V squared. So this equation comes from this equation. We just have both sides divided by C sub V. And over here, we can convert those partial derivatives to the just ordinary derivative over here, because we have this condition here. Just assume we have a system with constant internal energy, and then we have this. Therefore, dt is negative AN squared over CV V squared dV. Looking at this, we can integrate both sides. After we integrate both sides, delta T is just AN squared over CV, and then times the integral of negative 1 over V squared dV. The integral of 1 over V squared dV is just 1 over V, and therefore we have this expression in the end. For a Van der Waals gas, the temperature change depends on the volume change. It's AN squared over CV times the reciprocal of final volume minus the reciprocal of initial volume. What does this mean? Well, a couple things. This term depends on A. So if you have a larger attraction, you'll have larger delta T. Smaller A, smaller delta T. For ideal gas, A is 0 and delta T is 0. That's number 1. Number 2, let's look at expansion. When we have expansion, well, V final is greater than V initial. Therefore, this is actually negative. Delta T is negative. The temperature has to decrease when the volume expands. And by looking at this parameter A, we realize that when the volume increases, the distance between gas particles increases. That means we'll have like smaller attraction. How can we take this change in attraction into account? Somehow we'll have to overcome the attraction with some kind of help. In this case, the system is well insulated. We do not get any external help. So to overcome the attraction, Well, we have to convert part of the kinetic energy to potential energy. And if we have to convert part of the kinetic energy to potential energy, the kinetic energy of the real gas decreases. And temperature is a measure of the average kinetic energy, and then temperature decreases. We have a negative delta T. Again, if we use Van der Waals equation, if V final is greater than V initial, that means we need to overcome attraction. Where does that energy come from? From the decrease of kinetic energy, and therefore the temperature decreases. Let's look at 3 numerical examples. Well, the first one is actually an analytical example. So we'll just prove this for a Van der Waals gas in this Joule experiment. We will just assume the molar isochloric molar heat capacity is constant. U, the internal energy of a real gas, actually depends on pressure, volume, and temperature. But out of these 3 variables, only 2 are independent variables. We will choose volume and temperature for convenience. And then U is a function of temperature and volume. du is delta U over delta T times dt plus delta U over delta V times dV. And then let's evaluate this part. This part is simply delta Q plus delta W over delta T. And because volume is constant over here, it's just C sub V. We can also prove this later in chapter 5. So we have du is equal to CV dt plus something times dV. That something is T times delta P over delta T minus P. For Van der Waals gas, we have this derivation. This part is just AN squared over V squared. Now we have a simple equation for du. It's CV dt plus AN squared over V squared dV. Only 2 terms. This term depends on the temperature change. The second term depends on the volume change. For a Van der Waals gas with a constant U, then du is 0, CV dt is negative AN squared over V squared dV. And we can then integrate both sides. We have the expression for delta T. Delta T is simply this. Or we can just divide the top by n squared. We can divide this by n. We can divide this by n. We can divide this by n. And then we have all those intensive properties. Delta T is A over CVM times, well, the difference between the reciprocals of the final molar volume and the initial molar volume. And by the way, all these are intensive properties, and delta T is an intensive property. Now a numerical example. Example problem 3.3.2. We'll look at a nitrogen gas. Let's estimate the temperature change of 1 mole nitrogen gas when it expands against vacuum from 2 liters to 25 liters. We have the values of the Van der Waals parameters A and B over here. Unfortunately, they are not really in the SI unit. Decimeter cube, this is actually liter, and this is a liter squared. And then we have bar. Bar is not an SI unit either. So, but still, we're going to do the calculations. First, we convert this A from non-SI units to SI units over here. Well, again, this is decimeter to the power of 6. We convert it to 10 to the power of negative 6 meter times meter to the power of 6. And 1 bar is 10 to the power of 5. So therefore, we did this conversion. All right, this 1.3 becomes 0.13. All right, and then we have the molar volume for the gas in cubic meter per mole. It's just because meter is an SI unit. Now we compute delta T using this equation. We're plugging all those values in the SI unit. In the end, we get negative 3 Kelvin. So when this nitrogen gas expands, the molecular distance increases. And we'll have to somehow overcome the attraction, and we need energy to overcome the attraction. Where does this energy come from? Well, we have to borrow from the kinetic energy of the nitrogen. That's why the kinetic energy of the nitrogen decreases. and therefore the temperature of the gas decreases. Again, this is a good example for the transformation of energy. In this example, kinetic energy is transformed into potential energy. And if we look at this equation again, we see only the parameter A. We didn't even see parameter B. For the Van der Waals equation, it's a flaw of the Van der Waals equation. Alright, because when we increase the volume, the distance between gas particles increases. Both attraction and repulsion should be affected. Both attraction and repulsion should decrease, and both should play a role in the temperature change of the real gas. Now another numerical example. This time we just replace nitrogen with HCl. That's the only change. We still have the gas expands against vacuum from 2 liters to 25 liters. We will still use the same equation, but this time we have a larger A. Just by looking at this, if we have a larger A, we'll have a larger delta T. And it's true. When we do the calculation, we see the temperature decrease is now negative 8 Kelvin for HCl. When HCl gas expands, again, the distance between gas particles increases on average. Therefore, the attraction decreases. Somehow we need to overcome the attraction to increase the volume. And where does this energy come from? We need to convert some of the kinetic energy into potential energy, and that will decrease the temperature of HCl. And also, by looking at this equation, delta T is proportional to A. For HCl, we have a larger attraction than the attraction between nitrogen gases, and therefore we have a larger A. When we have a larger A, we have larger delta T. We can see more obvious temperature change, in this case with HCl as our system. Now let's back to the ideal gases. For ideal gases, A is 0, B is 0. There's no attraction, there's no repulsion. So supposedly this delta T is just 0. Alright, so the expansion of an ideal gas, okay, against vacuum will make no change in its temperature. Chapter 3, Internal Energy and Enthalpy. Section 3.4, the Joule-Thomson Experiments. In the previous section, we studied the Joule experiment, in which a real gas expands against vacuum. In this experiment, Q is 0, W is 0. Therefore, delta U is 0. The internal energy of the real gas is held constant. In that experiment, the Joule experiment, we were able to study how the internal energy depends on the volume. Now here's the Joule-Thomson experiment. It's a collaboration between Joule and Thomson. In this experiment, the enthalpy of the real gas is held constant, and we call that isenthalpic condition. This comes from enthalpy isenthalpic. This isenthalpic condition is realized in this simple experimental setup. So we have a pipe, and on the left hand side of the pipe we have a real gas with pressure P1, V1, T1. Between the left hand side and right hand side there is a porous plug, so the gas can pass through this plug. Now we have 2 pistons, one piston here, another piston here. Right now we will just slowly compress this real gas from the left hand side and allow the gas to pass through this porous plug. Alright, so this is the initial state of the system, and this is the final state of the system. We make sure on the left the external pressure is P1, on the right hand side the external pressure is P2. And in this experimental setup we will prove that the enthalpy of the real gas remains constant. So first, let's look at the work done to the system. On the left hand side, work is equal to negative integral P external dV. P external is set to P1, so we have P1 here, and then we have the integral of dV from V1 to 0. We evaluate this because P1 is constant, then W1 is P1 V1. This is a positive because on the left hand side the work is done on the system. Now let's look at the right hand side of the pipe. Well, W2 is also negative integral P external dV. We just make sure this P external is equal to P2, and then we can evaluate this integral. The result is negative P2 V2. Now you may ask, if this P external is equal to P1, how can we compress the gas? Well, how about this? We'll just make sure this P external is greater than P1 by an infinitesimal amount. And over here, same here, this external pressure is smaller than P2 by an infinitesimal amount, and therefore we can assume this is this numerical value is just P2 and this numerical value is just P1 when we evaluate W1 and W2. So overall, work is done on the system on the left hand side, work is done by the system on the right hand side. The total amount of work is P1 V1 minus P2 V2. We need to sum this up. And because delta U is equal to W, I forgot to mention the entire pipe is well insulated. There's no Q, so Q is 0 for the system. There's no heat transfer between this gas and its surroundings, and therefore Q is 0. Again, Joule and Thomson made sure that there's no heat flow between this real gas and its surroundings throughout this entire experiment. So if Q is 0, delta U is equal to W. Therefore, U2 minus U1, that's delta U, is equal to W. W is P1 V1 minus P2 V2. Now we rearrange this equation. We can move this minus U1 to the right hand side, minus P2 V2 on the left hand side. And now we have this U1 plus P1 V1 is equal to U2 plus P2 V2. And remember the definition of H is just U plus PV, and therefore we have H1 is equal to H2. The enthalpy of the initial state is equal to the enthalpy of the final state. The enthalpy of this real gas remains constant after this real gas is pushed through this porous plug. And then we will evaluate this integral, this derivative, delta T over delta P, under this isenthalpic condition, that means constant enthalpy. We will again use the triple product rule in calculus and also the reciprocal rule. The triple product rule gives us this equation. We have H over P, P over T, T over H. The result is negative 1. Do pay attention to the subscripts. When we do delta H over delta P, T has to be the subscript. When we do delta P over delta T, H has to be the subscript. And when we do delta T over delta H, P has to be the subscript. We need 3 variables, 3 terms, and the product is negative 1. And therefore, we can evaluate this delta H over delta P on a constant temperature condition. It's equal to negative 1 divided by this 2 terms. So I'm copying this 2 terms here. And now we keep this negative sign here, and then we flip this to be delta T over delta P. We flip this to be delta H over delta T. And also we need to make sure the subscripts. So over here we have subscript H, subscript H, subscript P, subscript P. So when you use the reciprocal rule, make sure the subscripts are the same. And then this part is simply Cp. Delta H over delta T on a constant pressure condition is simply Cp. There's a reason delta H is equal to Q sub P. And then we have this expression, delta H over delta P on a constant temperature is equal to negative Cp times delta T over delta P under the constant enthalpy condition, or isenthalpic. Over here, this is just one line derivation that shows you delta H over delta T under constant pressure is indeed Cp. It's a little tedious because you need to expand this H to be U plus PV. And delta U is delta Q plus delta W. And delta PV is P delta V plus V delta P. Because pressure is constant, this part is just 0. And because it's isobaric, delta W is simply negative P delta V. And we have negative P delta V here, positive P delta V here, so they cancel. So these two terms cancel. This term is just 0. And then we have only the first term, delta Q. And we have delta Q over delta T, that's heat capacity. So over here we have the isobaric heat capacity. And now we have this expression. Okay, we showed you this expression. Now we're going to define this delta T over delta P under constant enthalpy condition. We name this Joule-Thomson coefficient in honor of both Joule and Thomson because they designed this experiment. Alright, so this is Joule-Thomson experiment under constant enthalpy condition. How does temperature depend on pressure? And we can see this term is equal to negative delta H over delta P over here, this one, divided by Cp. Okay, and there's a negative sign here. Again, this is Joule-Thomson coefficient. Why is this important? Well, if we kind of just produce this Joule-Thomson experiment with this isenthalpic condition, and somehow we can change the temperature of a real gas by changing its pressure. And if this is a positive number, we can drop the pressure of the gas significantly to drop its temperature so much that this gas can be liquefied. The temperature of the gas can be decreased to below its boiling point, and this way we can liquefy a real gas. So that's why it's important. Again, if this is non-zero, and then we can look at the sign whether it's positive or negative. If this is positive, then mu jt is negative. If this is negative, then mu jt is positive. So it's really important for us to realize this Joule-Thomson coefficient, mu sub j hyphen t, and this delta H over delta P under constant temperature condition, they have opposite signs because this isobaric heat capacity is always positive. Now let's look at the analytical expression of this Joule-Thomson coefficient again. Joule-Thomson coefficient is defined to be delta T over delta P under constant enthalpy condition. And by using the triple product rule, this is equal to negative delta H over delta P over Cp. So again, this is important because somehow we can change the pressure of a real gas to change its temperature. If the temperature of a real gas drops significantly, it's possible to liquefy the gas. Now let's evaluate this delta H over delta P. So first, delta H over delta P under constant temperature condition is V minus T times delta V over delta T. And we will be able to prove this after chapter 5. For now, we'll just evaluate this for a van der Waals gas. For van der Waals gas, we use van der Waals equation. P is nRT over V minus MB minus AN squared over V squared. There are two parameters, A and B. They are van der Waals parameters. And A is the measure of the attraction, B is the measure of the size of the real gas particles. And B also represents the repulsion between those gas particles. We will be able to kind of evaluate this for the van der Waals gas. Oh, by the way, if you evaluate this expression for ideal gas, it's going to be just 0 because delta V over delta T is simply V over T for ideal gas. And these two terms cancel for ideal gas. So for ideal gas, H does not depend on P under constant temperature condition. Under constant temperature condition, H is a constant for ideal gas. Therefore, that's why we cannot liquefy an ideal gas, but we can use this to liquefy a van der Waals gas. Now let's look at this. We need to kind of evaluate delta V over delta T. It's pretty hard to do. So we're going to evaluate delta T over delta V first and then take its reciprocal. So first we can express temperature in terms of volume. So this way. Alright. How do we do this? Because we can see temperature only appears here. So we can have both sides plus AN squared over V squared. So we can move this to here. And then both sides multiplied by V minus MB divided by NR, and then we get this expression. So anyway, this is the analytical expression of temperature of a van der Waals gas in terms of pressure and volume. Okay, we went from this equation to this equation, and now we can take its first derivative with respect to volume on a constant pressure condition. That means we'll treat this pressure as a constant, and then we take its first derivative. We copy 1 over nr here, and then, well, we have a product of two terms. So what we do is we use the product rule in calculus. What's the first derivative of this guy? Well, it's this. We copy n squared, and then this is v to the power of -2. Its derivative is -2 times v to the power of -3. So we get the first derivative multiplied by v minus mb, and then we copy this here. We take the first derivative of this part, which is just 1. So we have this expression. And also, because pressure is simply nRT over v minus mb minus n squared over v squared, we replace this pressure with this expression. The only goal is actually to simplify this, because in P we have minus n squared v squared. Over here we have positive n squared over v squared. So if we add this two, we get this. Now we expand this product, we expand this expression, we get 3 terms. 1, 2, 3. We have 3 terms. This is delta t over delta v, and look, we have delta v over delta t here. Eventually we'll have to take the reciprocal of this expression. However, it's really tedious to just take the derivative of this and then plug it in. So we're gonna make approximations. We will make some reasonable approximations so that we get a fairly simple expression for delta H over delta P, and then we can plug it in here. We determine the expression of mu JT, the Joule-Thomson coefficient, and then we understand how can we change the pressure to change the temperature of a real gas. All right, and again we'll make approximations, and then we will eventually prove delta H over delta P on a constant temperature. It's V minus T times delta V over delta T is roughly this. And again, this is delta T over delta V on a constant pressure condition. This is delta V over delta T on a constant pressure condition. So this term and this term are reciprocal to each other. Now for a van der Waals gas, again we have this expression for delta T over delta V, and eventually we'll have to take the reciprocal, so it's complicated. We need to make approximations. What I will do is I will simplify this under 2 conditions. The first condition is this. I'm going to assume A is negligible, or simply A is 0, and then we evaluate this term. And then I'm going to assume B is negligible, and we will evaluate this term. Alright, and then this way we can somehow just simplify the expression of delta H over delta P. We'll see. Now first, let's say A is negligible. So this first term is 0, the second term is 0. Delta T over delta V is simply 1 over nr times this part. Nr and nr cancel, so delta T over delta V is T over V minus mb. It's a lot simpler. And then delta H over delta P, we will evaluate this based on the assumption is negligible. So we have this is equal to V minus T times the reciprocal of this. Alright, so the reciprocal of this is simply V minus MB over T. We plug it in, alright, and then we get MB. This is simple. If A is negligible, H depends on P. The dependence is just MB. That's actually the space taken up by those real gas atoms or molecules. So it does have a physical meaning. What if B is negligible? Let's look at this. If B is negligible, we keep this. B is negligible, so this part disappears. If B is negligible, this part becomes nRT over V. So we still have 2 terms, but they look a lot simpler than this. Alright, so we have this copied here, and over here we have this nRT over V. Because B is 0, we get this expression. Now we will evaluate delta H over delta P. It's just V minus T times delta V over delta T, and this is just the reciprocal of this. So I'm gonna put the reciprocal of this here. It's 1 over this and then times nRT. The T comes from here, NR comes from here. Alright, we need to take the reciprocal of 1 over NR, therefore it's just NR. So this does look very complicated. We will simplify this a little bit. Alright, so first we're gonna use this V as the common factor, and then we have 1 minus this guy, and on the bottom, okay, we need to multiply this by V, we need to multiply this by V, so we have these two terms. Alright, and we can further rewrite this by dividing the top and bottom by nRT. The top divided by nRT is 1, the bottom divided by nRT is 1 minus this, so we get this expression. And then we further evaluate this subtraction. 1 minus this is simply this guy. Alright, this is negative because this is 1 and this is smaller than 1. Okay, this is smaller than 1, this is 1. I'm sorry, this is greater than 1 because the denominator is smaller than 1, so this whole fraction is greater than 1. 1 minus a number greater than 1, we get a negative result. So this is negative. So from here to here, it's just algebra and it's negative. And now we're gonna make some approximation again. So if you look at the bottom, it's 1 minus 2an over VRT. If a is small enough, actually for real gases, usually a is small enough so that 2an is much smaller than VRT, and therefore this fraction is much smaller than 1. For example, this can be 0.01, and then we're gonna make approximation. 1 minus 0.01 is roughly 1. Alright, only because this 2an is usually much smaller than VRT. Alright, for that reason. And then we can say this is roughly 1. We can have this expression. V and V cancel. We have negative 2an RT. Very important. If B is negligible, only A plays a role. So H depends on P. The dependence is proportional to A, and it's negative. Now let's look at here. When A is negligible, H depends on P. The dependence is MB. When B is negligible, H depends on P as well, but this time the dependence is negative 2an over RT. This is proportional to B, this is proportional to A. This is a measure of repulsion, this is a measure of attraction. Repulsion is positive, attraction is negative. And now we made two different approximations. When A is negligible and then when B is negligible, what if neither is negligible? We're going to assume delta H over delta P is then this plus this. Okay, the repulsion factor plus the attraction factor. Alright, so it's going to be MB minus 2an over RT. Again, when A is negligible, delta H over delta P is MB. When B is negligible, delta H over delta P is roughly negative 2an over RT. When both A and B play a role, we're going to assume this delta H over delta P is the sum of MB and negative 2an over RT. Now we have this Joule-Thomson coefficient. Mu sub J hyphen T is delta T over delta P. It's negative delta H over delta P over Cp. This equation comes from the triple product rule in calculus. And then the expression for delta H over delta P in terms of A and B is this. Now both the top and bottom divided by n, the number of moles, we get this. It's going to be just 2ART minus B on top, CPM on the bottom. So now we can say this. Mu JT can be positive, 0, or negative. If 2A over RT is greater than B, mu JT is positive. If 2A over RT is equal to B, well, mu JT is 0. If 2A over RT minus B is negative, then mu JT is negative. Alright? So it's more common for mu JT to be positive. So we'll study this case. Mu JT can be negative if the attraction is really small, the repulsion is really large. This is less common. But anyway, if mu JT is positive, then somehow we can lower the pressure of a real gas to lower its temperature. Here is one numerical example. Alright, we will examine the nitrogen gas given its van der Waals parameters A and B. We also have CPM of nitrogen, roughly 3.5 R. Now we're going to use this expression mu JT is delta T over delta P, and over here this is from the triple product rule, and then delta H over delta P under constant temperature condition is 2AN over RT minus MB, and then we simplify this by dividing the numerator and denominator by N, and then we can plug in all the numbers. 2A over RT minus B over CPM, which is 3.5 R. We plug in all the numbers. I think I have been using the SI units, so in the end this number is in the SI units, 2.47 times 10 to the power of negative 6 Kelvin per Pascal. Both Kelvin and Pascal are SI units. We can convert it to 0.247 K per bar. Bar is not a SI unit, but using bar is sometimes more convenient than using Pascals. Alright, so what does that mean? That means, well, if you increase the pressure of nitrogen under the isenthalpic condition, its temperature is going to go up by 0.247 Kelvin. What if you decrease the pressure of the nitrogen gas? The temperature will decrease. What if you start with, for example, 100 bar nitrogen at room temperature, and you change its pressure from 100 bar to 1 bar? Then the pressure drop is going to be 99 bars, and 99 bars times this, well, approximately you can decrease the temperature of this nitrogen gas by 25 Kelvin, and actually that's fairly significant. If you can drop the temperature by 25 Kelvin, it's almost like from the room temperature to 0 degrees Celsius. I mean, you can feel it, right? And what if you can drop the pressure of nitrogen from 500 bars to 1 bar, and you will see more significant temperature decrease. Alright, again, we get this number in SI unit, this number in non-SI unit. Both values are positive. Well, that means when pressure goes up, temperature goes up. When pressure goes down, temperature goes down. Alright, and this is positive because this attraction term is greater than the repulsion term. Numerical example 3.4.2. This time we'll look at a hydrogen gas with its A value, B value, and CPM. And similarly, we do this kind of calculations. We're plugging all the numbers in SI unit. This time we get a negative number. It's a negative 2 times 10 to the power negative 7 Kelvin per Pascal, or negative 0.02 Kelvin per bar. So actually this is negative. I just want to remind you, actually this mu GT coefficient can be negative. Why? Because sometimes the attraction term is smaller than the repulsion term, and then in that case this mu GT can be negative. It's a very small negative number. That means, well, if you drop the pressure of a hydrogen gas from 100 bars to 1 bar, although the pressure decrease is very large, 100 bars, its temperature change is fairly small. It's only 2 Kelvin based on this number. Alright, it's only 2 Kelvin based on this number. So why does this temperature change when pressure changes? So we can do a qualitative analysis. When pressure changes in this Joule-Thomson experiment, the volume changes actually. So when pressure drops significantly, the volume increases and the distance between the gas particles increases. That means you have to overcome the attraction. So if the attraction is large enough, you need to convert a great deal of kinetic energy to attraction. Well, and then in that case, part of the kinetic energy is transformed into potential energy. You have lower kinetic energy and therefore lower temperature. The temperature decreases. But in this case, in the hydrogen case, actual repulsion is like more significant than attraction. So in this case, when you drop the pressure significantly, you increase volume, and then that plays a role in the change of both attraction and repulsion. All right, and but because the repulsion is predominant, actually you're going to have a smaller repulsion. When you have a smaller repulsion, well, the potential energy decreases, but energy cannot be created or destroyed. So where does this potential energy go? It goes into kinetic energy. So the kinetic energy increases, the temperature increases in this case, but not by much, okay, by only a little bit. Usually, okay, mu jt is positive. Okay, it's rare to have a negative mu jt. I'm just trying to show you a rare example over here. Now let's use this Joule-Thomson phenomena to cool nitrogen gas to a temperature below its boiling point so that we can liquefy nitrogen. Actually, this is how the industry make nitrogen liquid. For the nitrogen gas, the Joule-Thomson coefficient is roughly 0.247 Kelvin bars. Then it gives us an idea. What if we have a nitrogen gas with a huge pressure at room temperature, and then we drop its pressure to only 1? That way we can significantly drop its temperature, to below the boiling point, and then we have liquid nitrogen. But it can be a little bit more complicated than that in the industry. All right, so let's look at a few steps on how we liquefy nitrogen. First, let's say we have just nitrogen, 1 bar pressure, room temperature. That's cheap because you can get it from air. All right, but this time we're gonna compress this nitrogen at room temperature from 1 bar to 200 bars. This is gonna increase the temperature of nitrogen. Okay, because of this, you can see when pressure goes up, temperature goes up. All right, so we have a really hot and a high pressure nitrogen gas. This time we can use ice cold water, which is cheap, to lower the temperature of nitrogen back to a lower temperature. For example, over here it's just 0 degrees Celsius. That's not a problem, and this is cheap, just ice cold water. And then if we have some really cold nitrogen gas, we can further lower the temperature of this high pressure nitrogen gas to 120 K. So now you have a real gas, nitrogen gas, very high pressure, 200 bar, and low temperature, 120 Kelvin. And now what do? We will do this Joule-Thomson experiment. We will allow the pressure of this gas to drop from 200 bars to 1 bar. And therefore, the temperature of this nitrogen gas will drop correspondingly by this much. So it's just basically this ratio, 0.247 times the pressure change. It's going to be roughly 50 K. All right, remember over here we had 120 K, and then we drop another 50 K. It's going to be 70 K. 70 K is below the boiling point of nitrogen, and therefore the nitrogen is liquefied. It has now a 1 bar pressure and a 70 Kelvin. All right. By the way, how do we get this 120 Kelvin nitrogen gas, really cold nitrogen gas? It's just because after we make this liquid nitrogen, well, inevitably we will have some evaporation of this liquid nitrogen. It's going to produce a very cold nitrogen gas, which can be roughly this temperature, 120 Kelvin, or even lower than that. So we can use this very cold nitrogen gas to cool the 200 bar nitrogen at 0 degrees Celsius to like 0 degrees from 0 degrees Celsius to roughly 120 Kelvin. This is pretty cold. This is negative 150 degrees Celsius. So we have a diagram to show you all those steps. First, we have nitrogen, room temperature 1 bar. That's boring. We compress it to actually after we compress it, we allow it to cool down to room temperature and 200 bars, and then we use ice cold water to further cool it to 0 degrees Celsius, 200 bars, and we use very cold nitrogen gas to further cool it to 120 K It's very, very cold and 200 bars. The final step is the Joule-Thomson experiment. It's so-called isenthalpic expansion of a real gas. When the pressure drops, its temperature drops, and the temperature change divided by the pressure change for nitrogen is 0.247 Kelvin per bar. So going from here to here, we can make the temperature of this nitrogen gas below its boiling point, and then we have liquid nitrogen. Chapter 3, Internal Energy and Enthalpy. Section 3.5, Internal Energy of Reaction and Hess's Law. The internal energy of reaction is the internal energy of the products minus the internal energy of reactants. The products are the final state of the chemical system. The reactants are the initial state of the chemical system. For example, if we look at this reaction with N2O4 as the reactant, NO2 as the product, then the internal energy of reaction is equal to 2 moles of NO2 minus the internal energy of 1 mole N2O4. However, this example is problematic because if you look at these coefficients 1 and 2, they are not really the number of moles. They only reflect the ratio between the number of moles, not the actual number of moles. Therefore, we say the internal energy of reaction of this N2O4 to 2NO2 should be defined as, again, the internal energy of 2 moles of NO2 minus the internal energy of 1 mole N2O4. But then we need to add these 3 words, per mole reaction. And now this definition is more rigorous. The SI unit of the internal energy of reaction thus is joule per mole. Again, over here you see per mole reaction. So the SI unit is joule per mole. However, if we use joule per mole for typical chemical reactions, the corresponding numerical value will be very large, usually in the order of thousands, tens of thousands, or even hundreds of thousands. Therefore, the more commonly used unit is kilojoule per mole, just for convenience. And then we have usually several kilojoule per mole, tens of kilojoule per mole, or at most, several hundred or thousand kilojoule per mole. And similarly, the enthalpy of reaction is simply the enthalpy of the products minus the enthalpy of the reactants per mole reaction. Now let's look at this as example. You can say, well, the enthalpy of reaction is the enthalpy of 1 mole water minus the enthalpy of 1 mole H2, and then minus the enthalpy of half a mole of O2, and then per mole reaction. Again, the SI unit of the enthalpy of reaction is simply joule per mole, but we often use kilojoule per mole for convenience. Now let's look at the standard enthalpy of reaction for this H2 plus 1/2 O2 to become water at room temperature. It's negative 285,800 joule per mole. So this is not very convenient. That's why we usually say negative 285.8 kilojoule per mole. Now what if we double the coefficients? When we double the coefficients, we double this numerical value to negative 571.6 kilojoule per mole. What if we flip the direction of the reaction? So over here we have water on the right hand side. What if we write water on the left hand side, H2 and O2 on the right hand side? Then we need to change the sign for the enthalpy of reaction. Now it's positive 571.6. This is dictated by the Hess's law. Now let's look at the internal energy change of reaction. It's actually equal to the heat flow of the reaction at constant temperature and volume condition. And now if we look at the enthalpy reaction, it's equal to the heat flow of the reaction at constant temperature and pressure condition. So now let's review the expression of du. du is delta u over delta t times dt plus delta u over delta v times dv. And we have this equation only if there's no chemical reactions. And at constant temperature and volume, if there's no chemical reaction, dt is 0, dv is 0, and therefore du is 0. But what if there's a chemical change? Then du is non-zero, even if t and v are constant. This is because at the beginning we have reactants, at the end we have products. They are different. Therefore, there is some internal energy change, even if temperature and volume are constant. And if we integrate this du, we get delta U reaction. This is equal to Q reaction plus W reaction. If the volume of the system is constant, there's no expansion, there's no compression, this part is 0, and therefore we have delta U of the reaction is equal to Q reaction. Similarly, we can write dH in terms of dt and dP, assuming H is a function of T and P. So if we just look at this equation, if temperature is constant, pressure is constant, then H is a constant. If there's no chemical reaction, but what if there is chemical change? The initial state is the reactants, the final state is the products. Therefore, dH is non-zero, even if temperature and pressure are held constant. And again, we can integrate this dH. This is delta H reaction. It can be expanded as U plus PV. That's just the definition of H. H is defined to be U plus PV. And then we have this equation. This is because delta U is Q plus W. This is Q and this is W. W is negative P delta V under constant Bragg condition. And what about this delta PV? Delta PV is actually P delta V, only because this is isobaric, P is constant. Therefore, delta PV is equal to P delta V. And this to cancel, we just showed this delta H of the reaction is Q of reaction. And over here, just a reminder, when we have this in kilojoule per mole, this has to be kilojoule per mole. This is Q reaction per mole reaction. Exothermic reactions releases heat. Q reaction is less than 0. Endothermic reactions absorb heat, and Q reaction is greater than 0. And in the end, is Q reaction equal to delta U of the reaction or delta H of the reaction? We don't know. It depends on the experimental condition. If the chemical reaction proceeds at constant temperature and volume, then Q reaction is delta U of the reaction. If the reaction proceeds under constant temperature and pressure condition, then Q of the reaction is delta H of the reaction. In general chemistry, Hess's law is used to calculate the enthalpy change of a reaction that can be expressed as a linear combination of multiple reactions. Hess's law is exact because enthalpy is a state function. The enthalpy difference between a set of products and a set of reactants is the same regardless of the process in which the reactants is converted to the products. For the same reason, Hess's law can be used to calculate the change of any other state functions. It does not have to be enthalpy, because internal energy is a state function, G and A are state functions, entropy is a state function, temperature, pressure, volume are state functions. Actually, Hess's law can be used for all these other state functions. For example, the internal energy of reaction of A to 2C can be calculated given the internal energy of reaction of this from A to 2B and then from C to B. Okay, we're going to treat those reactions as if they were numbers, and then we can do addition, we can do subtraction, we can multiply those reactions by numbers. Alright, so for example, from A to 2B, if the internal energy of reaction is 20 kilojoule per mole, we'll put it here. And from C to B, it's 30. Therefore, from B to C, if we reverse this reaction, it should be negative 30. That's why you see a negative sign here. From B to C, it's negative 30. What if it's 2B to 2C? It's negative 2 times 30. Therefore, we have these two reactions. And then if we sum up these two reactions as if they were numbers, we can get the sum. What's the sum? The sum is we just combine the left hand side, which is A plus 2B. We combine the right hand side, it's 2B plus 2C. Note this 2B appears on the left hand side and also on the right hand side. they cancel. Therefore, the sum of these two reactions is from A to 2C, and correspondingly, the internal energy of reaction is this 20 minus 2 times 30, which is negative 40. Again, I really want to emphasize this. Hess's law is not about just enthalpy. You can apply Hess's law to any state functions, PV, TS, UH, because the change of a state function depends only on the initial state and final state. How the system reaches from the initial state to the final state is irrelevant if we just want to compute the change of a state function. Chapter 3, Internal Energy and Enthalpy, Section 3.6, Enthalpy of Reaction and Enthalpy of Formation. Hess's law states that regardless of the steps in a reaction mechanism, the total enthalpy change for the reaction is going to be the sum of all changes involved in all steps. This is only because enthalpy is a state function. Therefore, the enthalpy change of a chemical system is going to be the enthalpy of the products minus the enthalpy of the reactants, regardless of the steps involved in this reaction mechanism. For example, we can determine the enthalpy of reaction for this reaction from A to 3D plus E given the information about 3 individual reaction steps. Over here we have the reaction from A to 2B plus C, from D to B, from D plus E to C. So now let's look at these 3 reaction steps. We see A appears only in the first reaction step. Therefore, we need this reaction step, so we put it here. And also, in this target chemical reaction, we do not see any B or C. So somehow we need to cancel this 2B. Therefore, we use this reaction from D to B. We change its direction. It becomes from B to D, and then we multiply that by 2, and that's why we multiply 30 by negative 2 here. And also we need to cancel this C. Therefore, we need to reverse the third reaction step so that C appears on the left hand side, and we need to change the sign correspondingly from negative 10 to positive 10 here. Now if we add up the left hand side, it's A plus 2B plus C on the left hand side. We add up the right hand side, 2B plus C plus 2D plus D plus E, and now the total enthalpy of reaction is going to be 20 minus 60 plus 10. The result is negative 30 kilojoule per mole. And if we look at this chemical equation, we have 2B on the left and the right. We have C on the left and right. We can combine this two. Therefore, we get A to 3D plus E. The enthalpy of reaction is negative 30 kilojoule per mole. Now let's look at another example, problem 3.6.1. Calculate the enthalpy of reaction. This is from A plus 2E to 3C using the data provided in the previous example over here. So we have this from A to 3D plus E. We copy this here, and then somehow we need to get rid of the D's, and we need to introduce C's into this equation. So we have this 3D plus 3E equals 3C. That's negative 30. That's from this reaction step multiplied by 3. And then we combine this two. On the left we have A plus 3D plus 3E. On the right we have 3D plus E plus 3C. The left and right cancel. Well, the 3D on the left and the 3D on the right cancel. And over here partially cancel. And then we have this final equation, A plus 2E, we get 3C. And the enthalpy of reaction is simply negative 30 minus 30, it's negative 60. Because enthalpy is a relative quantity, the value of H, the enthalpy, can be determined only after some zero references are defined. The UPAC decided that pure elements in the most stable state of aggregation, it could be solid, liquid, or gas, under the standard pressure, which is 1 bar, they have a zero enthalpy of formation. It's written this way: standard enthalpy of formation is 0 at 298.15 Kelvin. that's the room temperature. Over here, this delta actually denotes change. So what kind of change? Well, it's changing from the pure elements to compounds, and we need this data. What if the change is from pure elements to pure elements? Well, that's just zero. That's why, the enthalpy of formation of pure elements in their most stable state of aggregation under the standard pressure at room temperature is simply zero. Note that the room temperature is used in the definition of the enthalpy of formation, not the standard temperature. The standard temperature is actually 0 degrees Celsius. The room temperature is 25 degrees Celsius. The UPAC has chosen this room temperature in the definition of the standard enthalpy of formation. Again, the standard enthalpy of formation of a compound is the enthalpy change of the formation reaction in which the product is the compound and the reactants are the pure elements in their most stable state of aggregation, each in their standard state at room temperature. For example, the standard enthalpy of formation of propane, carbon 3, hydrogen 8 is the enthalpy of the reaction of this. From 3 carbon and 4 H2 we get propane, because on the left hand side graphite is an element and this hydrogen gas is an element. Okay, and remember, when we define the standard enthalpy of formation to be 0 for pure elements, the temperature has to be room temperature. So we have 298.15 Kelvin for the temperature. And also, graphite, not diamond, is the most stable state of aggregation of carbon under 1 bar pressure at room temperature. Under this condition, graphite is slightly more stable than diamond. And in the above standard reaction of formation of propane over here, H2 and propane are both gases. They're in the gas phase, and to make sure they are under the standard condition, they have to have a standard 1 bar pressure. How about graphite? It's a solid. So for a solid in a standard state, that solid has to be under 1 bar external pressure. Same for the liquid. If we say a liquid is in the standard state, that means that liquid is under 1 bar pressure. The standard state of reaction is almost always hypothetical. This is just because for all 3 chemicals in a reaction to be in a standard state, you have to have a 1 bar propane, 1 bar H2, and also at the same time the graphite is under 1 bar external pressure. It's almost never achieved. Now if you look at this notation, delta U superscript naught is delta U with all involved chemicals in their standard state. This superscript 0 or superscript naught means standard state. Same here, in delta H superscript naught, it means delta H when all involved chemicals are in their standard state. Again, this superscript naught in delta U naught and delta H naught denotes the standard state, and this indicates every single chemical involved in the chemical reaction is in the standard state. The standard state is also defined by UPAC. If you click this web link, you can get to the definition of the standard state. The standard state is the state of a system chosen to be the standard for reference by convention, and the following standard states are recognized. For a gas phase, it's the hypothetical state of the pure substance in the gaseous phase with P is equal to 1 bar, and assuming this gas behaves ideally. So that's why it's hypothetical. None of the real gases is really ideal. For a pure phase or a mixture or solvent in a liquid or in a solid, it's the state of the pure substance in the liquid or solid phase at the standard pressure. P is equal to P naught. So if you have pure gold under the standard state, it has to fill 1 bar external pressure. And if you have pure mercury in the standard state, that means the mercury is under 1 bar external pressure. For the solute in a solution, the standard state is also the hypothetical state of solute at this concentration. Well, you can say 1 mole per kilogram solvent or 1 mole per liter solution. So which one is correct? Well, it really depends on the situation, how the properties of this chemical in the standard state is tabulated. But they should be under the standard pressure, which is 1 bar pressure. And also over here, very important, this is hypothetical because the solute has to exhibit infinitely dilute solution behavior. So that's why it's hypothetical. For the solvent in a solution, its standard state is when the mole fraction of this solvent is 1. Actually, that means pure solvent, so it's also a hypothetical state. For alloy, the standard state of each metal is when its mole fraction is 1. That means pure metal. So we can never reach the standard state if you have an alloy. But you can imagine there are 2 different metals forming this alloy, and if one of the metals has a mole fraction of 0.9999, and approximately this metal is in the standard state if it's under 1 bar pressure. The standard state is defined so that 0 references are available for relative quantities such as enthalpy and some other thermodynamic properties. Now we have a bunch of equations for the internal energy of reaction and enthalpy of reaction. For example, the internal energy of reaction is simply the internal energy of products minus the internal energy of the reactants. And specifically, if all chemicals are in the standard state, we can put a superscript naught for this internal energy of reaction and also for the internal energy of products and that of the reactants. Same for enthalpy. If you look at this, it simply tells you the enthalpy of reaction is equal to the enthalpy of products minus the enthalpy of reactants. And again, we can specifically put a superscript naught here for all 3 terms. So this means the standard enthalpy of reaction is the enthalpy of products in the standard state minus the enthalpy of reactants in the standard state. Again, there's no way to determine the absolute value of enthalpy for any chemical because enthalpy is a relative quantity, and therefore we often define 0 references. The enthalpy of formation of pure elements in their most stable state, if the pure element is also in the standard state at room temperature, and we say they have a 0 enthalpy of formation. So pure elements are simply chosen to be the 0 references. And then it's easy to compute the enthalpy of reaction. So over here we have the standard enthalpy of reaction. It's simply the standard enthalpy of formation of the products minus the standard enthalpy of formation of the reactants. It's easy to determine experimentally the change of H or U of the reaction because we can simply measure the reaction heat. Delta H of a reaction is equal to the reaction heat at constant temperature and pressure condition. The internal energy of reaction is equal to the reaction heat at constant temperature and volume condition. So we'll have to pay attention to the experimental conditions. Constant Tp, Q is delta H. Constant Tv, Q is delta U. For safety and lower cost, most chemical reactions are conducted under the isobaric condition. That's why we often deal with the enthalpy of reaction instead of the internal energy of the reaction. Chapter 3, Internal Energy and Enthalpy, Section 3.7, Temperature Dependence of the Enthalpy of Reaction. Given the enthalpy of reaction at temperature 1, we can calculate the enthalpy of reaction at temperature 2 using Hess's law, as long as the pressures are held constant. Let's look at one very simple example from A to B. Now, the reaction from A to B at temperature 2 can be decomposed into 3 steps. Step 1, from A at T2 to A at T1. Step 2, from A at T1 to B at T1. Step number 3, from B at T1 to B at T2. Steps 1 and 3 are physical changes. We're simply changing the temperature of A and B. Step 2 is a chemical reaction from A to B, and this reaction proceeds at temperature T1. So because enthalpy is a state function, therefore the enthalpy of the reaction at T2 is simply the sum of the enthalpy change of step 1 plus step 2 plus step 3. If you look at the 3 consecutive steps, the initial state is A at T2, the final state is B at T2. Therefore, if you sum up all the changes, well, it's simply the enthalpy of B at T2 minus the enthalpy of A at T2. That is indeed the enthalpy of reaction at T2. Now let's look at the molar enthalpy change of the 3 steps. So molar enthalpy change, that means the molar enthalpy change of A in the first step, and over here this is the enthalpy change per mole reaction in step 2. In step 3, that's the molar enthalpy change of B. Now let's look at 1. It's from A at T2 to A at T1. The initial temperature is T2. So over here we have lower limit T2, upper limit T1, and we integrate CPM of A. Why molar CP? It's because we are interested in the molar enthalpy change. Now look at step 2. It's a chemical reaction. Assuming we know the enthalpy of reaction at T1. So that's the molar enthalpy change of step 2. Number 3, we have this chemical B from T1 to T2. Therefore, we integrate the CPM of B from T1 to T2. And then we can sum up these 3 terms to get the enthalpy of reaction at T2. Again, over here, we have the sum of the molar enthalpy changes of the 3 steps. Step 1, we change the temperature of A. Step 2, from A to B. Step 3, we change the temperature of B. The first and the third terms can be combined because this is integral, this is integral, and we are integrating over here from T2 to T1. This is from T1 to T2. We can simply change the sign of the integral and at the same time switch the lower and upper limit, and then we get this enthalpy of reaction at T2 is equal to the enthalpy of reaction at T1, and then plus this integral. This is molar heat capacity of B minus molar heat capacity of A. Why negative sign? This is because we switched the lower and upper limits, and therefore we have a final expression over here. It's the sum of only 2 terms. This is the enthalpy of reaction at T1, and over here this is the integral from T1 to T2, and over here this is not just CPM of B or A, it's the difference between B and A. This is a change of the CPM, and the change of CPM is simply the CPM of the product minus the CPM of the reactant. Delta CPM again is the change of the isobaric heat capacity per mole reaction. Now we look at a slightly more complicated chemical reaction. Now we have 4 chemicals involved in this single chemical reaction, and we have coefficients 1, 2, 1, and 3. Now we're going to use Hess's law again to calculate the enthalpy of reaction at T2 given its enthalpy of reaction at T1. Still, we will decompose this reaction at T2 into 3 steps. In the first step, we will change the temperature of the reactants from T2 to T1. Step number 2, we allow this reaction to proceed at T1. Number 3, we will have the product's temperature changing from T1 to T2. Now let's look at the initial state of these 3 consecutive steps. The initial state is the reactants at T2. The final state is the products at T2. Therefore, overall, the sum of the changes is equal to, again, the products at T2 minus the reactants at T2. That is indeed the enthalpy of reaction at T2. Now we're going to express the molar enthalpy change of the three steps and then sum them up. Step 1, it's from T2 to T1. And over here, because we have 1A and 2C, we have the molar heat capacity of A and 2 times the molar heat capacity of C. Step number 2, it's simply the enthalpy of reaction at T1. Step number 3, we will change the temperature of the products from T1 to T2. Since we have 1B and 3Ds, that's why we have the molar heat capacity of B and 3 times the molar heat capacity of D. And therefore, the enthalpy of reaction at T2 is simply equal to the enthalpy of reaction at T1 plus the temperature dependence. And over here, this large integral is from T1 to T2. We have positive molar heat capacity of the products, but negative sign in front of the reactants. Only because over here, if you look at this integral, it's from T2 to T1. But if you look at this integral, this is from T1 to T2. Therefore, we need to change the sign. In general, the enthalpy of reaction at T2 is equal to the enthalpy of reaction at T1 plus the integral of delta Cp m dt. And the integral is from T1 to T2. Delta Cpm is the change of the molar isobaric heat capacity. It's the isobaric molar heat capacity of all products minus the isobaric molar heat capacity of all reactants. And when we calculate this delta Cpm, we have to take the coefficients into account. For example, there's a 3 in front of D in the chemical reaction, and there's a coefficient 2 in front of C in the reaction. That's why. Now let's look at one numerical example. Let's say the standard enthalpy of reaction for this from A plus 2C to B plus 3D is negative 200 kilojoule per mole at room temperature. Our goal is to compute the standard enthalpy of reaction for this same reaction at a different temperature, 318 Kelvin. Now we have to know the values of those isobaric molar heat capacity of all chemicals. And then we have some numbers, 40, 30, 70, and 60 for chemicals A, B, C, and D. Alright, now let's look at this equation. The enthalpy of reaction at T2 is equal to the enthalpy of reaction at T1. You may view this as a baseline and the integral as the correction between the temperature 1 and temperature 2. So now let's plug in all the numbers. The enthalpy of reaction at 318 K is the enthalpy of reactions at 298 K plus the integral from 298 K to 318 K. And then the integral is the integral of delta Cpm, the products minus the reactants. And we can compute delta Cpm easily. We have 1B and then 3D. We have 1A and 2C. We take the difference, we get 30 joule per mole Kelvin. And then we can evaluate this integral and then do this addition. The enthalpy of reaction at 318 K is simply negative 200 kilojoule per mole. This is the room temperature data plus the correction. When you look at the correction, we integrate the constant. Therefore, it's really easy. It's just 30 joule per mole K times the temperature change, which is 20 Kelvin. And then we get 600 joule per mole. Pay attention to the units. Over here, we have kilojoule per mole. Here, we have joule per mole. Therefore, we need to convert this joule per mole to kilojoule per mole. The result is negative 199.4. The standard enthalpy of this reaction changes from negative 200 to negative 199.4 kilojoule per mole as the temperature changes from 25 degrees Celsius, which is this temperature, to 45 degrees Celsius, which is this temperature. Actually, for most chemical reactions, this integral of delta Cpm is much smaller than the enthalpy of reaction. So that means this temperature dependence of the enthalpy of reaction is usually small. and it is usually neglected unless the temperature difference is significant. For example, more than 100 Kelvin or more than 100 degrees Celsius, and then this integral can be significant and must be included over here. What if the temperature change is only several Kelvin or 20 Kelvin? Well, we can assume the enthalpy of reaction is approximately a constant within such a small temperature range or even a moderate temperature range. Chapter 3, Internal Energy and Enthalpy. Section 3.8, Pressure Dependence of Enthalpy of Reaction. In the previous video, we studied the temperature dependence of enthalpy of reaction. The temperature dependence of enthalpy of reaction is usually small because the integral of delta CPM is usually much smaller than the magnitude of the enthalpy of reaction. Therefore, the enthalpy of reaction is approximately a constant within a small temperature range, or even within a moderate temperature range, up to tens of degrees Celsius. Now, what about the pressure dependence? It's even much smaller than the temperature dependence. The enthalpy of an ideal gas does not depend on pressure at all. The enthalpy of a real gas depends slightly on pressure. If we use Van der Waals equation, we can somehow derive the pressure dependence of the Van der Waals gas approximately. Delta H over delta P on a constant temperature condition is Nb minus 2AN over RT. A and B are the Van der Waals parameters. Now we have this delta H is approximately this Nb minus 2AN over RT times delta P. When the pressure changes in an isothermal process, you see this T in the subscript. That means when temperature is held constant, how does enthalpy depend on pressure? Now let's look at one numerical example problem 3.8.1. Estimate the molar enthalpy change for the nitrogen gas given its Van der Waals parameters A and B when the pressure changes from 1 bar to 30 bars. Okay, this is a very significant pressure change, but you will see the molar enthalpy change is very small. Now let's convert A and B to SI units just for convenience. And then we have B minus 2A over RT, which is just this divided by N. We're going to look at the molar enthalpy change. And now we plug in all the numbers in SI units. And then we have negative 7 joule per mole bar as this B minus 2A over RT. And therefore, the molar enthalpy change is B minus 2A over RT times the pressure change, delta P. Delta P is roughly 30 bars. After we do these calculations, we will be able to get this negative 0.2 kilojoule per mole. And this significant pressure change results in only a very small enthalpy change for the real gas. That means if a chemical reaction involves real gases, well, the pressure dependence from the enthalpy change of those real gases can be very, very small. And again, in general, the pressure dependence of a real gas is often very small, even if the pressure change is significant. Now we're going to look at another numerical example to show that the enthalpy of a solid and the enthalpy of liquid does not really depend on the pressure. Well, or you can say the pressure dependence of the enthalpy of a solid or a liquid is negligible. Again, we will change the pressure from 1 bar to 30 bars. This is a significant change. Now let's look at the molar enthalpy change for both ice and liquid water. And then we can estimate the change of the enthalpy of fusion of water when pressure changes. Now first, delta H over delta P is equal to V minus T times delta V over delta T under constant pressure condition. And this equation is correct for all substances. And now this delta V over delta T is simply V times alpha. This is from the definition of alpha. And then we have this expression. Since ice has a density of 0.92 gram per milliliter, we can compute its molar volume. The molar volume is simply the molar mass divided by the density. We get this much. And then delta H over delta P for ice is approximately this much. And we can compute this molar enthalpy change when the pressure changes from 1 bar to 30 bars. You can see this is only 57 joule per mole, or 0.057 kilojoule per mole. Note that the enthalpy of fusion or the enthalpy of chemical reaction, those are usually in like tens of kilojoule per mole, or sometimes even more than 100 kilojoule per mole. So this number is really small. Now let's look at liquid water. We have a molar volume of 18 milliliter per mole, and then we can compute this delta H over delta P, and it's roughly 18 milliliter per mole. Now, what if the pressure changes from 1 bar to 30 bars? How does the molar enthalpy of liquid water change? Well, it's just the molar volume, 18 milliliters over mole, times the pressure change. The result is also very small. It's 0.052 kilojoule per mole. And now when the pressure changes from 1 bar to 30 bars, the enthalpy of fusion of water is changed by this much. We're going to have the change of liquid water minus the change of the solid. It's only negative 0.005 kilojoule per mole. Now, what's the standard enthalpy of fusion of water at 0 degrees Celsius under 1 bar pressure? It's 6.02 kilojoule per mole. If you raise the pressure to 30 bars, still this enthalpy of fusion is about 6.02 kilojoule per mole. The pressure dependence of a solid or a liquid is negligible. Therefore, the pressure dependence of pretty much all chemical reactions is negligible. Again, in the end, it's just because the pressure dependence of the enthalpy of either a real gas or a solid or a liquid is negligible. Chapter 3: Internal Energy and Enthalpy. Section 3.9: Bomb Calorimetry. Chemicals combust in a bomb calorimeter under the isochoric condition, and therefore the reaction heat is equal to the internal energy change of the chemicals in the system. Let's look at the diagram of a bomb calorimeter. So we have a temperature reader. This is to monitor the temperature change of the system. And we have a bomb right here with a constant volume condition. We have sample inside. The sample may combust in pure high pressure oxygen. And over here we have fuse wires connected to the ignition box. We usually just push a ignition button to send the electric current through the wire, and the wire will be ignited first, which will in turn ignite the sample. And over here we have a stirring motor and a stirrer. This is to ensure the temperature is even inside this calorimeter. Now, how can we actually compute the enthalpy of reaction given the internal energy of the reaction? We have to do some theoretical derivations. H is defined to be U plus PV, and therefore delta H is delta U plus delta PV separately. And now if we can somehow measure the reaction heat, we will get this internal energy of reaction. But how can we get this delta PV, the PV change of the chemical system? Again, in this bomb, chemicals combust in high pressure pure oxygen, and then from the reactants to the products, the PV actually changes. But how can we account for the PV change? So first, we will neglect the PV change of liquids or solids, only because the PV change of a liquid or solid is much smaller than the PV change of a gas. So over here, this delta PV is approximately the delta PV of gases only. And for gases, we will use the ideal gas law to estimate PV, and PV is approximately nRT. And then we will estimate this delta nRT, the change of nRT. If we use a large water bath, the temperature change of the reaction will be very small. It's just because although the combustion heat can be significant, if we use enough water, the temperature change of everything inside the calorimeter may undergo a very small temperature change, for example 2 degrees Celsius. And then if the temperature goes from 298 K to 300 K, then this nRT changes just very small. So really this R and this T are treated as constant. Okay, R is indeed a constant. It's just we treat the temperature of the reaction also as a constant, even if the temperature increases during the combustion. However, this N is not a constant because we have a chemical reaction. This N is the number of moles of gases, and in chemical reactions we may have the number of moles of gases change. For example, if you combust benzene in oxygen, we will produce water and CO2. The number of moles of CO2 is very likely different from the number of moles of oxygen as a reactant. So delta U and delta H of the combustion reactions differ. They differ by approximately RT times the change of moles of gases. And because delta U and delta H of a combustion reaction is in the order of 10 to the power 3 kilojoule per mole, and this term is in the order of only 10 to the power 0 kilojoule per mole, that's why it's okay to make so many approximations, because if we have a for example 5% error for this delta PV term, it's not going to affect the delta U or delta H of this reaction significantly. And know that this delta N gases is unitless, because the physical meaning of this is the change of the number of moles of gases per mole reaction. We need to divide a mole in the end. So again, by looking at this diagram, we notice this water bath. We use a large water bath to absorb most of the heat released from the combustion. And again, this ensures the accurate measurement of the initial and final temperature, because we're trying to make sure the temperature is even inside the calorimeter. And also the water bath prevents the bomb from being overheated. One more reason is this: we ensure the temperature of change is really small. Again, from 298 K to 300 K, the change is even less than 1%. Therefore, from here to here, well, even though we introduced some error, the error is actually less than 1%. Alright, we made 3 approximations in this theoretical derivation. First, H is U plus PV, that's exact. From here to here, it's also exact mathematical derivation. But from here to here, we're assuming the product of PV of a liquid and from a solid is much smaller than those from gases. Again, it's just because the volume of gases are much larger than the volumes of liquids or solids. And now from PV to nRT, we assume it's ideal gas. And from delta nRT to RT delta N gases, we assume T is a constant and R is a constant. We can take R and T out of this delta. However, this N actually changes, because N sub gases is the number of moles of gases, and delta N gases is the change of the number of moles of gases per mole reaction. And very often we have different coefficients in front of the gaseous chemicals in a chemical reaction. So again, we're going to talk about the 3 approximations one by one. Over here, from here to here, we assume the change of PV of liquids and solids are negligible compared with that of gases. This approximation introduces about only 0.1% error in the calculation of this. 0.1% error is because the volume of a liquid or solid is usually only 0.1% of those of a gas. And then this is ideal gas law, PV equals nRT. This will introduce roughly 1% error in the calculation of this. And now here we assume the temperature is constant. That's why we can take the temperature out. What if the temperature actually changes by 1% from 298 Kelvin to roughly 301 Kelvin? Well, it does introduce roughly 1% error to this calculation. But overall, if we make the approximations for delta PV to be RT delta N gases, we introduce up to around 2% error to this. And this is, by itself is small enough. This is about 10 to the power of 0 kilojoule per mole, and then multiply by 2%. So the error is pretty small. Making this three approximations is reasonable. In this bomb calorimetry experiment, the combustion heat is absorbed not only by this large water bath, but also by anything else inside this calorimeter, which includes the bomb, the stirrer, the water bucket. Actually, there's a water bucket that holds the water, and also there's air on top of water, and there's inside surface of this calorimeter. All of these items absorb heat. Therefore, the heat capacity of everything inside the calorimeter is called the calorimeter constant. It's denoted by C sub calorimeter. Now let's look at one example problem, 3.9.1. The combustion of 0.01 mole standard chemical X raises the temperature of the water bath by 2 Kelvin. The internal energy of combustion is negative 2000 kilojoule per mole. The amount of water is 2 kilograms. Now let's calculate this calorimeter. Okay, this heat capacity of calorimeter is the total heat capacity minus the heat capacity of water. So first, let's compute C total. That's the heat capacity of everything inside, including water. How do we compute this? We have the amount of the substance, 0.01 mole. We have the internal energy change of the combustion, 2000 kilojoule per mole. By multiplying the number of moles and this internal energy change of combustion, we get 20 kilojoule. That's the amount of heat released from the combustion. And now this amount of heat divided by the temperature change, which is 2 Kelvin, we get 10 kilojoule per Kelvin. This is the heat capacity of everything inside the calorimeter, including the water. Now we need to subtract the water. So it's 10 kilojoule per Kelvin. Subtract the heat capacity of water. We have 2 kilograms of water, and its specific heat capacity is 4.184 kilojoule per kilogram Kelvin. And we do this calculation. In the end, we get 1.632 kilojoule per Kelvin. So the calorimeter constant is 1.632 kilojoule per Kelvin. And this calorimeter constant is the heat capacity of everything inside the calorimeter, excluding the water. Chapter 4, Entropy. Section 4.1, Definitions of entropy. In statistical thermodynamics, Boltzmann proposed an equation for entropy. Entropy equals the Boltzmann constant times the natural logarithm of W. W is the number of microstates accessible to the system. And the Boltzmann constant, K sub B, is equal to the ideal gas constant divided by the Avogadro constant. K sub B is 1.38 times 10 to the power of negative 23 joule per Kelvin. If we have n particles occupying various energy levels, we can compute the number of microstates accessible to the system. This uppercase W is n factorial divided by a1 factorial, a2 factorial, a3 factorial, etc. This n again is the total number of particles. A1 is the number of particles in energy level 1. A2 is the number of particles in energy level 2. A sub I is the occupation number of energy level I. In this diagram, as heat flows into the system, the number of microstates changes, going from 5 to 10 to 30. So over here, we have 5 particles, so 5 factorial on top. And then we have 4 particles in energy level 1, 1 particle in energy level 2, therefore W is 5. Over here, when heat flows into the system, one of the 4 particles can move to the second energy level. Now we have occupation numbers 3 and 2. W is 5 factorial over 3 factorial and 2 factorial, we get 10. If heat keeps flowing to the system, now we have a particle in the second lowest energy level. In this case, W is 30. When there's no particles in an energy level, we have 0 factorial, and 0 factorial is equal to 1. Again, in statistical thermodynamics, we have an equation for entropy proposed by Boltzmann. Entropy is equal to the Boltzmann constant times the natural logarithm of W, and W is the number of microstates accessible to the system. So the system can be in any one of the W microstates. In thermodynamics, however, we have a different definition for entropy, and it's defined indirectly. We define the differential of entropy. ds is equal to dq reversible over T. So over here, we have to have a reversible process, and then we can measure the amount of heat that flows into the system at a constant temperature T. That way we get the expression of entropy. Later in statistical thermodynamics, we can prove these two definitions are consistent with each other, and therefore we have the exact differential of entropy is equal to d, the exact differential of Kb, times the natural logarithm of the number of microstates. It's also equal to dq reversible over a temperature T. And we can equate these two sides. And over here we have kBT times the exact differential of Ln(W) is equal to dq reversible. We can now integrate both sides at constant temperature. Then we have this q reversible is kBT times the difference between the logarithm of final W minus the logarithm of initial W. And in the end, we have this equation. Okay, the final number of microstates divided by the initial number of microstates is a exponential function. It's e to the power of q reversible over kBT. So if q reversible is positive, we have more microstates in the end. If q reversible is negative, we have less microstates in the end. The number of microstates accessible to a thermodynamic system increases as heat flows into the system in a reversible isothermal process indicated by this equation. And loosely speaking, heat increases the disorder and thereby the entropy of the system, while work does not, because when we do work to the system, we're not changing the occupation numbers. Entropy is a state function. The change of entropy depends only on the initial and final states of the system. Therefore, the cyclic integral of ds must be 0, so it's expressed here. By the simplicity of this equation, the exact differential of entropy is equal to dq reversible over T. This equation can hardly be used to calculate the entropy change directly, because there's no simple relation between this temperature T and this dq reversible, and it's often more convenient actually to use this equation to rewrite the equation for ds, because du is dq plus dw. We have du is equal to dq reversible plus dw reversible for reversible processes. Again, du is equal to dq plus dw for all processes. Therefore, we can use that equation for reversible processes. Therefore, ds is equal to dq reversible over t, and dq reversible is du minus dw reversible. And dw reversible is simply negative pdv. And therefore, we can have this ds is equal to du plus pdv divided by t. Now, the internal energy can be expressed as a function of temperature and volume. Therefore, du can be expressed in terms of dt and dv. It's delta U over delta T times dt and plus delta U over delta V times dV. Now let's examine this part. Delta U over delta T under constant volume condition is simply the isochloric heat capacity. Why is that? Under constant volume condition, work is 0 and delta U is just delta Q under the constant volume condition. So over here we see delta Q over delta T under constant volume condition. Isn't that just C sub V, the isochloric heat capacity? And over here, delta U over delta V on a constant temperature condition is T times delta P over delta T on a constant volume condition minus P. We can prove this expression of delta U over delta V in chapter 5 after we learn the Maxwell relations. So for now, we'll just use this. And now we can plug in the expression of du. Well, it contains 1, 2, 3 terms. We will replace this du with these 3 terms. So ds is equal to du plus pdv over t, and then we plug in this 3 terms for du. Fortunately, this pdv and this pdv cancel, and then we have in the end only 2 terms. The exact differential of entropy is cv times dt over t plus delta p over delta t times dv. So it comes from here. This is delta p over delta t on a constant volume condition times dv. What about the temperature here? T and t cancel, and this negative pdv and positive pdv cancel. Now we have this expression. And because entropy is state function, so somehow if both the temperature and volume change for a system, we can always allow the temperature change first and followed by the volume change. Therefore, the finite change of this entropy is the integral of cv dt over t and the integral of delta p over delta t on a constant volume condition and dv. Somehow we can evaluate this delta p over delta t on a constant volume condition for an ideal gas. It's very simple. It's just p over t or nr over v. We can evaluate this for Van Hoff's equation, and the math is more complicated, but approximately this is also nr over v. For solids and liquids, actually delta P over delta T on a constant volume condition can be expressed as alpha over kappa, and alpha and kappa are approximately constants for liquids and solids within a moderate temperature range and pressure range. We just need to plug in the values of alpha over beta here and then multiplied by the change of volume. We get the second component. So that's not too bad. And usually we will be given the molar heat capacity for the substance, and then multiplied by n, we get C sub V. Now, it's possible to express ds in terms of dt and dp as well. Remember, among pressure, temperature, and volume, there are only 2 independent variables. Which 2? Well, we just choose the 2 variables that make our derivation more convenient. Now let's look at this situation. What if we want to express entropy in terms of temperature and pressure? For example, in some cases both the initial and final temperatures and pressure are given, and we would like to compute entropy this way. And then ds is dq reversible over t, and dq reversible is du minus dw reversible. dw reversible is negative pdv. Now we have this equation, and remember u is h minus pv based on the definition of enthalpy. Enthalpy is u plus pv. So now we have on the top dh minus dpv plus pdv. We can expand this. This is pdv plus vdp based on the product rule in calculus. Now we have this equation. It's dH minus VdP over temperature. Now we will express enthalpy in terms of temperature and pressure. dH is delta H over delta T times dt plus delta H over delta P times dP. Pay attention to the 2 subscripts. And now if you look at this one, delta H over delta T under constant pressure condition is simply Cp. And then delta H over delta P under constant temperature condition is volume minus T times delta V over delta T. We can prove this derivation for delta H over delta P is this in chapter 5. So now we're going to plug in the expression of dH. So 1, 2, 3, 3 terms on top for dH and then minus VdP. And then fortunately this VdP and this negative VdP cancel. So we have only 2 terms left for the differential of entropy. The 2 terms are Cp dt over T and also negative delta V over delta T times dP. And again, entropy is a state function. So if both temperature and pressure of the system change, we can allow the temperature change first to calculate the entropy change. And then we allow the pressure to change. The entropy of this system can then be calculated using this equation. The finite change of entropy delta S is the integral of Cp times dt over T and then minus the integral of delta V over delta T times dP. So we have only 2 terms in this expression of the finite change of entropy. So note that this ds can be expressed in terms of dt and dp or in terms of dt and dv. And again, because there are only 2 independent variables out of PVT, it's okay to pick any 2 variables. You can even express entropy as a function of PV, but it's not very convenient. So usually we say the entropy is a function of TP or a function of TV. And we got these 2 expressions for ds. ds is Cv dt over T plus delta P over delta T times dV. ds is equal to Cp dt over T minus delta V over delta T times dP. Which equation should we use? Well, just use the one more convenient for us. For example, if we are given the initial temperature, volume, and the final temperature and volume, I would use the equation on the left. If we are given the initial and final temperature and pressure, we will use the equation on the right. Now, the differential of entropy may be expressed in terms of dt and dp or in terms of dt and dv. So we have these 2 equations over here, and therefore these 2 equations should be exactly the same. The reason is entropy is a state function, so there's only one way to calculate the difference of entropy. Given the same, there's only one possible value of delta S between the initial and final state, and therefore this expression should be equal to this expression. So we write that equation here: Cv dt over T plus delta P over delta T times dV is equal to Cp dt over T minus delta V over delta T times dP. And now we move this dt term to one side and the dv dp term on the other side. We have this equation, and now we see Cp minus Cv times dt over T is equal to the sum of 2 terms. One is delta P over delta T times dV, one is delta V over delta T times dP. We can further expand dV because V is a function of temperature and pressure. dV is delta V over delta T times dt plus delta V over delta P times dP. So now we actually make this expression more complicated. Now we have 3 terms. The first term is this times this, we put it here, and then delta P over delta T times delta V over delta P over here, and then we have a 3rd term here. By looking at these 3 terms, we notice this one depends on dt. This one, well, it depends on dp. This one depends on dp. And somehow these 2 terms cancel. And why the 3rd term and the 2nd term cancel? Well, we will use the reciprocal rule and the triple product rule in calculus. This delta P over delta T times delta V times over delta P, and then times delta T over delta V is -1. Therefore, the product of these 2 is -1 over delta T over delta V. Using the reciprocal rule, we can flip this, and then we have negative delta V over delta T. Look at this. This is negative delta V over delta T. This is positive delta V over delta T. And they have the same subscripts. Therefore, these 2 terms cancel. We have only 1 term left, and dt cancel. We will get a expression for Cp minus Cv. So we have this expression. Again, we're going to cancel dt and dt, both sides multiplied by temperature. We have the expression for Cp minus Cv. It's temperature times delta P over delta T times delta V over delta T. Over here we have volume in the subscript. Over here we have pressure in the subscript. So again, this is the analytical expression for Cp minus Cv for all substances, regardless of the state, whether it's a gas, a liquid, a solid. We can always use this equation. And in summary of this section, the exact differential of entropy can be expressed in various ways. We usually use these two equations. In the first equation, entropy is expressed as a function of temperature and volume. In this equation, entropy is a function of temperature and pressure. When do we use this equation or this equation? Depending on the information given to us. If we know the temperature and volume, we use the first equation. If we know the temperature and pressure, we use the second equation. Again, these two equations hold for all substances, regardless of the state, whether it's solid, liquid, or gas. And also, by equating these two equations, we can actually derive the expression for Cp minus Cv. It's temperature times delta P over delta T under constant volume condition, and then times delta V over delta T under constant pressure condition. Cpm minus Cvm is simply T times delta P over delta T, and then over here we need to divide this volume by the number of moles. So we have delta Vm over delta T under constant pressure condition. Chapter 4, Entropy. Section 4.2, the Carnot cycle. The Carnot cycle consists of 4 reversible steps. In each step, P external is equal to P. The Carnot cycle is a process undergone by an ideal gas. So here we have the diagram for a Carnot cycle. It involves 4 steps: the red one, black one, blue one, and black one. 4 states are involved in this cycle. They are arbitrarily labeled 1, 2, 3, 4. But we're gonna study these 4 steps from state 3. So from state 3 to state 2, it's isothermal expansion under a constant temperature condition. And temperature is denoted by TH, T hot. From 2 to 1, it's adiabatic expansion, volume increases. Adiabatic means Q is 0. And then we go from 1 to 4. It's isothermal compression because volume decreases. And in this compression, temperature is again held constant, but this temperature T sub C is different from T sub H. T sub C stands for T cold, lower than T hot. Finally, we go from 4 to 3. It's adiabatic compression. We get back to this original state. So we can go from this state 3 and then 3 to 1, 4, 3. Alright, we're going to look at all 4 steps, and we will compute Q, W, delta U, and delta H for all steps. And we'll see after this Carnot cycle, delta U and delta H should be 0 because U and H are state functions. However, Q and W are non-zero. Now, what about entropy? Well, delta S is also 0 because entropy is also a state function. So we're going to do some calculations, some derivations in this section. First, let's look at this isothermal expansion from state 3 to state 2 at this temperature T sub H. Actually, it's just T hot. Because this is expansion, work should be negative, and we can derive the expression for work. Work hot is equal to negative integral P external dV. The reason I put P here is because all 4 steps are reversible steps. Therefore, P external is equal to P. And we integrate this from the initial state 3 to the final state 2. in this isothermal expansion. And pressure is nRT over V. nRT is a constant because this is isothermal. We take nRT hot out of the integral. We integrate 1 over V dV. That's the logarithm of V, and then we have this equation. This is less than 0 because V2 is greater than V3. So this logarithm is positive, but we have a negative sign here. Therefore, this work is less than 0. What about delta U of this step from 3 to 2? It's isothermal expansion of an ideal gas. Well, because the internal energy of an ideal gas only depends on temperature, delta U is 0. If delta U is 0, Q is delta U minus W, which is just negative W, and we get this expression for Q sub hot. Q is greater than 0 in this isothermal expansion of ideal gas. And similarly, if we look at this step from 1 to 4, it's also isothermal. It also involves ideal gas. It's just this process is compression at a lower temperature. Using similar derivation, we have W cold, which is negative nRT cold times the natural logarithm of V4 over V1. Because V4 is less than V1, the logarithm is negative, and we have another negative sign here. This work at T cold is greater than 0. Delta U again is 0 for this ideal gas under constant temperature condition, and Q is delta U minus W. In this case, Q is less than 0. So we analyzed these two steps from 3 to 2, isothermal expansion at T hot. From 1 to 4, that's isothermal compression at T cold. Again, T hot is greater than 0. The expression says heat flows from a hot reservoir to the ideal gas. The reason we can keep a constant T hot temperature is because we're assuming our ideal gas is in thermal contact with an infinitely large hot reservoir with this temperature. And now we have this expression of entropy. This is the definition of entropy in thermodynamics. It's an indirect definition. We define the differential of entropy as dq reversible over T. So we have dq reversible coming from this, and then we have temperature over here. So delta S hot at this temperature is dq hot over T hot. Because T hot is constant, we can take this T hot out of this integral. Then we have the integral of dq hot. The integral of dq hot is just q hot. Now we have q hot over T hot. We get this expression, going from here to here. All right, we have this expression for the entropy change of this ideal gas under a constant temperature condition. In this isothermal expansion, temperature is constant, volume increases, entropy increases. Similarly, we have Q cold, and we can derive the entropy change of this isothermal compression. We have this expression: volume decreases and entropy decreases. All right, there is no heat flow in the adiabatic steps. So this is adiabatic expansion, this is adiabatic compression. Both are reversible, so we get this equation. The entropy change of a adiabatic reversible process is 0, only because of the definition of entropy here. If it's a reversible process and dq is 0, ds is equal to 0 over temperature. It's just 0. There's no change in entropy when an ideal gas undergoes this adiabatic and reversible process. And now we will prove this logarithm and this logarithm are opposite to each other. They have the same magnitude and opposite sign. The proof is very simple because we know entropy is a state function, and therefore the cyclic integral of ds should be 0. So the sum of the entropy changes of these 4 steps from 3 to 2, 2 to 1, 1 to 4, 4 to 3, the sum should be 0. And we have entropy change of the isothermal expansion, the entropy change of the isothermal compression, and these two are the adiabatic expansion and compression. The sum is 0. And now by looking at this equation, well, divided by nr, we get this equation. So we have proven the logarithm of v4 over v1 is equal to negative logarithm of v2 over v3. We can remove the logarithms. We can just say, yeah, v4 over v1 is simply the reciprocal of v2 over v3. So you can also say v4 over v1 is v3 over v2. v1 over v4 is simply v2 over v3. And through just simple algebraic operation, we can see this v1 divided by v2 is equal to v4 divided by v3. So we get a lot of equations for the ratios of the volume in this cyclic process. We can prove this same equation using a different way. From 2 to 1, it's adiabatic and reversible. We know the temperature ratio is the volume ratio to the power of 1 minus gamma. From 4 to 3, it's adiabatic and reversible. Therefore, the temperature ratio is the volume ratio to the power of 1 minus gamma. And pay attention here, T1 and T4, they are actually the same. T1 and T4, they are both T cold. Actually, T2 and T3 are the same. They are both T hot. Alright, so we have this equations over here. And also gamma is just Cp over Cv. Now what I will do is I will multiply this right hand side and this right hand side. Okay, so this times this is going to be T1 T3 divided by T2 T4. T1 is T cold, T3 is T hot, T2 is T hot, T4 is T cold. So if you look at this, the result is actually 1. Alright, because T cold cancel, T hot cancel. So this is 1. Therefore, this is 1. Alright, we can combine this two. And therefore, we have the logarithm of V3 divided by V2, V4. This is just 0. And then, because the logarithm of multiplication is just the addition of logarithms. And we can actually flip this v1 over v4. We can flip this by putting a negative sign here. v2 and v3, we also do the same thing. We put a negative sign here. So mostly it's just from multiplication to addition. And we swap the numerator and denominator by adding a negative sign in front. We have this equation. And then we can move this to the right hand side. We have this equation at the beginning. We have proven this equation. The logarithm of v4 over v1 is equal to negative logarithm of v2 over v3. Also, it means v4 over v1 is equal to the reciprocal of v2 over v3. Alright, so again we have this cyclic Carnot cycle. That means the integral of the cyclic integral of all state functions should be 0. Alright, and we have expressions for as hot and as cold. Alright, so overall the entropy change in the Carnot cycle should be 0. So is the cyclic integral of internal energy, that should be 0. The cyclic integral of enthalpy should be 0. I didn't mention the cyclic integrals of pressure, volume, temperature, but obviously they should be 0 as well, because PVT are also state functions. However, Q and W are path functions. Therefore, it's very likely the cyclic integral of Q is non-zero. Let's look at this. This Q Carnot is the cyclic integral of Q. There are 4 steps. We have 1, 2, 3, 4. Adiabatic expansion, Q is greater than 0. Oh, I'm sorry, isothermal expansion, Q is positive. Adiabatic expansion, Q is 0. Isothermal compression, Q is negative, and over here this is adiabatic compression, Q is 0. All right, and we have this part. This part is actually Q hot. This part is Q cold, and together we have the integral of TdS, and TdS is dq reversible. That's from the definition of ds, and we know this is greater than 0. We have seen the derivation of this part and this part. This part and this part have opposite signs and different magnitude, because this part is proportional to Q hot. This part is proportional to this part is proportional to T hot. This part is proportional to T cold. So this magnitude is greater than this magnitude. So therefore, this Carnot cycle is not going to be 0. And also, we can look at the graphical representation of Q Carnot. If you imagine this integral T hot times TdS, well, it's just the area under this function t with respect to s. So that means we should just make a graph of temperature versus entropy, temperature versus entropy, and we'll do isothermal expansion. Temperature is constant T hot. That's why I have this red arrow with a constant temperature. So going from to here, and the horizontal axis is entropy. So what's this integral? This integral is just the area under the red curve. So I'm going to draw the rectangle here. So from here to here, and then to here, and then to here, and then to here. So the area of this rectangle is the integral of T hot times ds at T hot. All right, so this integral. Right, and then let's look at this one, T cold, ds cold. Well, it's the area from here to here, and then we have this smaller rectangle. Again, this is positive, this is negative, so overall it's going to be this large rectangle minus this small rectangle. The large rectangle minus this small rectangle under the blue arrow is simply the shaded area, and this rectangle has a physical meaning. That's Q sub Carnot. This is the amount of heat of the entire Carnot cycle. Alright, this is just calculus, the integral of this function. The S is just this shaded area. Alright, again, the area under this arrow is simply 0 because the width is 0, same here. So 0 and 0. Now let's get back to the PV diagram. Okay, if we get back to PV diagram, because P external is P, so this cyclic integral of P dV is equal to the cyclic integral of P external dV. So if you look at this shaded area, that's the amount of work. That means the amount of work of this Carnot cycle is not 0. It's equal to this shaded area. Again, over here, this is the integral of PdV from 3 to 2, and down there the integral, okay, is from 2 to 1, and go back, we need to subtract this area, and then we need to subtract this area. So after you subtract the integral from 3 to 2 and 2 to 1, after you get this integral from 3 to 2 and 2 to 1, it's actually from this line, this vertical line to this vertical line. You get a very large integral area, and then you need to subtract the integral below this 1 to 4 and 4 to 3. So you need to subtract this much. Therefore, the shaded area is the cyclic integral of PdV, which is the cyclic integral of P external dV, which is the amount of work, or the magnitude of work, because over here we do not have that negative sign. In the expression of work, we have work is equal to negative integral of P external dV. So we're going to have a summary over here. In the Carnot cycle, the entropy gain of the system in the isothermal expansion at this temperature cancels its entropy loss in the isothermal compression. Well, because entropy is a state function, so they have to cancel. The cyclic integral of entropy has to be 0. Alright, so we have this equation. And the change of any state function in a cycle should be 0. So we have delta T, delta P, delta V, delta S, delta U, delta H, they're all 0. Later, after we learn Gibbs energy and Helmholtz energy, delta G is 0, delta A is 0. Alright, but Q and W are path functions. So Q of this entire Carnot cycle is not 0, W is not 0. However, Q and W should cancel because we know delta U is 0. So over here we have Q is positive, W is negative, and these two have the same magnitude, and therefore, well, they cancel. This Q of a Carnot cycle and this W of a Carnot cycle should cancel, so that delta U in the end is 0. And overall, the Carnot engine converts heat to work. So if you think about this, Q Carnot is greater than 0, so in each Carnot cycle, heat flows into this Carnot engine, and the W of this Carnot cycle is less than 0. That means this Carnot engine can do work to its surroundings, and overall this Carnot cycle absorbs heat and does work to the surroundings. The heat is converted to work, and the amount of the conversion is this. But don't forget, this Q hot is positive, Q cold is negative. So over here, Q hot plus Q cold, so it's actually less than Q hot. In the Carnot cycle, the system, which is the ideal gas in a Carnot engine, gets heat from a cold hot reservoir. It releases heat to the cold reservoir, but there's a difference. The difference between Q hot and Q cold is the amount of work done by this Carnot engine, and we can have the relation between Q hot and Q cold. Q hot over T hot is equal to Q cold over T cold, and it's equal to this amount of work over T hot minus T cold, and overall we have this is equal to 0. This is only because when we sum up these two, we get the Q Carnot, and the Q Carnot plus W Carnot, it's delta U of the Carnot cycle, which should be 0. Alright, so we have this equation, and then we have this equation. We can then determine the efficiency of this Carnot engine. Overall, this Carnot engine gets heat from hot reservoir, okay, which is this Q hot, and part of the heat is released to the cold reservoir, and the other part is converted to work. So this is greater than 0, okay, and these two arrows are both less than 0. Alright, so one example is this. It's possible for this Q hot to be, for example, 100 joules, and this is, for example, 60 joules, and then only 40 joules of this energy is converted to work. And the efficiency of the Carnot engine is this 40 joules over 100 joules. It's 40%. Alright, it's going to be 40%. Here's the analytical expression. The efficiency of the Carnot engine is denoted by epsilon. Epsilon is the amount of work of the entire Carnot cycle divided by Q hot, and it's just T hot minus T cold over T hot. And we can simplify this. This is 1 minus T cold over T hot. This is always less than 1 because we cannot achieve a 0 T cold. Okay, for us to have this T cold to be exactly 0 Kelvin, it's impossible. So this ratio is always greater than 0 but less than 1. So this epsilon is always less than 1. Alright, the Carnot engine cannot convert heat to work at 100% efficiency. This statement is actually equivalent to the second law of thermodynamics. We can prove this later. We looked at the efficiency of a Carnot cycle, which is this much. Epsilon is the amount of work of the entire Carnot cycle divided by Q hot. It's just this, or 1 minus T cold over T hot. So we got this expression. Epsilon is less than 1. A Carnot cycle cannot convert heat to work at 100% efficiency. And if we look at any other reversible cycle, we can actually express just any reversible cycle as the sum of an infinite number of infinitesimal box-shaped TS temperature versus entropy Carnot cycle. Because if you look at this process, if this process is reversible, we can divide this process into a infinite number of small rectangles. In each rectangle we have a Carnot cycle. So this is isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. And over here we have the cyclic integral of TdS, and this is just the amount of Q in a Carnot cycle. So we can just divide this arbitrary process into an infinite number of rectangles, and the area inside this arbitrary process is equal to the sum of the areas of all those rectangles, and each rectangle is a Carnot cycle, and in each rectangle you have this Q and this W. So again, in the end, just an arbitrary reversible process can be decomposed into a sum or a combination of just Carnot cycles, and therefore in the end the efficiency of any reversible process should have a efficiency less than 1. Okay, in each of those rectangles the efficiency is less than 1, so overall the efficiency is also less than 1. And again, this Q Carnot of this arbitrary process is simply the sum of the areas of all rectangles in this graph. Chapter 4, Entropy, Section 4.3, Heat Engine, Heat Pump, and Refrigerator. A Carnot engine is a heat engine because it converts heat to work. Not at 100% efficiency, it's always lower than 100%. This is because a Carnot engine absorbs heat from a hot reservoir, and it releases part of the absorbed heat to a cold reservoir. The remaining part becomes work, denoted by work sub Carnot. Q hot is greater than 0 because heat flows into the ideal gas in the Carnot engine. Q cold is less than 0 because heat flows out of this ideal gas to a cold reservoir. And W Carnot is less than 0 because the ideal gas of this Carnot engine does work to its surroundings. And overall, Q hot plus Q cold plus W Carnot should be equal to 0, because after each Carnot cycle this delta U should be 0, and U is a state function. Now let's look at the efficiency. It's defined to be the magnitude of the work in this Carnot cycle divided by Q hot, the amount of heat provided to the Carnot engine. And then we have this equation, and this equation is 1 minus T cold over T hot. Therefore epsilon should always be less than 1. Now let's look at the diagram of a heat pump. You may notice the heat pump looks almost exactly the same as a Carnot engine. And actually a heat pump is simply a reversed Carnot engine. We reverse the direction of Q hot, we reverse the direction of Q cold, and we reverse the direction of work. And over here, work is done to the ideal gas in this heat pump. Over here, if you see this W, it's no longer W Carnot, it's W electric. A heat pump must be powered by electricity, and this electric work is done to the heat pump. Therefore, this arrow flows into the heat pump. This work is greater than 0. And now, what does a heat pump do? Well, it actually absorbs heat from the cold air outside your room, and then it pumps heat into your room air in the winter. So a heat pump can actually transfer heat from a colder region to a hotter region, well, with some help, electricity. Now if we look at the magnitude of Q hot, Q cold, and work, they are exactly the same as those of a Carnot engine. However, the signs all change. This becomes negative, this becomes positive, and this becomes positive. What's the efficiency of a heat pump? Well, it depends on which function we want to maximize, this one. Which function we want to minimize, this one. We like to reduce the electric utility bill. We like to maximize this Q hot. The amount of heat flows into the room air, so the equation for the efficiency of a heat pump is Q hot over this electric work. Q hot is proportional to T hot, and this work is proportional to T hot minus T cold. By looking at this equation, the efficiency of a heat pump is always greater than 1. Alright, for example, if T cold is 270, T hot is 300, you can see the result is going to be 300 divided by 30. It's actually much larger than 1. And why is that? Well, it's just because not only this electric work is converted to Q hot, this Q cold is also converted to Q hot. Now we're looking at a refrigerator. We have the Carnot engine and refrigerator side by side. A refrigerator is also a reversed Carnot engine. We have Q hot, we have Q cold, we have work, but all those directions are reversed. This Q hot is less than 0, this Q cold is greater than 0, and over here this work is greater than 0 for this refrigerator. So that means we need to power this refrigerator by electricity, and this work goes in, electric work goes in. It helps to extract cold from a cold reservoir and release the heat to a hot reservoir. But for a refrigerator, well, we usually use the air inside this refrigerator as the cold reservoir. So over here, we extract heat from the air inside the refrigerator. And where does this energy go? We have work into refrigerator. We have extract air from the air inside the refrigerator. Where does the energy go? It goes to the room air that surrounds the refrigerator. That's why we still have Q hot, Q cold, and work. The sum of Q hot, Q cold, and work is still 0. But again, compared to a Carnot engine, all the directions are reversed. This Q hot is now going to be less than 0, Q cold is greater than 0, work is greater than 0. For a refrigerator, we have a different equation for efficiency. Because for a refrigerator, what do we want to maximize? We want to maximize Q cold. We care about the amount of heat that we can remove from the inside of the refrigerator. And also we like to reduce the electric utility bill. So in this case we have Q cold over work. And this is the expression, this is going to be T cold over T hot minus T cold. Again, Q cold is proportional to T cold. Q hot is proportional to T hot. And finally, work is proportional to T hot minus T cold. Again, refrigerators are reversed Carnot engines. We need to reverse all 4 steps in the Carnot cycle to achieve the cycle for a refrigerator. And because of that, the signs of Q hot, Q cold, and W are all reversed in a refrigerator. And make sure you understand why the efficiency for a refrigerator is different from the efficiency for a Carnot engine. For Carnot engine, we like to maximize work. That's why work is on top. For Carnot engine, we want to minimize Q hot. That's why Q hot is on the bottom. However, for a refrigerator, we like to minimize work, the electric work. We want to maximize Q cold. Now we have 3 different equations for the efficiency of a Carnot engine versus a heat pump versus a refrigerator. Again, it's just because our goal is different. For a Carnot engine, we like to maximize work. Therefore, work is on top. For a heat pump, we like to maximize Q hot. That's why Q hot is on top. For a refrigerator, we like to maximize Q cold. That's why Q cold is on top. Now let's get back to Carnot engine. What do we want to minimize? We want to minimize Q hot. That's why Q hot is on the bottom. For heat pumps and refrigerators, we like to minimize the electricity. That's why this work is on the bottom. For this reason, we have 3 different equations for the efficiencies of a Carnot engine, heat pump, and refrigerator. Going from here to here, just remember work is proportional to T hot minus T cold. Q hot is proportional to T hot, and Q cold is proportional to T cold. So that's why we got those equations. Here's one numerical example, 4.3.1. Compute the efficiency of an ideal Carnot engine, an ideal heat pump, and an ideal refrigerator. The temperature of the hot reservoir and cold reservoir are 300 Kelvin and 250 Kelvin. First, just a reminder, U is a state function, so delta U is a cyclic integral of internal energy in this cyclic process. Therefore, it has to be 0. So Q hot plus Q cold plus W Carnot has to be 0. Alright, now let's use these 3 equations for a Carnot engine. We have 300 minus 250 on top, 300 on the bottom. The efficiency is only 1/6. It's roughly 17%. But if you look at the efficiency of a heat pump, well, you have T hot on top, and then the difference between T hot and T cold on the bottom. The efficiency is 6 or 600%. It's actually more than 100%. For a refrigerator, you have T cold on top, the temperature difference on the bottom. The efficiency is 5 or 500%. And over here, there's another numerical example. So you just imagine you have an ideal gas as your system. There's a 300 Kelvin reservoir, which is your hot reservoir, 250 Kelvin as the cold reservoir. So really, if 6 joules of heat flows into the system, 5 joules flows into the cold reservoir, 1 joule is done to the surroundings as work. That's a Carnot cycle for the heat engine. Alright, so you can see we get only 1 joule of work out of 6 joule of this Q hot. The efficiency is 1/6, which is 17%. But if you look at a heat pump, alright, we are using 1 joule electricity, and somehow we can also get 5 joules of heat from the cold air outside your room. We combine this 1 and 5, and we can pump 6 joules of heat into the room air. That makes you feel warmer, and the efficiency is 6/1/1. That's 600%. If we look at this as a refrigerator, our goal is to abstract heat from the cold air inside the refrigerator. So somehow, if we can abstract 5 joules of heat from the refrigerator, with only 1 joule electricity, what's the efficiency? It's 5 joule over 1 joule. That's 500%. So again, the Carnot engine does 1 joule of work, provided 6 joule of heat. Therefore, the efficiency is only 1 out of 6. The heat in the amount of 5 joule is dissipated into the cold reservoir, and this amount of heat is considered wasted for a Carnot engine. What about a heat pump? It can pump a total of 6 joules of heat into the hot reservoir. So among this 6 joules, 1 joule from electricity, 5 joules from the cold air. Therefore, the efficiency is 6 over 1. The refrigerator can abstract 5 joules of heat from the inside cold air. That means inside the refrigerator, given only 1 joule electricity. Therefore, the efficiency is 5 joules over 1 joule. That's actually 500%. So if you look at a Carnot engine, a heat pump, and a refrigerator, keep this in mind. The efficiency of the Carnot engine is always less than 1. The heat pump and the refrigerator are reversed Carnot engines. They have different equations for efficiency, because when you look at the heat pump, we care about Q hot. When you look at the refrigerator, we care about Q cold. Chapter 4, Entropy. Section 4.4, Entropy change in reversible and irreversible processes. It's straightforward to calculate the entropy change of a system that undergoes a reversible process. This is the definition of entropy in thermodynamics. The differential of entropy is dq reversible over T. dq reversible is du minus dw reversible. dw by itself is negative p external dv, but now it's a reversible process, so p external is equal to p. Therefore, dw reversible is negative p dv. Negative dw reversible is positive p dv. Now we have this expression for the differential of entropy. U is a function of temperature and volume. Therefore, du is delta U over delta T under constant volume condition times dt, plus delta U over delta V under constant temperature condition times dV. And this term is C sub V. This is because in the isochoric condition, delta U is equal to delta Q. Delta Q over delta T is C, the heat capacity. Now, what about this delta U over delta V under constant temperature condition? In chapter 5, we'll be able to prove this is equal to T times delta P over delta T minus P for all substances. Now we have this du expanded into 3 terms. We replace this du with these 3 terms, and then we have only 2 terms left, because this positive PdV, this negative PdV cancel. Now we have only 2 terms in the end. We have CVdT over T over here. That's from this term divided by T. And also we have this term, delta P over delta T under constant volume condition times dV. So it's from this times dV over temperature. So we have this. Again, PdV, negative PdV cancel. What if a system changes from its initial state to its final state in an irreversible process? Well, you simply forget about this process and design another process which is reversible, that connects the initial state to the final state. And then you use the same equation to compute the entropy change of the system. Why? Because entropy is a state function. The definition of ds is dq reversible over T. So if you see an irreversible process that connects the initial to the final state, that information is useless when we compute the entropy change of the system. Alright, we need to have this dq reversible. So we have to mentally design a reversible process that connects the initial state and the final state. And then we can use this equation. Alright, because of that, the entropy change is the integral of Cv dt over T plus the integral of delta P over delta T times dV. So basically, we just need to integrate this. That accounts for the temperature change. We need to integrate this. That accounts for the volume change. Again, when the initial and final temperature and volume are given, we use this equation. What if the initial and final temperature and pressures are given? Then we can use this equation. We have ds is equal to Cp dt over T minus delta V over delta T times dP, proven in the previous video. We just integrate this side, that accounts for the temperature change, and then minus the integral of this, that accounts for the pressure change. And also, I think we have proven this sum is equal to this difference. So this equation for ds and this equation for ds, they can be proven to be the same. They are equivalent to each other. Now let's look at one numerical example problem, 4.4.1. An ideal gas, 2 moles, expands reversibly in an isothermal process until its volume doubles. Calculate the molar entropy change of this ideal gas, and also calculate the entropy change of the surroundings of the system. Again, we'll just use this equation, all right? And because I think we're given information about temperature and volume. Temperature, isothermal, there's no temperature change. This dt is 0. Therefore, we just need to look at one term. Over here, pressure is doubled. So we just need to integrate this. How can we integrate this? First, it's an ideal gas. So delta P over delta T is equal to nR over V for an ideal gas. It's just simple derivative problem. And then we can replace this derivative with nR over V, and then we can integrate this nR over V dV. And since the question is asking about the molar entropy, so we're going to have this divided by N, and we have this R times Ln2. Why Ln2? It's the natural logarithm of volume, and the volume doubles. So V final over V initial is 2. So we have this, R is 8.314 times Ln2, we get 5.763. Yeah, the unit is joule per Kelvin mole. Since the amount of the ideal gas is 2 moles, we can also compute the entropy change of the gas. Just 2 moles times the molar entropy change, we get 11.53. What about the entropy change of the universe? It has to be 0 because this is a reversible process. Alright, in a reversible process, the entropy change of the universe must be 0. And therefore, we can just write out this equation. Delta S plus delta S surroundings has to be 0. Therefore, delta surroundings should be negative 11.53. Or we can calculate the entropy change of the surroundings this way. We'll use the definition of entropy. ds is equal to dq over t. So delta S of the surroundings is the integral of dq surrounding over t. And dq surroundings is negative dq, all right? And then dq is du minus dw. Now we have this. And because du is 0, why? Isothermal ideal gas. Therefore, du has to be 0. We get this equation. And dw is negative p external dv. However, it's a reversible process, so dw can be written as negative p dv. So we have this. And the pressure over T is nR over V, and then we just need to integrate this. In the end, we get negative nR ln2. So over here, delta S is positive nR ln2. For the surroundings, the entropy change is negative nR ln2. The sum is 0. The entropy change of the universe is 0. That means this process can be reversed without violating the second law of thermodynamics. Now let's look at a different numerical problem. Now this ideal gas expands against vacuum until its volume doubles. We're going to calculate the molar entropy of this ideal gas. Alright, this is an irreversible expansion. So we cannot just say, well, ds is equal to dq over t, because the definition of entropy in thermodynamics is dq reversible over t, and this is not a reversible process. The expansion against vacuum is not a reversible process because P external is 0 and the system pressure is greater than 0. P external is different from P. So we cannot compute entropy directly based on the information given from this statement. What we have to do is we have to design a reversible process that connects the initial state and final state. So if we look at the final state, the volume has doubled. What about the temperature change? The temperature change is 0, only because this is an ideal gas expands against vacuum. We cannot have heat flows into or out of the vacuum. We cannot do work to the vacuum. So during this expansion, there's no change in the internal energy of this gas. All right, dU is just 0. dW is 0, dQ is 0. All right. So because of that, there's no temperature change in this ideal gas. Why? Because if there's no internal energy change and there's no potential energy change for this ideal gas, therefore there's no kinetic energy change. The temperature is constant. Alright, so we have T final equals T initial, and V final is equal to 2 times V initial. So if you really think about all those changes from T initial to T final, V initial to V final, it's actually exactly same as this. If you just look at the initial and final states, the numerical problem 4.4.1 and the numerical problem 4.4.2, they share something in common. They have the same initial states, they have the same final states. So really, we do not have to do any numerical calculations for this problem. We'll just design a reversible process that connects the initial state and the final state. This process is isothermal, reversible, and in the final volume is 2 times the initial volume. The final temperature equals the initial temperature. Alright, so we can just borrow the result from this numerical calculation. We get delta S is just this, and we have delta S molar entropy change, which is this. Again, the molar entropy change of the system is R times Ln2, and the entropy change is Nr times Ln2. Alright, so we'll just use the same result. We can get the molar entropy change of the system. It's just R times Ln2. We get 5.763 joule per mole Kelvin. Alright, another numerical example problem, 4.43. 2 moles of ideal gas expands against vacuum until its volume doubles. Now this time, let's calculate the entropy change of the universe. When the gas expands against vacuum, we know P external is 0 and P is greater than 0. So it is a irreversible process. Therefore, the entropy change of the universe must be positive. Now we're going to verify that. First, let's look at the entropy change of the system. Again, when we look at the entropy of the change of the system, we have to do the calculation not based on this information. What we need to do is we need to mentally design a reversible process that connects the initial state and the final state. The initial state and the final state, they differ in the volume. The volume has doubled. However, they have the same temperature. Again, it's just because there's no change in internal energy or kinetic energy. Therefore, there's no change in temperature. Alright, so we can still use this equation. Again, we're assuming that a reversible process has been mentally designed to connect the initial state and the final state of the system. And because dt is 0, we have only one term, and then this delta P over delta T is Nr over V. So we can easily compute this delta S. It's 11.53 joule per Kelvin. Now, what about the surroundings? Because the ideal gas expands against the vacuum, nothing can be done to the vacuum. Therefore, nothing has changed the surroundings. The entropy change of the surroundings is exactly 0, because it's surrounding the system. There's a vacuum and there's no change done to the vacuum. That's why. And what about the entropy change of the universe? Well, the universe is the system plus the surroundings. Therefore, the total entropy change of the universe is delta S plus delta surroundings, and now we get a positive number. And remember, as long as the change of the entropy of the universe is positive, it cannot be reversed. Because if we were able to reverse the process, the entropy change of the universe would be negative 11.53 joule per Kelvin. That means the entropy of the universe would decrease, and that's a violation to the second law of thermodynamics. We cannot do that. Now again, just to summarize, reversible versus irreversible. In a reversible process, the entropy of the universe remains constant, and that's why we can reverse it. In an irreversible process, the entropy of the universe increases. That's why we cannot reverse such a process. And again, the total entropy change of the entire universe is the entropy change of the system plus the entropy change of its surroundings. When we calculate the entropy change of the system, you may just focus on the initial state of the system and the final state of the system. For example, if you know the initial temperature, initial volume, and the final volume, you should be able to calculate the entropy change of the system. You can ignore any information about the process, whether it's reversible or irreversible. Just ignore this process. You just focus on the initial state and final state. And again, this is just because entropy is a state function. For the same reason, to calculate the temperature change of water, you just need the initial temperature of the water and the final temperature of the water, right? You do not need the information about the process between the initial temperature and final temperature. Delta T is just T final minus T initial. Temperature is also a state function. Hopefully by looking at this analogy, you should understand when we calculate the entropy change of the system, we just need to focus on the initial state of the system and the final state of the system. However, when we calculate the entropy of the surroundings, there's something slightly different. We should always use this equation. In this equation, we're going to assume this Q of surroundings is always reversible. So that means when we calculate this ds surroundings, we should use the definition of entropy, which is dq surroundings reversible over T surroundings. However, because the surroundings is infinitely large, this is the rest of the universe, we're going to assume whatever happens to the infinitely large surroundings is reversible. And therefore, we can simply just drop this reversible because any dq surroundings is dq surroundings reversible. So we have this. Now dq surroundings is negative dq, right? So again, dq surroundings is equal to negative dq. We have this because we're assuming q of surroundings plus q is always 0. That means we're just assuming q of the universe is 0. There's no heat flows in or out of the universe. So this is where this equation comes from. And now we have this equation. We have negative dq over T surroundings. We always use this to calculate the entropy change of surroundings. Now we integrate both sides. Delta S surroundings is the integral of dq over T surroundings. Again, T surroundings is the temperature of the surroundings, but for convenience, you can also say it's the temperature of the immediate surroundings. Alright, because again, the surroundings is infinitely large. If you have a bottle of water and the moon is part of the surroundings of the bottle of water, and the temperature on the moon is totally different from the temperature of the immediate surroundings of your water bottle. So that's why it's just reasonable to just use the immediate surroundings instead of the temperature of the moon. And in this equation, we made a big assumption, which is this: we don't care if the process is reversible or irreversible to the system. Okay, it's always reversible or considered reversible for the surroundings. So we can always use this equation. And dq surroundings is always equal to negative dq. Again, we're assuming dq of the universe is always 0, and therefore we can go from here to here. Alright, so now this equation is always used to calculate the entropy change of the surroundings. Now let's look at one more numerical example problem, 4.4.4. Let's look at this 20-liter ideal gas with 4 bar pressure expanding to 80 liters against a P external equals 1 bar at constant temperature. It's isothermal, and if you look at this, P is 4 bar initially, P external is 1 bar. Therefore, there is a finite difference between P external and P. We know this process is irreversible, and also we know it's constant temperature. Therefore, du is 0 for this ideal gas. Alright, because it's an irreversible process, we know the entropy change of the universe is greater than 0. And also, we can quantitatively calculate the entropy change of the universe. So first, let's look at this delta S surroundings. When we look at delta S surroundings, again, we'll just use this equation. This is integral of negative dq over T surroundings. Because it's an isothermal process, there's no change in temperature of the system, and therefore we can assume T surroundings is equal to T. Otherwise, there's going to be some temperature change to the system inevitably. So we'll have to assume T surroundings is equal to T, so we get this equation. And because T is constant, so it's just T on the bottom. On top, we have integral of the Q, so that's just negative Q. Negative Q is W minus delta U, and we have this equation. Delta U is 0 because it's an ideal gas and it's isothermal. So we have W over T. W is negative P external times V final minus V initial. This forms the work equation. You know, work is equal to the integral of negative P external dV. So over there. And P external is equal to P final, because this system will expand until P final is equal to P external, which is 1 bar. So I'll just replace P external with P final over here, and now we have this expression. And it's actually hard to compute this directly. Right now, I'm gonna just try to get the common factor, PF VF over T. So we have PF VF over T. Alright, so this is why there's minus 1 here. Obviously, this is different from PF VF over T. It's PF VI over T. So this term is PF VF over T times VI over VF. I'll let you verify. This multiplied by this is just the first term. The reason I do this is because PF VF over T is simply NR. It's just that we have an ideal gas, so PV equals NRT. T never changes, so PF VF is equal to NRT, and this is just NR. What about VI over VF? VI is 20 liters, VF is 80 liters, so we plug in this equation, and we have a quarter minus 1, which is negative 0.75 NR. I mean, it's fairly easy for you to just plug in, you know, the values of N and R to compute this, but I think this is good enough to answer this question. For the system, however, when we calculate the entropy of the system, we'll have to just focus on the initial state and final state, because this is a irreversible process. This information is useless. We have to focus on just the initial state and the final state of the system, because entropy is a state function. And for a reversible process, we'll just use this equation, because temperature is constant. So we have this expression. When we have this expression, we have NR over V, because it's an ideal gas. We'll just integrate this, which is NR times Ln4. The reason is very simple. LnV final minus LnV initial is just Ln4 over here, and we get a positive expression for the entropy change of the system. So when the system expands in this irreversible process, the entropy change of the system is positive. The entropy change of the surroundings is negative. They do not cancel. They do not cancel. We sum it up, we get a positive number, positive 0.636 NR. This is greater than 0. That's why this process cannot be reversed, because the reversal would violate the second law of thermodynamics. Another numerical example, 4.4.5. So now we have a 20 liter ideal gas expands to 80 liters against P external equals P. So when you look at this, you know it's reversible, and you know the entropy change of the universe should be 0. So if you don't do any calculation, you just say the entropy change of the universe is 0, it's actually correct. But we can also calculate the entropy change of the surroundings. We can also calculate the entropy change of the system. First, let's calculate the entropy change of the surroundings. It's the integral of negative dq over T surroundings. Because it's an isothermal process, T surroundings is just T. And we have negative dq. Okay, we can integrate that. We get negative q over T. it's W minus delta U. Delta U is 0, so we have delta W over T. W is negative integral P dV, and P is nRT over V, and then we have all this. The surroundings has a entropy change of negative nR ln4 in the end. Now, what about the system? Again, we're going to use this equation. We mentally design a reversible process. Well, it happens this is already reversible, so we'll just use this equation. There's no temperature change, so we just integrate this dV term, and delta P over delta T is nR over V for an ideal gas. We integrate this, we get nR times the natural logarithm of V final over V initial. This is nR ln4. So for the surroundings, the entropy change is negative. For the system, the entropy change is positive. For this problem, they cancel. The entropy change of the universe is exactly 0. Now let's look at the entropy change of a liquid or a solid. We can calculate the entropy change using either of these two equations. So both equations are correct. This equation is used when temperature change and volume change are given. This equation is used when temperature change and pressure change are given. Now delta P over delta T can be proven to be alpha over kappa. What is alpha? Alpha is actually delta V over delta T on a constant pressure condition and then divided by V. What is kappa? Kappa is defined to be a little bit different. It's actually negative delta V over delta P under constant temperature condition divided by V. The reason we have negative sign in the equation of kappa is to ensure the numerical value of kappa is always positive. Alright, kappa is compressibility. Alright, this is how the relative volume changes when the pressure changes. Alright, alpha is how the relative volume changes when the temperature changes. Okay, now we have this equation, and delta V over delta T is simply alpha times V. So we have these two equations. The reason we rewrite those derivatives in terms of alpha and kappa is because for a liquid or a solid, the values of kappa and alpha are approximately constant within a moderate temperature change and a moderate pressure change. So it's just very convenient for us to plug in the values of alpha and kappa here and here. Alright, numerical problem 4.4.6. Calculate the molar entropy change of copper when its temperature changes from room temperature to like 26 degrees Celsius, and when the pressure changes from 1 bar to 2 bars. We have the density of copper, we have alpha and kappa of copper, we have CPM of copper, we have a lot of information. So now we have pressure change. So let's look at this. Let's look at this and this. These two terms have physical meanings. Over here, this is a molar entropy change under isobaric condition. This is molar entropy change under constant temperature condition. So first, let's look at this one. This is molar entropy change under isobaric condition. So we have this term over here, this term over here. Plug it in. All right, they just differ by the number of moles. We plug in all the numbers, we get this much. Now over here, what if temperature is held constant? And then we need this second term, negative V alpha dP. So we plug it in here. Again, these two just differ by the number of moles. And what's the molar volume? It's this one. Molar volume is just molar mass over density. That's molar volume. All right, molar mass over density, you get molar volume. And then you have alpha over here, and then you have pressure change over there. We get this one. Now let's compare this number and this number. I think this number is so much bigger than this number. This is 10 to the power of negative 2. This is 10 to the power of negative 5. Over here, temperature changes. Over here, pressure changes. So really, entropy depends much more on the temperature change than on the pressure change. Alright, but still, what's the total molar entropy change? We just sum it up. This is due to the temperature change. This is due to the pressure change. We sum it up, we get this number. The entropy change of a liquid or a solid may be calculated using either this equation or this equation. Either way, I mean, just based on the information you're given. If you are given temperature and volume, use this equation. If you are given temperature and pressure, use this equation. Alright, so now another numerical example 4.4.7. Calculate the molar entropy change of copper when its temperature changes from this to this. We have pressure change from this to this. The density of copper is this, and we have alpha and kappa. And now this time we have CVM of copper. Alright, not CPM, we're given CVM of copper. So somehow it's a little different from the previous example. In the previous example 4.4.6, I'm going to show you, we're given CPM. Over here we're given CVM. Alright, and now let's calculate the entropy change. So there are a bunch of ways to do the calculations. One way is to compute CPM given CVM, and then we're going to just do this. Alright, just like in the previous example, all the same calculations except one thing. From CVM we compute CPM. But another way is this. We can use this equation instead. We can get the temperature change, and also we can get the volume change, and then we integrate this part, and then we integrate this part. Alright, so first let's look at this. In this equation we have molar entropy change under constant volume condition. That's why we can use CVM over here. We have CVM over here, and then logarithm T final over T initial. We get this number. This is the entropy change of the system because due to the temperature change under constant volume condition. Now let's look at how the entropy changes when the volume changes. First thing, we need to calculate the volume change. How does the volume change? The volume depends on the temperature and pressure. So this will give you the relative volume change multiplied by molar volume. We'll get the absolute volume change. And why is this a relative volume change? Remember alpha. What is alpha? Alpha is delta V over delta T divided by V. What is kappa? Kappa is negative delta V over delta P divided by V. So that's why over here the first term will give you the relative volume change due to temperature change. The second term will give you the relative volume change due to the pressure change. So we need to sum it up, and then we get the molar volume change. It's a very small number in cubic meter divided by mole. Now we can compute this. We have alpha, we have kappa, we have delta V. Where does this come from? It comes from the second term over here for the differential of entropy. Alright, we just plug in on the numbers, we get this. So if you compare these two numbers, again, the entropy depends more on the temperature change, less on the volume change. But still, we can sum it up, and we get the total entropy change per mole of the substance. And it's 0.08186. If we look at the previous example, 0.08184, and if you really think about it, the initial and final states of this numerical problem and the initial and final states of this numerical problem, they are actually the same. So supposedly we get the same result, and indeed we get the same result. Only the last digit differ. It's just some like numerical inaccuracy. So really important for us to realize that this equation is exact for all substances. This equation is also exact for all substances. Which equation should we use? We can use either one. But we need to examine the information given to us and use the equation that's more convenient. If we're given the temperature change, pressure change, and if we are given CPM as well, we definitely use this equation. What if we are given the temperature change, the volume change, and CVM? We definitely use the first equation. What if we have only CVM and then pressure change? Okay, somehow we can calculate CPM given CVM, or somehow we can just compute the volume change, alright, given the temperature change and pressure change. Either way, we should be able to get the same results if we are starting from the same initial state and same final state, only because, remember, entropy is a state function. The change of the entropy of a system is simply the final entropy minus the initial entropy, which does not depend on the process. So that's why you can use this equation. You can use this equation. Over here, we just look at how entropy changes with temperature when the volume is constant, and then how entropy changes with volume when temperature is constant, and then we sum it up. Over here, we just look at how entropy depends on temperature when pressure is constant, and then how entropy depends on pressure when temperature is constant, and then we sum up this to delta S. And either way, you should be able to get the same numerical value like I showed you here, 0.08186, and over here 0.08184. Okay, they are essentially the same. Chapter 4, Entropy, Section 4.5, the second law of thermodynamics. The second law of thermodynamics states that the entropy of an isolated system can never decrease. Therefore, any process that's associated with the entropy increase of an isolated system is irreversible, because such a reversal would result in the entropy decrease of an isolated system, and that's a violation to the second law. The universe is considered an isolated system, and therefore the entropy of the universe can never decrease. And we can also use this mathematical inequality here. The change of the entropy of the universe can never be negative. It has to be positive or zero. The entropy of an isolated system always increases, except for two scenarios. Scenario 1, this system has reached thermodynamic equilibrium. That means its entropy can no longer be changed. It has been maximized. Scenario number 2, this isolated system undergoes a reversible process. For example, reversible adiabatic expansion. In this case, dq reversible is 0. And remember, in thermodynamics, ds is equal to dq reversible over 0. So if dq reversible is 0 itself, ds is 0, delta S is 0. So in this scenario, entropy is a constant. Again, we have these two different scenarios. Scenario number 1, the system has reached thermodynamic equilibrium. The entropy has been maximized. Scenario 2, it's reversible adiabatic for this isolated system, and then the entropy remains unchanged. Now let's look at one example problem, 4.5.1. Calculate the entropy change of the universe when 1 mole water freezes at temperature T, and T is lower than 0 degrees Celsius by an infinitesimal amount under 1 atm pressure. We may assume this T surroundings is equal to T, so both of these are actually, you can say 0 degrees Celsius, or you can say, well, it's lower than 0 degrees Celsius by an infinitesimal amount. Alright, and then we can assume dq is equal to dq reversible, because for such a process we may consider this process is reversible. Alright, so by looking at this reversible, you might think, well, then this delta S universe has to be 0. It's correct. Now let's look at delta S and delta S surroundings individually. So first, ds is dq reversible over t. That's the definition. And 2, if dq is equal to dq reversible, we have this dq over t as the expression of ds, then delta S is the integral of dq over t. Now if you look at the surroundings, it's also the integral of dq over t, but with a negative sign. So these two may cancel. The entropy change of the universe is thus 0. Now why this equation? Again, we learned this. For the surroundings, any dq surroundings is considered a reversible dq surroundings, and dq surroundings is equal to negative dq, because we're assuming dq universe is always 0. There's no heat flows into the universe, there's no heat flows out of the universe, therefore dq of the universe is 0. Therefore dq plus dq surroundings is always 0, and that's why I was replacing this dq reversible with negative dq, and then the result is expected. The change of the entropy of the universe is 0 for this reversible process. Again, we can express this as the second law of thermodynamics. Well, basically this says, well, the entropy of the universe cannot decrease. Now let's look at example problem 4.5.2. Let's prove delta S universe is positive when heat flow from the higher temperature surroundings to the lower temperature system. So heat flows into the system, Q is positive. And delta S of the system is Q over T cold. This is the temperature of the system. Now let's look at the surroundings. It's negative Q over T hot. Delta S universe is the sum of delta S of the system and delta S of the surroundings. So we need to add this up, and then Q is the common factor. Really it's just 1 over T cold minus 1 over T hot, and then multiply by Q. Again, Q is positive because heat flows into the system. And let's take the difference here. This difference is also positive because T cold is less than T hot. So overall, delta S universe is greater than 0. Now, what if the system has a higher temperature? The surroundings has a lower temperature. Let's evaluate the entropy change of the universe. Same equation here. Again, the universe is simply the system plus its surroundings. And delta S is Q over T hot. T hot is the temperature of the system, and then T cold is the temperature of the surroundings. So we have this expression. We can combine this two because we have this Q is the amount of heat lost by the system, and this Q is also considered the amount of heat gained by the surroundings. But if you look at the sign of Q, Q is less than 0 because Q is defined to be the heat that flows into the system. In this problem, heat flows out of the system, and therefore Q is negative. Now let's look at the entropy change of the universe. It's the sum of these two. We'll take the common factor out. We're going to use negative Q here, and then it becomes 1 over T cold minus 1 over T hot. Negative Q is positive, and 1 over T cold minus 1 over T hot is also positive. And therefore, the entropy change of the universe is greater than 0. Again, in this example problem, heat flows from the surroundings to the system. In this example problem, heat flows from the system to the surroundings. Either way, the entropy change of the universe is greater than 0. The entropy change of the universe is greater than 0. But in these two cases, what's in common? What's in common? It is this: heat flows from a higher temperature object to a lower temperature object. Heat flows from a higher temperature object to a lower object temperature. So that means the heat flow from a higher temperature object to a lower temperature object is a spontaneous process which is associated with the entropy increase of the universe, and we cannot reverse it because the reversal would result in the violation to the second law. And another thing I want to mention is later we're going to see this delta S is greater than Q over T cold, and over here this delta S is greater than Q over T hot for this problem. So in the end, this delta S universe is greater than this expression, but of course this is greater than 0. So if you have this delta S universe greater than a positive number, so this is greater than 0, so it's going to be greater than a positive number, and therefore it has to be positive. Same here, this delta S universe is greater than this positive number, and this tells us the entropy of the universe increases. Chapter 4, Entropy. Section 4.6, the Clausius inequality. The Clausius inequality states that the temperature times the differential of entropy is greater than or equal to the differential of Q. TdS is greater than or equal to dQ. This inequality can be derived from the second law of thermodynamics for an isothermal process in which T surroundings is equal to T. Because the second law states the entropy of the universe cannot decrease, we have this inequality: ds plus ds surroundings must be greater than or equal to 0. Therefore, ds is greater than or equal to negative ds surroundings. ds surroundings is equal to dq surroundings over t surroundings. And therefore we have ds is greater than or equal to negative dq surroundings over t surroundings. And because dq surroundings is negative dq, and then we have this inequality, ds is greater than or equal to dq divided by t surroundings. The temperature of the immediate surroundings of the system is the same as the temperature of the system. We can just replace this t surroundings with t. Therefore, ds is greater than or equal to dq over t. Now both sides multiply by temperature. We have TdS is greater than or equal to dq. So when we have a reversible process, TdS is equal to dq. That's actually the definition of entropy. Remember, the definition of entropy in thermodynamics is indirect. Its ds is equal to dq reversible over t. That's when this equal sign holds. For any irreversible process, TdS is greater than dq. The Clausius inequality can be proven in a different way, more generally. Assuming the initial state and final state of a system are connected by a reversible path and also by an irreversible path, we have du reversible equals du irreversible. This is because u is a state function. So now we have this equation. Du reversible is equal to dq reversible plus dw reversible. And du irreversible is dq irreversible plus dw irreversible. When we have a irreversible process, work is negative p external dv. When we have a reversible process, dw is negative p dv. Now we have this equation. And then this dq reversible is simply TdS. So over here, this is equal to this based on the definition of entropy in thermodynamics. Now we have this equation. TdS minus pdv is equal to dq irreversible minus p external dv. Now we will move this dq irreversible to the left-hand side, pdv to the right-hand side. So TdS minus dq irreversible is equal to pdv minus p external dv. And this is just p minus p external and then multiplied by dv. So we will analyze this product for two different scenarios. If p is greater than p external, the system will have to expand, and dv is greater than 0, and then this product is greater than 0. What if p is less than p external? That means the system will have to be compressed. dv is less than 0, and still this product is positive because p minus p external is negative, dv is also negative. The bottom line is this: the sign of p minus p external and the sign for dv are the same. Therefore, the product is always positive. Either way, this is positive. That means this is positive. Well, that means, well, TdS minus dq irreversible is positive. If TdS minus dq irreversible is positive, we have TdS being greater than dq irreversible. And also we have TdS equals dq reversible for a reversible process. That's just the definition of entropy in thermodynamics. Now we have this Clausius inequality. TdS is greater than or equal to dq, and this equal sign holds only for reversible processes. In an isothermal process, we have TdS greater than or equal to dq. dq is negative dq surroundings, and negative dq surroundings is just negative t times ds surroundings. And now we can see this TdS plus this TdS surroundings should be greater than or equal to 0. And now we have this inequality, both sides divided by temperature. We actually get the second law of thermodynamics. ds plus ds surroundings should be greater than or equal to 0. Chapter 4. Entropy. Section 4.7. The third law of thermodynamics. The third law of thermodynamics states that the entropy of a perfect crystal is zero as its temperature becomes 0 Kelvin. Given this zero reference, the absolute value of the entropy of a solid at finite temperatures can be determined with this equation. The entropy at temperature T is equal to the entropy at temperature T minus the entropy at 0K equals delta S. This is because entropy is a state function, and also the entropy of such a perfect crystal is 0 at 0K. So really, if we can determine the entropy change from 0K to this T prime, we should be able to determine the absolute value of the entropy of this solid. When there is no phase change, the exact differential of entropy is this. This is an indirect definition of entropy in thermodynamics. ds is equal to dq reversible over T. dq is du minus dw. dw is negative p external dv, and over here, if the process is reversible, we can say dw is negative p dv. Even if there is a irreversible process that connects the initial state and the final state, you can always mentally redesign a different reversible process and use q reversible there. So that's why we can do this. And du is dh minus pdv minus vdp. Therefore, we have this equation. ds is dh minus vdp. Now we're going to expand h. h is a function of temperature and pressure. That's why dh is delta h over delta t times dt plus delta h over delta p times dp. So we have this. What's delta h over delta t under constant pressure condition? It's just c sub p. It's just because dh is equal to dqp under the isobaric condition. What about delta h over delta p? It's v minus t times delta v over delta t. We'll prove this in chapter 5. Now vdp and vdp cancel. We have these two terms. When pressure is held constant, for example, if we have this process under a constant pressure condition, then ds is simply just cp dt over t. And therefore, the entropy of this solid at T prime is equal to the entropy difference between 0 temperature and T prime temperature. And this difference is simply the integral of Cp dt over T. The third law of thermodynamics states that the entropy of a perfect crystal is 0 when temperature is 0. So given this zero reference, we can also determine the entropy of a liquid at a finite temperature. How do we do this? We can again go from 0K solid to the liquid at temperature T prime. But we need to divide this process into 3 steps. The first step, we increase the temperature from 0K to the melting point. In the second step, the solid melts into liquid at the melting point. Above the melting point, we heat up the liquid. Because entropy is a state function, we just need to calculate the entropy change of the first step, of the second step, of the third step, and then we sum everything up. When pressure is held constant, the entropy of fusion at the melting point is determined this way. ds is dq over t, dq is dq sub p under isobaric condition for a reversible process. Over here, this reversible means, well, when the solid melts, the temperature should be higher than the melting point. But how much higher? What's the difference? The difference should be infinitesimal. Now we have this equation. ds is dH over T fusion, and then delta S fusion is simply the integral of this. Because the fusion temperature is constant, it's just the melting point, so we have the integral of dH over T, which is delta H over T at the melting point. Again, at the melting point, delta H fusion is the melting point times the entropy change of fusion. T fusion is just the melting point. Again, because entropy is a state function, the entropy of the liquid at temperature T prime minus the entropy of the solid at 0K, so this is actually 0, is equal to the sum of three terms. In this first term, we increase the temperature of the solid from 0 to the melting point. In the second step, we look at the entropy of fusion, which is delta H of fusion over T of fusion. Third step, we increase the temperature of the liquid from T fusion to T prime. Sorry about this mistake here. This should be T prime. The third law of thermodynamics states that the entropy of a perfect crystal is 0. Therefore, we can even calculate the entropy of a gas at a finite temperature. We just need to convert the solid at 0K to the gas phase at temperature T prime, and T prime is higher than the boiling point. And in this case, we need to divide the entire process into 5 steps. In the first step, we heat up the solid. In the second step, it's the fusion process from solid to liquid at a constant temperature, the melting point of the substance. And then between the melting point and the boiling point, we heat up the liquid. At the boiling point, we vaporize the liquid into gas. Above the boiling point, we heat up the gas. Therefore, there are 5 steps. We just need to add up the entropy changes of all these 5 steps. The first step, we heat up the solid. In the second step, fusion. Third step, we heat up the liquid from the melting point to the boiling point. The fourth step, well, we vaporize the liquid into a gas. The last step, we heat up the gas. Again, when there's no phase change, ds is Cp dt over T under isobaric condition. Therefore, you see this integral of Cp dt over T for solid, Cp dt over T for liquid, Cp dt over T for gas. At the melting point, delta H fusion equals T fusion times delta S fusion. So delta S fusion is this delta H over T. At the boiling point, delta H equals T times delta S as well on the isobaric condition. Therefore, over here we have the entropy change of the vaporization process. Again, at the temperature of a phase transition, delta H is T times delta S. This T is the temperature when this phase change or phase transition occurs. Delta H and delta S are the changes of enthalpy and entropy in this phase transition under isobaric condition. Under isochoric condition, which is extremely rare, we have delta U equals T delta S. Now we're going to analyze the entropy values versus the entropy values of a gas versus the entropy values of a liquid and the entropy values of a solid. In general, the molar entropy of a gas is greater than that of a liquid, which is in turn greater than that of a solid. And also, entropy increases as temperature increases. And there are more rules that help us compare the entropy of different chemicals. A weakly bound matter always has a greater entropy than a strongly bound one. Therefore, the transient state of this reaction has a tighter structure and thereby a lower entropy than the two separated reactants. The transient state of this reaction has a structure with hydrogen atom in the middle, partially bonded to chlorine and partially bonded to bromine. This transient state structure is more tightly bound than two separate chemicals. Here's another example. The transient state structure of the Diels order reaction has a tighter structure than two separated reactants, and therefore lower entropy than the two separate reactants. The entropy of a system increases as the number of microstates increases, and therefore molecules with more vibration modes have a higher entropy than the ones with fewer vibration modes, because we have more vibrational entropy. Molecules with more atoms have more vibration modes and therefore higher entropy. Here's one example. Ethane contains 8 atoms, methane 5 atoms. Therefore, the molar entropy of ethane is greater than the molar entropy of methane. Ethane has many more vibrational modes, therefore higher vibrational entropy. Propane has higher molar entropy than ethane for the same reason. For noble gases, heavier atoms have smaller translational energy spaces and thereby higher entropy than lighter ones. Therefore, neon has a higher molar entropy than helium. Argon has a higher entropy than neon. For similar molecules with the same number of atoms, heavier molecules always have higher molar entropy. For example, this is tetrabromide. This is carbon tetrabromide. It has a higher molar entropy than carbon tetrachloride. This is just because the heavier molecule have higher translational entropy. And also, a heavier molecule often has a higher rotational entropy as well. So overall, heavier molecules have a higher entropy than lighter molecules if they have roughly the same structure. Chapter 4, Entropy, Section 4.8, Entropy Change in Chemical Reactions. When we have a pure substance, we can calculate the entropy change given the temperature change and volume change. We can also compute the entropy change given the temperature change and pressure change. When the temperature change and volume change are given, we can either use this equation or this equation. They are equivalent to each other. However, usually it's easier to use this first equation to calculate the entropy change when ideal gas. We have Cv dt over T plus delta P over delta T on a constant volume condition Tv. If we have an ideal gas, delta P over delta T is simply Nr over V, and we just need to integrate Nr over V dV, and that's easy. What if we have a liquid or solid? In that case, delta P over delta T can be expressed as alpha over kappa. The reason we do this is because alpha and kappa are approximately a constant for a liquid or solid within a fairly wide temperature range and a fairly wide pressure range. That means we can just look up the numerical values of alpha and kappa for the liquid and solid, and we'll plug those values in. And the entropy change due to the volume change of a solid or liquid is simply alpha over kappa multiplied by the volume change. That's why for ideal gas we use this equation. For liquid or solid we use this equation. What about a real gas? We use the same equation for the ideal gases, but this provides us a approximate value for the entropy change of a real gas. Sometimes we're given temperature and pressure. Then we use this equation to compute the entropy change of ideal gas. Again, these two equations can be proven the same. But over here, if we have the pressure change, it's just easier to integrate Cp dt over T, and then integrate this negative delta V over delta T dP. For ideal gas, delta V over delta T under constant pressure condition is simply Nr over P. We just need to integrate this negative Nr over P dP for ideal gas. For real gas, we can still use this equation to get an approximate result. For liquid or solid, we use this equation. This is because alpha is defined to be delta V over delta T times V, or divided by V. Therefore, V times alpha is delta V over delta T under constant pressure condition. And again, for liquid or solid, we can look up the value of alpha and then we plug this in here. And we have the volume of the liquid or solid, and then we can compute the entropy change due to the pressure change. We just integrate this, and volume, alpha are approximately constant. So the integral of this is just negative V alpha times the pressure change. Again, for an ideal gas at constant temperature, it's pretty easy to calculate the entropy change. It's just because when temperature is constant, this dt is 0, this dt is 0. And then ds is either delta P over delta T times dV or negative delta V over delta T times dP. Again, we can just use either of these two. If we use the first one, delta P over delta T is Nr over V, and then we need to integrate this. We get the natural logarithm of V final over V initial, and then multiply by Nr. That's easy. Over here, we have a negative sign. Delta V over delta T is Nr over P. We can also integrate this. Alright, so this is the integral. We get negative Nr times the natural logarithm of P final over P initial. We can actually prove this equation and this equation are exactly the same because the pressure is inversely proportional to the volume. So P final over P initial is equal to V initial over V final. And pay attention to negative sign over here. The entropy of an ideal gas of pressure P can be determined given its standard entropy. So what is a standard entropy? That's just the entropy when this substance is in a standard state. For a gas, it's just 1 bar. So here, the difference between the entropy at pressure P and the standard entropy is simply negative Nr times the natural logarithm of P over P naught. P naught is 1 bar. We get it from this expression. We can divide both sides by the number of moles. The molar entropy of an ideal gas with this pressure is the molar entropy of this same ideal gas under standard condition, which means 1 bar minus R times the natural logarithm of P over P naught. So for ideal gas, if temperature is constant, the molar entropy depends on the pressure. When we have a higher pressure, we have a lower molar entropy. For real gases, we'll just use the same equations to get approximate solutions. So what equations? Again, there's 2 equations. Now let's look at example problem 4.8.1. Calculate the difference between the entropy of 1 mole oxygen in air and 1 mole pure oxygen in the standard state. So the oxygen gas, well, of course it's a real gas, but approximately we can use these 2 equations. So the entropy of the oxygen at pressure P minus the standard entropy is negative Nr ln P over P naught. And if we have oxygen in air, the partial pressure for oxygen is 0.2 bars. P naught is 1 bar. So we plug in all the numbers and do the calculation we get 13 joule per Kelvin. This means the entropy of 1 mole oxygen in air has a larger entropy than pure oxygen in the standard state. How much larger? 13 joule per Kelvin larger for 1 mole oxygen in air versus 1 mole pure oxygen in the standard state. We know the oxygen gas in air is more disordered than pure oxygen, and this is just because we have 1 mole oxygen in air versus 1 mole oxygen in standard state. You have different volume. The 1 mole oxygen gas in air occupies a larger volume than 1 mole pure oxygen in the standard state, and therefore the energy of this oxygen in air is more dispersed, and that means we have higher entropy, because entropy is a measure of energy dispersal. So we have learned 3 different definitions of entropy. Entropy is a measure of disorder. Entropy is a measure of energy dispersal. Entropy is a measure of the natural logarithm of the number of microstates. For solids and liquids, we can use this equation when temperature and pressure change. So over here, this is the entropy change due to the temperature change. We just need to integrate this. Over here, this is how entropy change depends on pressure change. And also, we can integrate this. The integral of the first term is just Cp times the natural logarithm of T final over T initial. The integral of negative V alpha dP is approximately negative V alpha times the change of pressure. This is just delta P. So if we have Ti, Tf, Pi, Pf, we look up the value of alpha, we get the volume of the substance. We just use this equation to compute the entropy change for a liquid or a solid. Again, we can do that only because for a liquid or solid, this alpha is approximately a constant. The volume of the liquid or solid is approximately a constant. Alright, that's why we can integrate this approximately. Now for a chemical reaction from A to B at room temperature and 1 bar, we can compute its standard entropy of reaction. The standard entropy of reaction at room temperature is the standard entropy of product at room temperature minus the standard entropy of reactant A at room temperature. What if we do the reaction at a different temperature, such as 500 Kelvin? Well, we can just break down this chemical reaction at 500 Kelvin into 3 steps. The first step, A at 500 Kelvin, we change it to A at 298 Kelvin, and then we allow the reaction to proceed at room temperature to get B. And then finally we convert B at 298 Kelvin to B at 500 Kelvin. We make sure all 3 steps proceed under the standard condition. That means 1 bar condition. Now we can calculate the entropy change of step 1, step 2, and step 3. So this is the entropy change of step 1 from 500 Kelvin to 298 Kelvin. Step 2, the reaction proceeds at room temperature. Step 3, we change the temperature of B from room temperature to 500 Kelvin. Now we can just copy this here and then combine the first and third integrals. It's just the integral of 298 Kelvin to 500 Kelvin, and over here we have dsB minus ds sub A. Now if you look at this, we can rewrite ds as dq over t for reversible processes. So over here ds is dq over t, so we have this equation. And we do know dq is c dt, so dq of B for mole B is just CPM of B, alright, times dt. So we rewrite dq as CDT for B and also for A. When we look at this, it's just the change of the standard CPM in the reaction. So over here, it's the change with a delta sign of the molar heat capacity under the standard condition. So again, this superscript means 1 bar or standard condition. More generally, the standard entropy change at temperature 2 is equal to the standard entropy change at temperature 1 plus integral. The integral from T1 to T2 of delta CPM dt over T. Delta CPM is the change of the molar entropy. This denotes the standard state. So this equation looks very similar to this equation for enthalpy at different temperatures. So the standard enthalpy of reaction at T2 is equal to the standard enthalpy of reaction at T1 plus integral. This integral is from T1 to T2, and we're integrating delta CPM dt. For entropy, we integrate delta CPM dt over T. So this is the only difference. So by deriving this equation for enthalpy at different temperatures, we can have similar derivation for the standard entropy of reaction at different temperatures. Again, these two equations look awfully similar to each other. Now let's look at one example problem, 4.8.2. The standard enthalpy of formation of ABC are these three numbers in kilojoule per mole at room temperature. We have standard entropy of ABC in this joule per mole Kelvin at room temperature. Now let's calculate the standard enthalpy and the standard entropy of this reaction from A plus 2B to C at room temperature. So how do we do this problem? Well, the standard enthalpy of reaction is, well, again, the product minus reactants. The product is C, we look up the value, and then minus A, this is A, and then minus 2B. This is minus 2B. We get negative 50 kilojoule per mole. That's the standard enthalpy of reaction. About the standard entropy of reaction, same. C is the product, so we use the value for C minus A. This is A minus 2B. We get negative 115 joule per mole K. That's the standard entropy of the reaction at room temperature. Alright, and now we're going to assume the molar isobaric heat capacity of ABC in problem 4.8.2. So this one, approximately this much, between this temperature range, between 25 degrees Celsius to 55 degrees Celsius. Now we can compute the standard enthalpy and the standard entropy of the same reaction at 55 degrees Celsius. First, we need to know delta CPM. So we have the product C minus A minus 2B. We get this number, negative 5 joule per mole K. So this is just the change of CP per mole reaction. Now delta H of the reaction at 55 degrees Celsius or 328 Kelvin is simply the room temperature enthalpy of reaction plus this integral from 25 degrees Celsius to 55 degrees Celsius of delta CPM dt. We have delta CPM, negative 5 joule per mole K. We integrate this, and then here we have the result, negative 50.15 kilojoule per mole. Note that the enthalpy of reaction at 55 degrees Celsius is negative 50.15. The enthalpy of reaction at room temperature is negative 50. These two are awfully close to each other. So later you will see very often in physical chemistry, if we know the enthalpy of reaction at room temperature, we usually can use the same number for the same reaction at different temperatures, as long as the temperature difference is not too big. In this case, the two temperatures differ by 30 degrees Celsius. However, the enthalpy of reaction, well, you can see they differ by only 0.3%. Now let's look at the entropy of reaction at 55 degrees Celsius. It's equal to the entropy of reaction at room temperature plus this integral of, over here, it's delta CPM dt divided by T. We need to integrate this. We do have delta CPM, which is -5 joule per mole Kelvin. We just need to integrate dt over T. The integral of dt over T is the natural logarithm of T. Therefore, we have this natural logarithm here, and we do the calculation, we get -115.48. Compare this number at 55 degrees Celsius and this number at 25 degrees Celsius. They're awfully close to each other. In PChem, again, we always assume that the enthalpy of reaction and the entropy of reaction at room temperature can be used at some other temperatures, as long as the other temperature is not too far away from the room temperature. Chapter 5, Helmholtz energy and Gibbs energy. Section 5.1, Definitions of Helmholtz energy and Gibbs energy. The Helmholtz free energy, or simply Helmholtz energy, is equal to the internal energy minus Ts. The Gibbs free energy is equal to enthalpy minus Ts. U and H differ by PV. H is PV plus U, therefore G and A also differ by PV. G is A plus PV. At constant temperature, the differential of the product of Ts is just TdS, and we know the Clausius inequality is this: TdS is greater than or equal to dQ. Using these two pieces of information, we can prove dA is less than or equal to dW. This is just because A is U minus Ts and du is dQ plus dW. And we can rearrange these three terms. We have dW and then minus TdS minus dQ. And again, TdS is greater than dQ or equal to dQ. So this value has to be non-negative. And dW minus a non-negative value is less than or equal to dW. We can also integrate this dA and this dW. We get delta A is less than or equal to W. That means the change of A, the change of the Helmholtz free energy, serves as the lower limit of W. At constant temperature, the increase in the Helmholtz energy of the system should be no more than the work done to the system. For example, if work of 5 joules is done to the system at constant temperature, then the Helmholtz energy of the system can increase by no more than 5 joules. At constant temperature, the decrease in the Helmholtz energy of the system should be no less than the work done by the system. If work of 5 joules is done by a system, that means this W is -5 joules. Delta A should be less than or equal to -5 joule. That means it's going to be more negative than -5. And in this case, the Helmholtz energy of the system decreases by no less than 5 joules. In both cases, delta A is the lower limit for work. Again, delta A is less than or equal to W when temperature is held constant. Because A is a state function, we know the cyclic integral of dA is 0. And then we can evaluate the cyclic integral of both sides. We have this cyclic integral of W, dW, greater than or equal to 0. After the system undergoes a cyclic process and returns to its original state. And because the integral of du is the cyclic integral of du is always 0, because u is a state function and the cyclic integral of any state function is 0, we have the cyclic integral of dq is equal to negative cyclic integral of dw, and that's always less than 0 or equal to 0. At constant temperature, we have dA is less than or equal to dW, delta A is less than or equal to W. The change of A serves as the lower limit for work. Under constant temperature and volume condition, we have dW expansion equals 0, because when the volume is held constant, dV is 0, so dW expansion is simply 0. Now we just divide dW into two parts: expansion work, non-expansion work. If the condition is constant temperature and constant volume, dW expansion is 0, and because dA is less than or equal to dW, under constant temperature and volume condition, we can write dA is less than or equal to dW non-expansion, and therefore delta A is less than or equal to W non-expansion. The change of A serves as the lower limit of non-expansion work. For example, electric work is non-expansion work under the constant temperature and volume condition. Now we can prove this under constant temperature and pressure condition. The change of G serves as the lower limit of non-expansion work. Here's the derivation. If the temperature and pressure are both held constant, dG is dH minus TdS. It's just because G is defined to be H minus Ts. H is U plus PV. Du is dQ plus dW. dPV is actually PdV plus VdP in general, but in this case pressure is constant, so dPV is PdV. And since temperature is constant, dTs is TDS, and then we have this many terms. We can put dQ and TDS together over here, and then we have dW and PdV. And over here we just swap the sign. It's negative TDS minus dQ, and dW is non-expansion work plus expansion work, and then we have PdV. Now this expansion work is negative PdV, so negative PdV and PdV cancel. We have this three terms. If you look at the this number one term, number two term, TDS is always greater than or equal to dQ based on Clausius inequality. So over here we have a non-negative number, and this with this negative sign, we know the sum of these terms should be less than or equal to dW non-expansion. Again, this is just because TDS is greater than dQ for irreversible process. TDS is equal to dQ for reversible processes. Now we just proved dG is less than or equal to dW non-expansion. The equal sign holds when the process is a reversible process. We can then integrate both sides. Delta G is less than or equal to non-expansion work under constant temperature and pressure condition. The change of G now serves as the lower limit of non-expansion work when temperature and pressure are constant. At constant temperature and pressure, delta G is less than or equal to non-expansion work. Therefore, the increase in the Gibbs energy of the system should be no more than the non-expansion work done to the system. Here's an example. If the electric work of 5 joules is done to a system at constant temperature and pressure, the Gibbs energy of the system increases by no more than 5 joules. At constant temperature and pressure condition, the decrease of the Gibbs energy of the system should be no less than the non-expansion work done by the system. So if the system does electric work of 5 joules under constant temperature and pressure condition, the Gibbs energy of the system decreases by no more than 5 joules. For example, it can be 6 joules. Therefore, under constant TP condition, electric work of more than 5 joules must be done to a cell phone battery to increase its Gibbs energy by 5 joules. The battery can provide electric work of less than 5 joules when its Gibbs energy decreases by 5 joules. This is just because electric energy is partially wasted in the form of heat when you are charging or using the battery. Either way, part of the electric energy is wasted. After a cyclic process of charging and discharging, delta G should be 0, so the Gibbs energy of your cell phone battery should be unchanged after a cyclic process, because G is a state function. But W, non-expansion, this is non-expansion work, overall should be greater than 0 or equal to 0. The equal sign holds only for reversible processes. For irreversible processes, the non-expansion work is greater than 0, and then Q of the Q of the system should be less than 0. Heat is released to the surroundings. That increases the entropy of the surroundings, and overall it increases the entropy of the universe. So it's a irreversible process. Again, in an irreversible process, part of the electric work is wasted in the form of heat that's released to the surroundings, and that's why the battery gets warmer no matter you're charging it or using it. In summary, A and G are introduced in thermodynamics because delta A or delta G can serve as the lower limit for non-expansion work, such as electric work, under constant TV or constant TP conditions. Because chemical reactions and physical changes take place more often under constant TP conditions for safety and for convenience, so we often look at delta G. We often study delta G, calculate delta G as the lower limit for non-expansion work. Chapter 5. Helmholtz energy and Gibbs energy. Section 5.2. U, H, A, and G depend on P, V, T, S. In thermodynamics, there are many thermodynamic functions. Among those, U, H, G, and A are very important. They denote the internal energy, enthalpy, Gibbs energy, and Helmholtz energy of the system. U, H, G, and A depend on pressure, volume, temperature, and entropy. P, V, T, S. And we have equations that connect U, H, A, and G. U is A plus Ts, H is U plus PV, G is H minus Ts, and A is G minus PV. There are 4 other equations that connect U, H, G, and A. Among all these thermodynamic functions, only pressure and temperature are intensive properties that do not depend on the amount of the substance. U, H, G, A, V, and S are extensive properties that are proportional to the amount of the substance. The SI units for U, H, G, and A are all joules, and 1 joule is 1 kilogram meter squared over second squared. U, H, A, and G depend on PV and TS, and you can see all those equations over there. The SI units of PV, TS are Pascal for pressure, cubic meter for volume, Kelvin for temperature, finally Joule per Kelvin for entropy. And also you can replace this Joule with 1 kilogram meter squared over second squared. It's just a little bit too tedious. 1 Pascal is 1 Newton per square meter. Well, it's just remember pressure is force over area. And 1 Newton is 1 kilogram times meter over second squared. You can just memorize this by remembering force is equal to mass multiplied by acceleration. And also 1 Pascal can be written in terms of kilogram meter a second, because we can replace this Newton here with kilogram meter per second squared. And therefore 1 Pascal is 1 kilogram times meter to the power of -1 second to the power of -2. And also this can be written as 1 joule over cubic meter. Well, again, it's just because 1 Newton times 1 meter is a joule. So that's why. Now we have 1 Pascal multiplied by 1 cubic meter equals 1 joule. If we multiply P and V, the product PV has a unit of the unit of energy. Therefore, the SI unit of PV is joule. Same for TS. The product of temperature and entropy should be in the unit of energy, and the SI unit of the product, TS, is also joule. Again, we need to memorize all these equations that connect the four thermodynamic functions U, H, A, and G. For a fixed amount of a pure substance, its internal energy U depends on PV, T, and S, not N, because if you have a fixed amount, N is constant. Out of pressure, volume, temperature, and entropy, only two are independent variables, and you can pick any two. For example, you can view the internal energy as a function of PV, and you can write du is delta U over delta P times dP plus delta U over delta V times dV. This is correct, but not very useful in thermodynamics, because this partial derivatives do not really have a clear physical meaning. Also, we can write U is a function of PT. Similarly, du is delta U over delta P times dP plus delta U over delta T times dt. And pay attention to the subscripts. This equation is also correct, but not very useful. The reason is, yes, U is a function of two independent variables. What about the two other variables? The two other variables depend on the two independent variables of your choice. But if you choose PV as the independent variables or PT as the independent variables, the equations you get are correct, but not very useful. Very often we write U as a function of temperature and volume. Sometimes we write U as a function of entropy and volume. If we select temperature and volume as the independent variables for the internal energy, and we can write du is delta V over delta U over delta V times dV plus delta U over delta T times dt. And this term, delta U over delta V on a constant temperature, we can later prove this to be T times delta P over delta T minus P. And this can be easily measured. And also it can be derived for different substances. That's why it's convenient. What about delta U over delta T on a constant volume condition? On a constant volume condition, work is 0, so delta U is just delta Q. Delta Q over delta T is just C. So that's why we have C sub V here. Again, this is convenient when we view U as a function of temperature and volume, because we have something with physical meaning, easily measurable in front of dV, and this C sub V is also easily measurable, and it can be determined for the substance fairly easily, and then we can study how U depends on V and T. Actually, we can express U as a function of entropy and volume as well. This is because du is dq plus dw. For a reversible process, du is dq reversible plus dw reversible. And remember, the definition of entropy in thermodynamics is indirect. Its ds is equal to dq reversible over t. Therefore, dq reversible is tds. What about dw reversible? It's simply negative p external dv, and since it's reversible, p external can be replaced by p. So now du is just tds minus pdv. This is a really simple expression, and it contains pv, t, and s. When do we use the first equation, u as a function of tv, or the second equation, u as a function of entropy and v? Really depends on which of these equations is more convenient to use under the specific conditions. Later you will see. We will use this equation and this equation in many derivations and numerical calculations. And because du is equal to tds minus pdv, and also we have the definition of h, a, and g. H is u plus pv, a is u minus ts, g is h minus ts. We can do some simple derivations here. dH is just du plus PV, which is simply TdS minus PdV. This part is du, this part is dPV, and we cancel negative PdV and positive PdV. dH is TdS plus VdP. dA is du minus dTs. This part is du, TdS minus PdV is du, and then minus TdS minus SDT. Therefore, dA is negative SDT minus PdV. And also, we have this dG over here. dG is dH minus TS. dH is TdS plus VdP right here. And we can expand TdS using the product rule in calculus. And finally, dG is negative SDT plus VdP. U, H, A, and G all depend on PVTS. For a fixed amount of a pure substance, only 2 out of these 4 variables, PVTS, may be chosen to be the independent variables. You can choose any 2, but sometimes it's just more convenient to choose. For example, if you have G, if you look at G, it's probably better to express G as a function of temperature and pressure. It's just more convenient. And you know how G depends on temperature. It's just negative entropy. And you know how G depends on pressure. It's just volume. So it's just convenient. So in summary, we have these 4 exact differentials. It can tell you it's often more convenient to write U as a function of S and V, H as a function of S and P, A as a function of TV, and G as a function of TP. In addition, we use these 2 equations for U and H. It's also very convenient to express U as a function of Vt and H as a function of Pt. Again, one reason is it's easy to measure the change of temperature, volume, and pressure. There's another reason. Delta U over delta V on the constant temperature can be expressed in this form. And you look at this, it involves only pressure, temperature, and volume. All 3 quantities can be easily measured. Delta H over delta P is V minus T times delta V over delta T on a constant pressure condition. Again, this can be measured experimentally easily, and it can be derived for other substances as well. So it's just convenient to use these expressions for du and dH as well. Now, what about this delta U over delta T on a constant volume condition? It's just isochronic heat capacity. Delta H over delta T under constant baric condition is just the isobaric heat capacity. So again, it's just that we choose the independent variables depending on whether it's convenient for us to use to achieve our goals in the calculations or derivations. Chapter 5, Helmholtz energy and Gibbs energy. Section 5.3, Maxwell relations. There are 4 Maxwell relations, very useful in thermodynamics. Those are the 4 Maxwell relations that connect pressure, volume, temperature, and entropy together. Now let's look at the first equation. Delta T over delta V under constant entropy condition is equal to negative delta P over delta S under constant volume condition. So how do we actually memorize this equation before we can even prove it? Well, it's just if you notice this, the unit of delta T times delta S is the unit of energy. The unit of delta P times delta V is the unit of energy. So you always have TS on the opposite side and PV on the opposite side. Alright? And also when you do T over V, P over S, pay attention to the subscripts. This S goes here, this V goes here. Now the second Maxwell relation, delta T over delta P on the constant entropy condition, is equal to delta V over delta S under constant pressure condition. The first 2 equations are less useful than the bottom two equations, because it's usually more difficult to hold entropy constant. Usually we can think of adiabatic reversible in which the entropy is constant. However, it's just a lot easier to hold temperature constant or to hold volume and pressure constant. So you have isobaric here, isochoric here, isothermal here, isothermal here. Alright? So now let's look at the bottom two equations, which are more useful. Delta S over delta V under constant temperature condition is delta P over delta T under constant volume condition. Negative delta S over delta P under constant temperature condition is delta V over delta T under constant pressure condition. Not only it's easier to have temperature constant, volume constant, pressure constant, these two equations also tell us how entropy changes with volume, how entropy changes with pressure. So this way we can derive or calculate the change of entropy more easily using these two equations, because if you look at the right hand side, I mean, this is pretty easy to measure or pretty easy to derive. Same here. The Maxwell relations are useful again because they allow us to predict the last tangible entropy change of a system by measuring the more tangible changes of PV and T. For example, if you can somehow hold the volume constant, you just need to measure the pressure change and temperature change. Do a division, you get this. Before deriving the four Maxwell relations in thermodynamics, let's review some calculus. And the derivation of the Maxwell relations is based on calculus. Here's the calculus. If z is a function of x and y, we can write dz is equal to a function times dx plus another function times dy, and this is f function, this is g function. If the value of z solely depends on the values of x and y, z is considered a state function that depends on the state of z. That's simply the values of x and y. Alright, so if you have values of x and y, the value of z is fixed. And if z is indeed a state function of x and y, then actually there is a relationship between this f in front of dx and this g in front of dy. So again, when z is a state function of x and y, so what does that mean? That means if you're given the values of x and y, the value of z is fixed. Alright? And most mathematical functions have that feature. You can write dz is equal to a function times dx and another function times dy, and these two functions are denoted by f and g, f in front of dx and g in front of dy. Now if x is held constant, dz is simply just g dy. When y is held constant, dz is just f dx. Alright, so these two equations are true when one of the two variables is held constant. Since z is a state function of x and y, we can calculate the change of z when xy changes to x plus dx and y plus dy via two different routes. So again, just imagine, we go from the initial state, which is x and y, to the final state, which is x plus dx and y plus dy. We can go from here to here via two different pathways or two different routes. The first route, we change x first and then change y. In the second route, we change y first and then change x. In the first route, we look at the change of z. The change of z is the change of z in the first step and then the second step. In the first step, we have f xy times dxy. In the first step, y is held constant. Only x changes, so we have this. Now in the second step, only y changes. Alright, only y changes from y to y plus dy. And over here, this is x plus dx, this is x plus dx. There's no change, so we have this equation. Now let's look at the second route. In the first step, we change y, and in the second step, we change x. So we have this equation. And because z is the state function of x and y, So this expression should be equal to this expression. It does not matter which route you decide to take, dz is dz. So this sum is equal to this sum, and then we copy this expression to the left hand side, we copy this expression to the right hand side. Alright, now you can see there's dx, dy, dy, dx. Let's move all the dx to one side, all the dy to the other side. I see this dx here, I see this dx here. So if we combine the dx term together, we get this. I see dy here, I see dy here. We're going to combine this too. So we have this equation. Alright, now both sides divided by dx and then divided by dy. Alright, the left hand side divided by dx, this dx disappears, and then divided by dy. This side also divided by dx and then divided by dy. So we have this equation. And actually, what is this? This is actually, if you look at this, this is just simply the first derivative of y with a derivative of f, okay, with respect to y. So it's just this. It's the first derivative of function f with respect to y. When x is held constant, there's no change here. And look, we have on the bottom dy, that's the change of y. On top, that's the change of f when y changes from y to y plus dy. So this left side of this equation is the first derivative of function f with respect to y when x is held constant. Now let's look at the right hand side. Well, on the bottom you have the change of x, on top you have the change of g when x changes from x to x plus dx. And if you still remember this single variable calculus, it's just dg over dx. If you remember multi-variable calculus, we're holding y constant. Alright, so we put y here. This is just delta g over delta x when y is held constant. Now we see the relationship between f and g. So delta f over delta y should be equal to delta g over delta x. And also pay attention to these two subscripts. When we take the first derivative of y with f with respect to y, you need to hold x constant. When you do delta g over delta x, you need to hold y constant. Again, when z is a state function of x and y, there is a relationship between this f and g in this equation. dz is f dx plus g dy. And the relationship is this: delta f over delta y is equal to delta g over delta x. And don't forget the physical meaning of f. F is just delta z over delta x when y is constant. And g is delta z over delta y when x is constant, right? When x is constant, this term disappears. And then g is just dz over dy when x is constant. So this is g. This is f. And because delta f over delta y is delta g over delta x, we have this delta f over delta y is equal to delta g over delta x. Again, this is just f. F is how z depends on x when y is constant. And this part is g. G is how z depends on y when x is constant. Alright, so again, if z is a state function of x and y, if we can determine the value of z given the values of x and y, then we need to have this relationship between f and g. Here's one example. dz is 2y dx plus 2x dy. Is z a state function? So what we're going to do is we're going to take the first derivative of this function in front of dx. This 2y is in front of dx. We take its first derivative with respect to y. We get 2. We then take the first derivative of the function in front of dy with respect to x. We get 2. And this 2 is equal to this 2. Yes, z is a state function. And actually z is simply 2xy plus a constant, any constant. It can be 3.5 or some other numbers. You can just verify this. You can take the differential of this. You'll get 2y dx plus 2x dy. Now another example problem, 5.3.2. So we have dz is 2xy dx plus 2xy dy. Let's see the state function of x and y. In this case, the answer is no. The first derivative of this 2xy in front of dx, we take its first derivative with respect to y, we get 2x. Now we take the first derivative here in front of dy. With respect to x, we get 2y. 2x and 2y are different. This is not a state function. So given the value of x and y, you're not going to be able to determine the value of z. And there's no way to integrate both sides to get a function for z. No way. Again, when z is a state function of x and y, dz can be written as f dx plus g dy. F and g are functions of x and y. And there's a relationship between f and g over here. Delta f over delta y should be equal to delta g over delta x. Another example, if dz is just 2x dy, is z a state function of x and y? The answer is no, because we don't have any dx term, so f is 0, so we have this equals 0, and then delta g over delta x, 2x over delta x is just 2. 0 and 2 are different. This equation does not hold. Therefore, this case, z is not a state function of x and y. Looks simple, but there's no way to even get a function form for z. You cannot express z as a function of x and y. No way. Now this looks extremely complicated. In front of dx we have this, in front of dy we have this. Really complicated. And then is z a state function of x and y? Surprisingly, the answer is yes. We can verify this. We just take the first derivative of this function in front of dx with respect to y. The result is 2y over x plus 2x times cosine y. So you need to be able to take the first derivative of y squared. It becomes 2y. The first derivative of sine y is cosine y. What about x? X is treated as a constant. Now let's do this part. We're going to take the first derivative of this with respect to x. We copy 2y here. It's treated as a constant. The derivative of ln x is 1 over x. The derivative of x squared is 2x. Now if you compare these two expressions, they are exactly the same. Therefore, z is a state function of x and y, and actually z is y squared times ln x plus x squared times sin y plus a constant. You can easily verify this. Just take the first derivative of z with respect to x. You get y squared over x plus 2x sine y. It's right here. You can take dz over dy, assuming x is constant, and then you get 2y ln x, which is here, going from here to here, and then you get x squared times cosine y, you get here. Alright, now we can say the second derivative of z with respect to x and then y is equal to its second derivative with respect to y first and then x. So if you have a state function z of x and y, you can take its second derivative in two different orders. You can take the second derivative with respect to x and then y, or y then x. The result should be the same. In this numerical, in this example problem, this is the second derivative. This is the second derivative. We're just getting the second derivative in a different way. Now get back to thermodynamics. Because u, h, a, g are state functions, and then we can use the differential form of u, h, and g to get the four Maxwell relations. So du is TdS minus PdV. So T is delta U over delta S on a constant volume condition. Negative P is delta U over delta V on a constant entropy condition. Alright, so really we have this T in front of ds and negative P in front of dV. T is the first derivative of U with respect to S. Negative P is the first derivative of U with respect to V. So we have these two equations here. And then we're going to look at the Maxwell relation. We're going to assume the second derivative of U with respect to S and V, and its second derivative with respect to V and S are exactly the same. And on top, this part is simply temperature. On top here, this is negative P, and we have this equation. This is our first Maxwell relation. Now dH is TdS plus VdP. This T is dH over ds if pressure is constant, so we have this equation. And V is dH over dP if entropy is constant, so we have this equation. Now we get the second Maxwell relation by taking the second derivative of H in two different orders, S first and then P first and then S. Left is equal to right. On top over here, delta H over delta S, constant pressure, that's temperature. Delta H over delta P, constant entropy, that's volume. Now we have our second Maxwell relations. These two Maxwell relations, they are correct, but they are rarely used in thermodynamics. It's just hard to hold the entropy constant in an experiment. So here and here. The other two Maxwell relations derived from dA and dG are much more useful. So dA is negative S dt minus PdV, dG is negative S dt plus VdP. From these two equations, we get two more Maxwell relations. Delta S over delta V is delta P over delta T. Negative delta S over delta P is delta V over delta T. These two are really useful because by measuring this, we can get how entropy changes with volume. By measuring this, we can get how entropy changes with pressure. Now let's prove the last two Maxwell relations. Given dA is equal to negative S dt minus PdV, we have negative S is dA over dt on the constant volume condition right here. And then over here, negative P is dA over dV if dt is 0. So we have this equation. We have these two equations already, and then we will take the second derivative of A with respect to T and then V, or V and then T. Either way, the result should be the same. Delta A over delta T on the constant volume condition. Just copy this here, it's negative entropy. Delta A over delta V on the constant temperature condition, copy this here, it's negative P. So we get this Maxwell relation. And of course, you can just remove the negative sign on both sides. It's easy to determine delta P over delta T on the constant volume condition. For ideal gas, it's just nR over V. So it's really easy. And then we get the analytical form for this. For ideal gas, for a real gas, we can still evaluate this, right? Let's use Van der Waals equation. Delta P over delta T is just nR over V minus NB, right? And even for solids and liquids, delta P over delta T on a constant volume condition is simply alpha over kappa. Both alpha and kappa are constants, so we get a constant for this. So it's really good to have this equation to calculate the entropy change given the volume change. Here's some mathematical derivation. You know, if you have an ideal gas, delta P over delta T is just nR over V because pressure is just nRT over V. And when temperature is held constant for this ideal gas, we have just ds over dV is nR over V. So ds is nR V times dV. We have only one variable on the left hand side, only one variable on the right hand side. You can just integrate both sides. And then delta S is equal to nR times the natural logarithm of V final divided by V initial. and if this volume of the ideal gas is doubled at constant temperature, we get this equation. The entropy change is nRln2. The molar entropy change is simply just R times Ln2. And then we can just plug in R, 8.314 times Ln2, we get 5.76 joule per mole. Alright, when, I'm sorry, there's a mistake here, it's joule per mole Kelvin. And when the volume of this ideal gas is doubled in isothermal process. Now let's derive the last Maxwell relation. Given this equation, dg is negative s dt plus vdp. Negative s is just how g depends on temperature when pressure is constant. Alright, so negative s is delta g over delta t when pressure is constant, right here. V is just delta g over delta p when temperature is constant. Alright, so we have the Maxwell relation. We take the second derivative of g with respect to t and then p, or p and then t. They're the same, so we have this equation. Delta G over delta T on a constant pressure condition is negative entropy. Delta G over delta P on a constant temperature condition is just volume. So going from here to here, it's pretty simple. We just replace delta G over delta T with negative S, delta G over delta P with V. So we have this equation. And it's pretty easy to determine delta V over delta T under constant pressure condition. For an ideal gas, it's really easy to derive. For a real gas, well, it's close to nR over P. For a solid or liquid, this is simply alpha times V, and alpha is just a constant. So it's easy to determine this and then determine this, and then we know how entropy depends on pressure. Now let's look at the example of an ideal gas. Let's say the pressure of an ideal gas is doubled under constant temperature condition. We'll just use this equation, and for ideal gas, delta V over delta T is nR over P. So we have this is equal to negative nR over P, and then we can integrate both sides of this equation, and we get entropy change is equal to negative nR times the natural logarithm of P final over P initial. It's negative nR Ln2. The molar entropy change is negative R Ln2. It's negative 5.76 joule per mole per Kelvin. Sorry about the mistake here. It should be joule per mole and then per Kelvin. When the pressure doubles in isothermal process, entropy decreases. And over here, in this example, because it's isothermal, notice that the volume of this gas is halved. Alright, so you can also use the volume change to calculate the entropy change. It's also going to be negative 5.76 joule per mole per Kelvin. And using the last two Maxwell relations, these two, very useful, we can now derive how U depends on volume and how H depends on pressure under constant temperature condition. So it's very useful. Let's do it. Delta U over delta V under constant temperature condition. du is TdS minus PdV. So delta U is T delta S minus P delta V. Alright, it's just notation. Alright, we have this equation here. We're going to separate these two terms. On the left, T is constant, take T out. It's delta S over delta V under constant temperature condition. On the right hand side, you just have negative P delta V over delta V. It's just negative P. How do we go from here to here? Well, it's just Maxwell relation. Delta S over delta V under constant temperature is equal to delta P over delta T under constant volume condition. It's right here. It's right here. Now let's derive delta H over delta P under constant temperature condition. dH is TdS plus VdP. So we have this. And now this delta P over delta P cancel. So you have V here. You have T. Take T out because T is held constant. T. Delta S over delta P. Copy this. Constant temperature. Copy this. Delta S over delta P under constant temperature condition. What is that? It's right here. It's negative delta V over delta T under constant pressure condition. So we get this. Alright, this is how we derive delta U over delta V and delta H over delta P when temperature is held constant. This too can be expressed as this expression in terms of PVT and this expression in terms of PVT. It's just convenient to measure this or even derive this to get delta U over delta V and delta H over delta P under constant temperature condition. So again, we do a lot of derivations just for the convenience of calculations, derivations, or experimental measurement. Alright, we cannot do this directly, so we use mathematics to prove this is equal to this, and then we determine this either experimentally or mathematically. Same here. It's very hard to determine delta H over delta P under constant temperature condition, whether you do experiments or theoretical stuff. But over here it's easy. Experimentally or analytically, you can easily determine delta V over delta T under constant pressure condition. For ideal gas, it's simply nR over P. For solid or liquid, it's simply V times alpha. For a real gas, we can make approximations. This is awfully close to nR over P, etc. Again, for an ideal gas, now we can prove that U and H only depends on temperature. Delta U over delta V on a constant temperature condition, it's this, T times delta P over delta T minus P. Delta P over delta T is nR over V, and we have nRT over V, that's its pressure, minus pressure, that's 0. Delta H over delta P, well, it's just volume minus T times delta V over delta T on a constant barrier condition. And over here, delta V over delta T on a constant pressure condition is simply nR over P. So we have V minus nRT divided by P. This part is also V. We get 0 in the end. Alright, so it's now possible to derive delta U over delta V on a constant temperature condition and delta H over delta P on a constant temperature condition. This equation and this equation hold true for all substances. It's just for ideal gas, this part cancel, you get 0. For ideal gas, this is canceled, you get 0. Alright. For a real gas, these two are non-zero. For solid or liquid, these two are also non-zero. But now with these equations, it's pretty easy to determine these two terms, either experimentally or analytically. Chapter 5, Helmholtz energy and Gibbs energy. Section 5.4, U and A depend on T and V. U can be expressed as a function of temperature and volume. So du can be written as delta U over delta T times dt plus delta U over delta V times dV. Delta U over delta T under constant volume condition is simply C sub V, the isochloric heat capacity. Delta U over delta V on a constant temperature condition can be derived using one of the four Maxwell relations. So over here, delta U over delta V is T delta S minus P delta V over delta V on a constant temperature condition. The first term is T times delta S over delta V here. The second term is negative P. Delta S over delta V is delta P over delta T. Pay attention to the subscripts. This is just one of the Maxwell relations. And then we can use this to obtain delta U over delta V on a constant temperature condition. For van der Waals gas, U depends on volume when the temperature is held constant. The van der Waals equation is this: P is nRT over V minus NB minus N squared over V squared. A and B are van der Waals parameters. The variation of U with V is therefore this derivation here, T times delta P over delta T on a constant volume condition minus P. And this is simply nR over V minus NB. Minus P is replaced by minus this whole thing. And then in the end, the first term and the second term cancel. We have N squared over V squared. So if both the temperature and volume of a van der Waals gas change, we need to look at this dt term and dv term. delta U is the integral of this CV dt, and also the integral of this an squared over v squared dv. Again, this part is how u changes with v. We integrate this integral, we get cv times delta t. We integrate this part, it's just an squared times 1 over v final minus 1 over v initial. And then there's a negative sign in the front because the integral of 1 over v squared is negative 1 over v. In this derivation, Cv is assumed to be independent of temperature. It's mostly true because the isochloric heat capacity is approximately constant within a moderate temperature range. But for some molecules with very low vibrational frequencies, this Cv may depend on temperature. It's just because when you have many low frequency vibrational modes, the molecules can occupy some higher excited vibrational states at even room temperature. Now get back to the equation for delta U. For van der Waals gas, the internal energy depends on both the temperature and the volume of the gas. How does U depends on temperature? The dependence is C sub V. How does U depends on volume? The dependence is an squared over v squared. For ideal gas, we know A is 0. This van der Waals parameter A is 0. Delta U is simply the integral of Cv dt. U only depends on temperature. What about solids and liquids? Well, still we use this equation. It comes from this expression of delta U, which is T delta S minus P delta V. And then we're going to use this one of the Maxwell relations. Delta S over delta V on a constant temperature is delta P over delta T on a constant volume condition. So that's why you have this. And we can prove this delta P over delta T on a constant volume condition is just alpha divided by kappa for all substances. We actually need to use the triple product rule and reciprocal rule in calculus. Alright, so we can actually rewrite delta P over delta T as delta V over delta T over negative delta V over delta P. On top you have V times alpha, on the bottom you have V times kappa. Therefore the result is T times alpha over kappa minus P. This equation holds for all substances, including gases, liquids, and solids. It's just when you use this for liquids and solids, it's particularly convenient because alpha and kappa are just constants. You look up the values of alpha and kappa for those liquids and solids, plug those in. How do we get delta U? Delta U is just the integral of Cv dt again plus the integral of delta U over delta V times dV. But over here, if you have solids and liquids, you can rewrite this as T times alpha over kappa minus P. So it's going to be roughly this. If you know the temperature, pressure, and the values of alpha and kappa, just do the calculation. For most solids and liquids, T times alpha over kappa is much larger than P, that we can even neglect the pressure. Why is that? Here's an example. If you have copper at 300 Kelvin and 1 bar condition, we have alpha, we have kappa, and we can compute T times alpha over kappa. The result is 21,000. So this term is 21,000 larger than this term. Of course, we can then neglect the smaller, much smaller term over here. Again, when you do addition or subtraction between two numbers, you can always neglect the much smaller number. So again, for most liquids and solids, we first express delta U over delta V in this format, T times alpha over kappa minus P. And usually we can ignore this P because this P is much smaller than T times alpha over kappa, so it's going to be just T times alpha over kappa, so right here. And we have this expression. And how would you actually obtain the numerical value of U? Well, just plug in the value of CVM, T initial, T final, plug in the volume change, plug in the values of alpha and kappa you looked up, plug in the temperature. You get delta U. Again, U, H, A, and G all depend on pressure, volume, temperature, and entropy. It's just only two variables or independent variables. You can pick any two out of PVTS. It's up to you. For A, the Helmholtz energy, usually we say A is a function of temperature and volume for convenience. dA is du minus Ts. du is TdS minus PdV. The differential of Ts is TdS plus SdT. We cancel TdS and negative TdS. We get negative SdT minus PdV. Well, from this equation, you can see the change of A depends on the change of T and the change of V. A is a function of T and V. And also, we see the dependence, I think, are both negative. So, dA over dt is negative entropy when volume is constant. Entropy is always positive, so dA over dt is always negative. Over here, dA over dV is negative P when temperature is constant. So when temperature is constant, dA over dV is always negative because pressure is always negative. Mathematically, it's this: delta A over delta T under constant volume condition is negative entropy. It's always negative. Delta A over delta V under constant temperature condition is negative P, which is always negative. Also, we can analyze the change of A quantitatively. If volume is constant, the A only depends on temperature. If temperature is constant, A only depends on volume. So when volume is constant, delta A is negative integral S dt. Alright? And when temperature is constant, delta A is just negative integral P dV. Usually it's easy to derive this for a gas, for a liquid, or a solid. It's pretty easy to do this. This one, it really depends. I mean, if you have a small temperature range, entropy can be viewed as a constant within a very small temperature range, and then you can compute delta A directly. However, even if you have a moderate temperature range, because entropy depends on temperature, and somehow you need to kind of express entropy in terms of temperature, and you need to integrate a function of temperature over here when temperature changes. Alright, A is U minus Ts, therefore dA is negative S dt minus PdV. Here's the one-line definition. Alright, so A always decreases if T increases and V increases because of this equation. You can see negative S is how A depends on T, negative P is how A depends on volume. Here's one example problem, 5.4.1. Which of the following two ideal gases at 300 Kelvin has a larger Helmholtz energy A? And you can calculate the difference. And what's the physical meaning of this difference? Two different ideal gases. One has a 10 liter volume, 10 bar pressure. The other 1 liter volume, 100 bar pressure. They have the same temperature. At constant temperature, as volume increases, the Helmholtz energy decreases. And therefore, this one has a larger volume and lower Helmholtz energy. This one, smaller volume, larger Helmholtz energy. Alright? And dA is negative SdT minus PdV. The temperature is constant. I think I mentioned 300 Kelvin somewhere. So both gases are at 300 Kelvin. So you don't have to worry about dT. dA is negative PdV. And now we're calculating the difference in A between these two gases. Alright, so this is the Roman numeral 1, Roman numeral 2. This is just the difference. Alright, this is delta A is number 2 gas minus number 1 gas. We integrate negative PdV. Both are ideal gases. P is nRT over V. We integrate this, we get negative nRT times the natural logarithm of V. We plug in the volume of gas 2, the volume of gas 1, we get some expression. PV is you just plug in the numbers. PV is 100 bar liter, and you plug in this L10, and we get the result. Okay, I think I might have made a mistake here. I think PV is 100 bar liter, and then multiplied by Ln10, it should be 230 bar liters. Sorry about that. But again, we have this delta A. That's the difference in A between these two different gases. What's the physical meaning of this difference? Well, it's just the maximum amount of work ideal gas can do. I think it should be 23 kilojoule when it changes from 1 liter 100 bars to 10 liters 10 bars under the constant temperature condition. Conversely, the minimum amount of work needed to change an ideal gas from 10 liters to 10 liters 10 bars to 1 liter 100 bars should be I think it's 23 kilojoule. Again, this PV is actually 100 bar liters. That's 100 bar liters. No matter you use these two numbers or these two numbers, PV is 100 bar liters. Ln10 is 2.3. So put 2.3 times 100 should be 230. And 230 bar liters should be 23 kilojoule. Sorry about the mistake. Chapter 5. Helmholtz energy and Gibbs energy. Section 5.5. H and G depend on T and P. The internal energy, enthalpy, Helmholtz energy, and Gibbs energy of a system all depend on pressure, volume, temperature, and entropy. But out of this P, V, T, and S, only two can be chosen as the independent variables for a fixed amount of pure substance. It's often convenient to treat H and G as functions of T and P. Let's look at H first. dH can be expressed as delta H over delta T times dt plus delta H over delta P times dP. The reason we do this is because delta H over delta T under constant pressure condition is Cp. Delta H under constant pressure condition is simply Q sub P. We have proven that. And over here, delta H over delta P under constant temperature condition can be written as V minus T delta V over delta T. We can prove this using one of the Maxwell relations. Now for a van der Waals gas, pressure is this, nRT over V minus Mb, and then minus An squared over V squared. So we have this equation. Now we're going to use this equation to derive delta V over delta T and plug it in. Given this equation, we can simply take the first derivatives of both sides relative to volume. So we're going to take this nR delta T over delta V over here, and then on this side we're going to take the first derivative with respect to volume. So we'll do this part first. P does not depend on volume because we have a constant pressure condition. We'll just take this derivative to a negative 2 An squared over V cubed, and then multiply by V minus Mb, go here, and then we copy this here, and then we take the first derivative of V minus Mb, which is just 1. Again, this is just the product rule. The differential of Fg is the differential of F times G plus the differential of G times F. We can just clean this up. This P is nRT over V minus Mb minus An squared V squared. So this 2, the sum of this 2 is simply nRT over V minus Mb. This one, we just put this on top. That's how we got here. Delta H over delta P under constant temperature condition is simply V minus T times this delta V over delta T. Alright, delta V over delta T is the reciprocal of this delta T over delta V. So that's why we need to kind of do some algebra and then write delta H over delta P in this form. Really complicated. You have something on the bottom over here as the result of subtraction. That's why we cannot separate this easily. So again, if you have something like 1 over A minus B, there's no easy way to separate A from B or from B from A. But we're going to use some mathematical trick. We're going to allow A approach 0 and compute this delta H over delta P. We are going to allow B approach 0 and then evaluate delta H over delta P, and then we sum up the two results. So when A approaches 0, that's easier because this A is 0, this part disappears, and you simply get T over negative T over V minus MB. So really it's just V minus MB, and then you have V minus parenthesis V minus MB, and that's just MB. So really simple. If A approaches 0, delta H over delta P is simply a MB. And MB has a physical meaning. It's just the space taken up by the gas particles. Or you can say just the size of one particle multiplied by the number of particles. Alright, so that's the physical meaning of this. Now let's say B is 0, and then we delete this MB term, we delete this MB term. However, if you look at the denominator, it's still a subtraction over here. How do we simplify this? Well, we're just write this in this form. Alright, and I don't know if you have heard this or remember this. 1 over 1 minus delta is approximately 1 plus delta. Actually, it's just from the truncated version of the Taylor expansion. And we have this, and then we have this. Alright, so 1 minus delta is if you have 1 over 1 minus delta, you get 1 plus delta. Alright, and then we evaluate this, we got this term that contains only A. So if there's no B, delta H over delta P is negative. There's no A, delta H over delta P is positive. Now when both A and B play a role, we have this expression. Alright, this expression. We have MB, we have negative 2AN over RT, we put them together. N is the common factor, so it's just B minus 2A over RT. This derivation of delta H over delta P was detailed in the section on the Joule-Thomson experiment. So in that section, we needed to derive delta H over delta P, so you can see more detailed derivation there. Over here, this is just a quick derivation, especially going from here to here. I want you to just double check this numerically. So for example, 1 over 0.99 is 1.01. 1 over 0.999 is 1.001 with a very small numerical error. Now let's look at this. You can see delta H over delta P for a Reynolds gas depends on both A and B. If B is predominant, and then this delta H over delta P is positive. If A is predominant, and then delta H over delta P is negative. Alright, so really it's just mathematics. If B is greater than 2A over RT or smaller than 2A over RT, we have a different sign for delta H over delta P. Again, for a Van der Waals gas, we have this equation. It's just MB minus 2AN over RT. And then we can compute delta H this way. Again, we're assuming H depends on pressure and temperature, so we integrate CP dt. Over here, we just integrate this delta H over delta P dP. Assuming CP is a constant within a moderate temperature range, this integral is just CP times delta T. Over here, I'm going to assume all this are constants. That's a really reasonable approximation, and it's gonna be just this mb minus 2n over RT times delta P. For ideal gas, of course, A is 0, B is 0. There's no attraction, no repulsion. And then delta H over delta P is just 0. So this part becomes 0 for ideal gas. And then delta H is just the C integral of CPdT. That's really easy. Now for a liquid or solid, do not do this. Again, this is just for van der Waals gas with van der Waals parameters. So do not do this. Do this instead. We derive this equation using one of the Maxwell relations. And delta V over delta T on a constant pressure condition, this one is simply V times alpha. That's the definition of alpha. Alpha is this derivative over V. Alright, so you get this equation. And for a liquid or solid, alpha is usually very, very small. Okay, this alpha is usually very, very small, like 10 to the power negative 4 or even smaller than that. And then that means T times alpha. T is 10 to the power 2, 300-ish. So T times alpha is usually much smaller than 1. So we can say this is approximately 1. Now let's look at one example. If you have copper, you have alpha, you have kappa, and we multiply T and alpha, we got 0.015. That's much smaller than 1. So over here, this T times alpha at room temperature is much smaller than 1 for copper. Even for a liquid like water, T times alpha is roughly 0.06 at 300 Kelvin, so it's still much smaller than 1. Because of that, we can still use this approximation for the convenience of calculation. And then for a liquid or solid, we can simply integrate CPdT. We can integrate this. This is delta H over delta P times dP. The first integral is Cp times delta T. The second integral is V times delta P. Again, we'll just look at this subtraction and notice the term to be subtracted is much smaller than V, so we drop this one. Over here, we were assuming Cp is independent of temperature. As long as the temperature range is a moderate temperature range, we can use this equation. No problem. And again, U, H, G, and A all depend on PVTS, but out of pressure, volume, temperature, and entropy, only 2 may be chosen as the independent variables for a fixed amount of pure substance. Of course, if you can change the amount of the substance, then there will be a total of 3 independent variables. Now we have only 2. It's very convenient to view G as a function of temperature and pressure like this. dG is dH minus dTs. dH is TdS plus VdP. dTs is TdS plus SdT. You cancel TdS, you get negative SdT plus VdP. G depends on temperature, G depends on pressure. dG over dt is negative S when pressure is constant. When T is constant, dG over dP is volume. The Gibbs energy of a pure substance always increases as temperature increases. The reason is this negative entropy is always negative. So when temperature goes up, G goes down, assuming the pressure is held constant. The Gibbs energy always increases as V increases. Sorry, there's a typo here. As P increases. Alright, this is a typo. This is just because V is always positive, so if dP is positive, then dG is positive. If temperature is held constant. Alright, so we have this equation. Alright, delta G over delta T is always negative when pressure is constant. When we have a isobaric process, we can simply write dG is negative SdT, and then delta G is negative integral SdT. Alright, but this entropy also depends on temperature, so this integral is not that easy. Alright, you have to know how this entropy depends on temperature, and then integrate that. Now let's look at this equation. Delta G over delta P is V if temperature is constant. So when we have a isothermal process, dg is just vdp. We can just integrate this part. It's usually easy, no matter the substance is in the gas phase, liquid phase, or solid phase. If it's in the gas phase, this v is approximately nRT over p, and you will get nRT times the logarithm of p final over p initial, right? That's one way to do it. If you have a real gas, use the Van Hoff's equation, or simply just say this is approximately an ideal gas for a liquid or solid, because the volume of a liquid or solid does not really depend on the pressure change. All right, as long as your pressure change is moderate, the volume of a liquid or a solid remains constant or approximately constant, and it's really easy to integrate a constant. Again, in an isothermal process, dg is just vdp because dt becomes 0 when it's isothermal, and we have this equation. If we have a ideal gas, you can see the detailed derivation over here. Volume is nRT over p, and we integrate this, we get nRT times the logarithm of p final over p initial. For a real gas, most of the time we can just put an approximate sign here. V is approximately nRT over p, so we still get this. Again, for a liquid or solid, V remains constant, so we just do this. Delta G is V times delta P. As long as the pressure change is not too significant. For example, if you change the pressure by 5,000 bars, and then we might have to look at the volume change. We might. Let's look at one example problem, 5.5.1. Calculate the change in the Gibbs energy of 1.0 liquid water with this density when the pressure changes from 1 bar to 2 bars. We'll just do this. When the pressure changes from 1 bar to 2 bars, I'm pretty sure the volume of water remains roughly constant, and its molar volume can be easily calculated given the molar density, given the density and molar mass, which is 18 milliliter per mole, and we have 1 mole such water, so it's 18 milliliters multiplied by pressure change. Milliliter is 10 to the power of -6 cubic meter. Bar is 10 to the power of 5 pascals. So the result is only 1.8 joule. Or you can say 0.0018 kilojoule. Now let's look at another numerical example problem, 5.5.2. Same water, 1 mole water, and but this time it's water vapor. Okay, it's water vapor. Now we're going to change the pressure from 1 bar to 2 bars for this gas phase. Now let's look at this. This time we're going to use ideal gas law. Volume is nRT over P. We integrate nRT times the natural logarithm of PF over PI. So we have Ln2 here. Ln2 is roughly 0.7. Temperature is 400. R is 8.3, and we have 1 here, so it's 8.3 times 400 times 0.7. Roughly it's 2300 joule. Now if you compare this 1.8 versus 2300 joule, you realize that the Gibbs energy of the gas depends on the pressure significantly. The Gibbs energy of a liquid or a solid does not quite depend on the pressure change. The dependence is minimal. They differ by roughly in the order of 10 to the power 3. This is because if you look at this equation and this equation, you'll notice this V is much larger than this V. The V of the vapor is much larger than the V of the liquid. How much larger? Well, roughly in the order of 10 to the power 3. That's why this is larger than this by an order of 10 to the power 3. Chapter 5, Helmholtz energy and Gibbs energy. Section 5.6, Changes of U, H, A, G, S when ideal gases mix. The isobaric mixing of two or more ideal gases at the same temperature is equivalent to the expansion of the individual ideal gases. This is just because the mixing does not affect the potential energy or kinetic energy of any of those mixing gases. It only changes the volume of those gases. For example, let's look at this diagram. We're going to mix A and B. Now you can see A initially occupy a smaller volume. After expansion, A occupies a larger volume. Same for B. So really the volume of A is doubled, the volume of B is doubled. It's isothermal expansion. In isothermal expansion, well, we know PV equals nRT. So when the volume of A is doubled, the partial pressure of A is halved. Same for the partial pressure of B. And this isobaric actually means what? It means the total system pressure is unchanged. So for example, over here, let's say initially PA is 1 bar, PB is 1 bar. After mixing, the system pressure is PA plus PB. Although both PA and PB are halved, the total pressure is equivalent to the initial pressure of A and also to the initial pressure of B. In that sense, we say this is isobaric mixing. However, remember, the partial pressure of A and the partial pressure of B are reduced in the mixing process. It's just the total system pressure remains unchanged. And also, if you look at the total volume of the system also remains unchanged. And the temperature remains unchanged. So really, P, V, and T of the system remain unchanged during mixing. Now what about U, H, A, G, and entropy? We'll analyze those. When A and B ideal gases are mixed, gas A and gas B do not really feel each other. This is because ideal gas particles do not attract or repel each other. Therefore, we have delta U equals 0. So there's no change in potential energy. And also, since it's isothermal, there's no change in the average kinetic energy. And because there's no change in the number of particles, we can say there's no change in kinetic energy. Therefore, delta U is 0. Delta H is also 0 because H is U plus PV. And delta U is 0. We have proven this. Delta PV is delta nRT, so delta nRT is 0. Again, it may be a little confusing. When we say PVT, we are referring to the entire system. So if this is 1 bar, this is 1 bar, we say the whole system has a 1 bar pressure. After mixing, it's still 1 bar. And we consider this, the total volume of A and B before mixing, as the volume of the system. And over here, this is the volume of the system, so there's no change in V. And finally, there's no change in T. So let's say we start from room temperature here, and finally we have room temperature. Again, P is the total pressure of the system. Over here, this P. The pressure of the entire system is equivalent to the initial pressure of A and initial pressure of B. And again, V denotes the total volume of the entire system, so this whole thing. The Gibbs energy of gas A decreases after mixing. Alright, why is that? It's because the Gibbs energy of A depends on the partial pressure of A. So we can use this equation. Delta G of A is the integral of V of A dP of A, and V of A is nART over PA, and we integrate this. We're going to get nART, the number of moles of A times RT, times the logarithm of PA final. divided by PA initial. And PA initial is the total pressure P. Alright, so we have this equation here. And what's this? What's PA final over P? That's simply the mole fraction of A after mixing. That's why we have this equation. Delta G of A, the change of the Gibbs energy of A, is N sub A times RT times the natural logarithm of the mole fraction of A in the mixed system. Similarly, delta G of B is equal to MBRT times the natural logarithm of X of B. X of B is the mole fraction of B. Alright, after the mixing, you have the mole fraction of B less than 1. Because Gibbs energy is additive, we can just sum up the change of the Gibbs energy of A and the change of the Gibbs energy of B to get the total change of the Gibbs energy of the entire system. We get this equation. Alright, we have RT and then times NA ln XA plus NB times ln XB. Somehow you realize this NA is just N times XA and NB is just N times XB if we use N to denote the total number of moles. Again, when we have the isobaric mixing of two ideal gases at the same temperature, there's no change in PVT, there's no change in U, there's no change in H. However, the Gibbs energy decreases. We have this two equation because after mixing, X sub A is less than 1, X sub B is less than 1. Therefore, delta G of A is negative, delta G of B is also negative, and we can sum it up. We get this. And we set N as the total number of moles of all gases. In this case, we have only two gases. It's just Na plus Nb. Na is N times Xa, Nb is then N times Xb. Delta G is simply nRT times Xa ln Xa plus Xb times ln Xb. What if we have three ideal gases? We just need one more term. We need X of C times the natural logarithm of X of C. So we have the sum of three terms. We have delta G is equal to the sum of the Gibbs energy changes of A and B and C. What if we have N different ideal gases? Well, we'll have to resort to this uppercase Greek letter sigma. Sigma denotes the sum, and over here it's the sum of X of I times the natural logarithm of X of I. I is just the index of the ideal gases. I is from 1 to N. Alright? Again, there's no change in PV. Delta PV is 0. So delta A is equal to delta G. Why? A is G minus PV. So delta A is delta G minus delta PV. Delta PV is simply 0. And therefore, we have delta A is also equal to nRT times the sum of Xi ln Xi. The isobaric mixing of N different ideal gases at the same temperature results in no change in U and H. However, the Gibbs energy and the Helmholtz energy both decrease, and the change of A and the change of G are both negative. The equations are here. We can compute delta G using this equation, delta A using the same equation. And because delta U is 0 and we have delta U is delta A plus delta TS, somehow we can compute delta TS. Again, it's just because of this equation and temperature is constant, so we have this. And now we can just plug in the values. Delta U is 0, so delta A plus T delta S is 0. And delta A is this nRT times the sum of xi ln xi. So over here, this is delta A plus T delta S is 0. Using this equation, we obtain the expression of the entropy of mixing. It's negative nR times the sigma, or the sum of xi ln xi. This whole thing is greater than 0 despite the appearance of a negative sign. Only because every single term here is negative. The mole fraction of any species is less than 1. The logarithm of the mole fraction is negative. Therefore, the entropy change is positive. The entropy change of the mixing of ideal gases is always positive. Let's look at one example. Let's mix 3 gases, 0.2 moles of A, 0.3 moles of B, 0.5 moles of C, and then we mix them at constant pressure, constant temperature. The total number of moles is 1 mole, and delta S is simply, we're going to use this equation, negative nR, and then we have the sum of 0.2 ln 0.2, 0.3 ln 0.3, 0.5 ln 0.5. Do all the calculation, we get 8.56 joule per Kelvin. This is the mixing entropy, for this process of mixing 0.2 moles of A, 0.3 moles of B, 0.5 moles of C. Again, the entropy always increases when we mix ideal gases or even real gases. In general, the mixing of different gases always results in a significant increase of entropy. Chapter 5, Helmholtz energy and Gibbs energy. Section 5.7, Changes of H and G in chemical reactions. In a chemical reaction, the enthalpy of the system changes, even if the temperature and pressure remain constant. This is just because the initial state of the reaction system is different from the final state of the reaction system. In the initial state, we have reactants. In the final state, we have products. They're just different, even if they are at the same temperature and same pressure. In this case, we have the standard enthalpy of reaction is equal to the standard enthalpy of formation of products minus the standard enthalpy of formation of reactants. What about the standard internal energy of reaction? U and H differ by PV. So delta U is delta H minus delta PV. Now let's look at the standard Gibbs energy of reaction. It is equal to the standard Gibbs energy of formation of products minus the standard Gibbs energy of formation of reactants. And what about delta A, the Helmholtz change? Well, since A is G minus PV, and therefore delta A is delta G minus delta PV. At a given temperature T, we have delta G is equal to delta H minus T delta S. This is just because G is defined to be H minus Ts. So delta G is delta H minus delta Ts. And when T is constant, delta Ts is T delta S. We have this equation. The Gibbs energy of formation of pure elements in their standard state at the room temperature are chosen to be zero references. For example, if you have pure oxygen gas with 1 bar pressure, its Gibbs energy of formation is 0 at room temperature. Meanwhile, its standard enthalpy of formation is also 0. And based on these two values of 0, we can say, well, the standard entropy of formation of the oxygen gas is also 0 at room temperature. And note that the standard entropy of formation of oxygen is different from the absolute value of the molar entropy of oxygen with 1 bar pressure. The former is relative to pure elements at room temperature. The latter is relative to 0 Kelvin oxygen crystal. So major differences. Alright, over here we use the 0 reference at room temperature, and the oxygen as the zero reference should be in the gas phase. Over here we use a different reference at 0K, and that zero reference should be oxygen crystal, a perfect crystal of oxygen. Alright, but either way, if you just keep using the same reference, same set of references in your calculation, you will always get the same entropy of reaction. The enthalpy of an ideal gas does not depend on its pressure, and therefore the enthalpy of reaction with all involved gases in the non-standard state, that means not 1 bar pressure, is the same as the standard enthalpy of reaction. Alright, so if only ideal gases are involved, this enthalpy of any of those gases does not depend on the pressure. Now the Gibbs energy of an ideal gas, however, does depend on the pressure, and therefore the pressure dependence of the molar Gibbs energy of gas A must be considered using this equation. Look at this equation over here. This is the standard Gibbs energy of formation of A. This is non-standard. What's the difference? The difference is RT times the natural logarithm of the actual pressure of A over 1 bar. And why is this? Well, it's simple. dG is negative S dt plus VdP. Alright, if the temperature is held constant, dG is just VdP. For an ideal gas, VdP is just nRT over P dP. Alright, and therefore we can integrate this nRT over P dP. We get nRT times the natural logarithm of P. And now over here, these two are molar Gibbs energy, therefore we remove this n here, it becomes RT times the natural logarithm of pressure. And if the pressure changes from P naught to this P sub A, the Gibbs energy changes by this much. Now let's look at a few examples for this reaction. From H2 and CO2, we get 2 HCl molecule at room temperature. The enthalpy of formation of H2 and CO2 are both 0 because these two are pure elements, and we have room temperature, and this is the standard state. That means the enthalpy of formation of H2 of 1 bar at room temperature is 0. Same for chlorine. The standard enthalpy of reaction is twice the standard enthalpy of formation of HCl. Why twice? You see this 2 here. Alright? And we know the standard enthalpy of formation of HCl is negative 92.3 kilojoule per mole. You can look up this value from chapter 00, the appendices. You can find the value from the NIST website, National Institute of Standards and Technology. Alright, and we'll just have this equation. The standard enthalpy of reaction is the products minus reactants. We have 2 HCl as the products, so 2 times this minus reactants, which is 0 and 0. So in the end, we get negative 184.6 kilojoule per mole as the standard enthalpy of reaction over here. So this amount of heat will be released, assuming the isobaric condition. At 25 degrees Celsius, the enthalpy of 1 mole HCl in the standard state is 92.3 kilojoule, lower than the sum of 1/2 mole H2 in the standard state and the enthalpy of 1/2 mole CO2 in the standard state. So this is from this number, okay, 92.3. Now let's look at the same reaction. Let's analyze the Gibbs energy change of the reaction. The standard Gibbs energy of formation of both H2 and CO2 are both 0 again. It's just because, again, H2 and CO2 in the gas phase are chosen to be the 0 references when we define the standard Gibbs energy of formation. Alright, as long as they have 1 bar pressure, room temperature, their standard Gibbs energy of formation are just 0. Now the standard Gibbs energy of this reaction is just twice the standard Gibbs energy of the formation of HCl. We look up this value, it's negative 95.3 kilojoule per mole, Given this number, we can compute the standard Gibbs energy of reaction. Alright, for this reaction, we'll just do the calculation. We get negative 190.6 kilojoule per mole. This is the standard Gibbs energy of reaction for this. At 25 degrees Celsius, the Gibbs energy of 1 mole HCl in the standard state, that means just 1 bar HCl gas, is 95.3 kilojoule lower than the sum of the Gibbs energy of 1/2 mole H2 and 1/2 mole of CO2. This 95.3 comes from here because this is relative to the pure elements such as H2 and CO2. The production of 1 mole HCl gas from H2 gas and CO2 gas may generate electric work of no more than 95.3 kilojoule and 298 Kelvin. Alright, remember this equation. Alright, so if delta G of the system is reduced by this much, we can provide some non-expansion work such as electric work, no more than 95.3 because delta G serves as the lower limit for non-expansion work under constant temperature and pressure condition. Again, the same reaction over here from H2 and CO2 to HCl. We have the standard enthalpy of reaction. We have the standard Gibbs energy of reaction. Again, it's just the products minus reactants. Products minus reactants. You do need to look up the value of the standard enthalpy of formation of HCl and standard Gibbs energy of formation of HCl. All right. These two are just zeros. These two are just zeros, and then we got those numbers. By the definition of G, we have this Gibbs energy of reaction is the H minus Ts of the reaction. So we have this equation at given temperature, 25 degrees Celsius, and then we can compute the entropy of reaction over here. It's delta H minus delta G over T. Okay, delta H minus delta G over T. We'll plug in the standard enthalpy of reaction and the standard Gibbs energy of reaction here and here, and then divided by temperature in Kelvin, we get 20 joule per mole K. This is the entropy change of the reaction in the standard state. So this is a positive number, so that means at 25 degrees Celsius, the entropy increases. The entropy of 2 mole HCl is greater than the entropy of this H2 and CO2. Alright, so we have this. Assuming the standard entropy of formation of pure elements in the most stable state of aggregation at room temperature are just 0, and then we have just obtained the value of the standard entropy of formation for HCl. It's just this divided by 2. It's just 10 joule per mole Kelvin, because this is the difference between over here. You can see we have 2 HCl, but if you're looking at molar entropy, it's just this number divided by 2. And I want to emphasize this is not the traditional molar entropy of HCl. So we have a traditional definition of standard molar entropy of HCl. This is relative to the oxygen crystal at 0K. Over here, this has a different zero references. This value is relative to pure elements at room temperature in their most stable state of aggregation. So the standard entropy of formation of HCl is relative to the 1 bar H2 gas, 1 bar CO2 gas at room temperature. Over here, this is relative to the 0K HCl perfect crystal. So these two have different values. Alright. Although we are using different zero references for this absolute value of molar entropy, and over here for the standard entropy of formation, if your goal is to calculate the entropy change of a reaction, you can use either quantity. You just need to use them consistently. So for example, you can use the standard entropy of formation for all chemicals and then you can compute the entropy change of the reaction correctly. You can use the absolute values of the molar entropy of all chemicals, and you will get the entropy change of the reaction also correctly, and this too will result in the same entropy of reaction. Again, you just need to use the same set of zero references consistently for all chemicals in your calculation. Chapter 5, Helmholtz energy and Gibbs energy. Section 5.8, Criteria of spontaneity. The second law of thermodynamics states that the entropy of an isolated system always increases until the system reaches thermodynamic equilibrium. The second law can also be used to predict the direction of spontaneous chemical reactions or physical changes in an isolated system. Well, whatever chemical reactions or physical changes, they must result in an increase of the entropy of this isolated system. We're going to assume the universe is isolated, so all chemical reactions or physical changes, as long as they proceed spontaneously, well, they increase the entropy of the universe. The entropy change of the universe is greater than zero. There are different criteria for non-isolated systems. So if we have a closed system, that means there's no matter exchange under constant TV condition. Reactions or physical changes proceed spontaneously in the direction of decreasing A. Delta A should be negative. The Helmholtz energy must decrease when non-expansion work is zero. Here we have the proof. We start from the second law of thermodynamics. The entropy change of the universe must be greater than zero for a spontaneous process, and therefore delta S surroundings plus delta S is greater than zero. This is just the entropy change of the surroundings. This is the entropy change of the system. And now we multiply both sides by T. We can do that because T cannot be negative. So T times delta S surroundings plus T delta S is greater than zero. And T delta S surroundings is simply Q surroundings. And Q surroundings plus T delta S is greater than zero. Q surroundings is negative Q. So we have negative Q plus T delta S is greater than zero. By the way, we just proved the Clausius inequality again. TdS minus Q is greater than zero. TdS is greater than Q. This is Clausius inequality. Actually, we just proved this one more time. Now we have this equation. Negative T delta S is less than Q. Negative Q is W minus delta U. And if the non-expansion work is zero, and in this constant volume condition, the expansion work is also zero. Alright, remember we are proving this delta A is less than zero for the constant TV condition. So when it's constant volume, that means there's no expansion work. And also when there's no non-expansion work, okay, this work is simply zero. And then we have negative T delta S is less than negative delta U. We move this delta U to the left hand side. So delta U minus T delta S is less than zero. And again, we're proving this delta A is less than zero under constant TV condition. When T is constant, T delta S is delta TS. And then we get this equation. And then it's just delta A is less than zero because A is U minus TS. So all this constitute the proof of delta A must be negative under constant TV condition when there's no non-expansion work. Again, there are different criteria for non-isolated systems. If we have a closed system under constant TP condition, the criterion of spontaneity is this: delta G is less than zero when there's no non-expansion work. Here's the proof. This time we're going to start with the Clausius inequality right away. T delta S is greater than Q. And this Q is Q sub P under constant TP condition. So if pressure is constant, Q is Q sub P. And Q sub P is just delta H. Now we have TdS, T delta S is greater than delta H. So delta H minus T delta S is less than 0. Temperature is constant, so T delta S is delta Ts. On the left hand side, we have just delta of H minus Ts. H minus Ts is just G. Now we have delta G must be less than 0 for any spontaneous reactions or physical changes under constant temperature and pressure condition, when the amount of non-expansion work is 0. You may ask, what if there is non-expansion work? Then delta G is less than the amount of non-expansion work. For a closed system under constant entropy condition, how do we have this constant entropy condition? So one example is adiabatic reversible. In that case, entropy is constant. Now let's look at this. Exothermic reactions or physical processes proceeds spontaneously. Here we have a proof. So if we have constant entropy condition, first let's write out the Clausius inequality, which is negative Q plus T delta S is greater than 0, or T delta S is greater than Q. And then we have Q is less than T delta S. And look, it says constant entropy condition. That means delta S is 0. Therefore, Q is 0. So if you have a closed system and the system has a constant entropy condition, that means only exothermic reactions may proceed spontaneously. Now for a system under constant entropy and volume condition, chemical reactions or physical changes proceed spontaneously in the direction of decreasing the internal energy when non-expansion work is 0. So the proof is very simple. Delta U is Q plus W when there's no non-expansion work and no expansion work, because volume is constant. There's no expansion work as well. That means W is simply 0. So delta U is Q. And since Q has to be less than 0, delta U has to be less than 0. So if you have constant entropy and constant volume, and there's no non-expansion work, then not only Q should be less than 0, but also delta U should be less than 0. And that's the direction of the spontaneous reactions. For a closed system under constant entropy and pressure condition, we can easily prove this. Q sub P is less than T delta S. Again, delta S is 0, so Q sub P is less than 0. Delta H is equal to Q sub P if there's no non-expansion work, and then delta H has to be less than 0. So really, depending on the conditions of the closed system, we have different criteria for the spontaneity. For isolated system, we just look at the entropy. Entropy can only increase. We look at Helmholtz energy under constant TV condition. We look at Gibbs energy under constant TP condition. We have to look at the internal energy under constant SV condition, or enthalpy under constant SP condition. So under different conditions, we look at different criteria. So we have all those criteria on the different conditions. As you can see, we can use delta S, delta A, delta G, delta U, delta H as the criteria for the spontaneity under different conditions. Can we somehow unify all those different criteria for the system under all those different conditions? Well, the short answer is yes, but we have to define a new thermodynamic quantity, mu. Mu denotes chemical potential, and chemical potential is defined this way. And mu is delta G over delta N under constant TP condition. And why do we have I here? It's just because we need to look at a mixture. Mu sub I is the chemical potential of species I. This N is actually the number of moles of species I. And then we have delta G over delta Ni under constant TP condition. And we need to hold the amount of all other species constant. So this is how we define the chemical potential mu. For a pure substance, what is mu? Mu is simply just delta G over delta N under constant TP condition. So if you have a pure substance, the chemical potential is just the molar Gibbs energy, the same thing. But when you have a mixture, mu can be different from the molar Gibbs energy, and it's often different. Alright, and we will study chemical potential in the next section, 5.9. And then we'll realize that somehow we can unify all those criteria for spontaneity. We will cover Chapter 5, Section 9, Chemical Potential, in 9 short videos. In this very first video, we'll talk about the structure of Chapter 5 and also Section 9 in particular. In Chapter 5, we first define A and G. We'll look at how U, H, A, and G depend on pressure, volume, temperature, and entropy. In Section 3, Maxwell relations, we study how PVTs depend on each other. In Sections 4 and 5, again, we look at how U, A, and Hg depend on TV or TP. We look at how U, H, Ag entropy, how they change when ideal gases mix, and also specifically how H and G change in a chemical reaction. Right before Section 9, we talked about the criteria of spontaneity. For example, under constant TV condition, we should look at A. Under constant TP condition, we should look at G. In Section 9, there are 9 videos. The first video is the structure of this section. In the second video, I will present the rationale for introducing chemical potential. Video number 3 includes the definitions of chemical potential. Video number 4 is about the criteria of spontaneity in terms of chemical potential. And then the last 5 videos are about the numerical and analytical examples of chemical potential. In this video, I present the rationale for introducing chemical potential. We have learned pressure, volume, temperature, and entropy. We have also learned internal energy, enthalpy, Helmholtz energy, and Gibbs energy. We learned how these thermodynamic functions depend on each other. But now, why do we need another thermodynamic function, chemical potential? Well, I'll use several examples from the simplest to the more complex scenarios to justify the introduction of chemical potential. And later we'll see chemical potential connects U, H, A, and G. Chemical potential is the central piece of thermodynamics. Now let's look at a very simple system that consists of a single species with a fixed amount, and this species is in a single phase. And then the Gibbs energy of this system is a function of only 2 independent variables. We can pick any 2 from PVTs, but for convenience, we write dG is equal to negative SdT plus VdP. Negative entropy is how G depends on temperature. Volume is how G depends on pressure. Now let's make it more complicated. What if the amount of this single species may change? And then we have 3 independent variables. Other than temperature and pressure, we have the amount of this species. And now Gibbs energy is a function of T, P, and N1. dG can be expressed as delta G over delta T times dt plus delta G over delta P times dP plus delta G over delta N1 times dN1. And we need to pay attention to the subscripts over here. Temperature and pressure are held constant. So what if temperature and pressure are indeed constant? Then dt is 0. dP is also 0. dG is simply this term, delta G over delta N1 times dN1. Now, what's delta G over delta N1? Well, it's simply molar Gibbs energy of this species under the specified temperature and pressure condition. More generally, you can say it's the partial molar Gibbs energy. And then what if we make the system even more complicated with two species, or a single species in two phases, for example, water in the gas and liquid phases, and then we need to introduce one more variable. We have N2. All right, either we have two species or one species in two phases. Now we have four independent variables: temperature, pressure, N1, N2. And then we put those partial derivatives in front of those exact differentials. And also we need to pay attention to the subscripts. Over here, Tp and N2 are constant. Over here, Tp and N1 are constant. So again, when there are two species or a single species in two phases, they should be treated as two species. In the system, we have four independent variables. Again, G depends on temperature, G depends on pressure, G depends on N1, G depends on N2. Now, what if we hold N1 and N2 constant? Well, in that case, dG is simply delta G over delta T times dt plus delta G over delta P times dP. Over here, again, we have N1, N2 constant. And for this dt term, we hold P constant. For the dP term, we hold temperature constant. And also, we know this: if the amounts of all species in the system are fixed, we have dG is negative S dt plus VdP. Negative entropy is how G depends on temperature, which is just this. And volume is how G depends on pressure, which is just this. And then we get the expression for entropy and volume of the system with two species. Negative entropy is delta G over delta T when pressure N1 and N2 are constant. Volume is delta G over delta P when temperature N1 and N2 are constant. In general, we can write out this form of dG. dG is negative S dt plus VdP plus the sum of delta G over delta Ni dNi. So when we evaluate this partial derivative, temperature, pressure, and, well, the amount of all other species should be held constant. The last term can be simplified upon the introduction of chemical potential. Later we'll see this part, this partial derivative, is chemical potential. In this video, we will define chemical potential in 12 different ways. But first, the most fundamental definition. UPAC defines the chemical potential mu of a species I in a mixture as follows. Mu sub I is delta G over delta Ni. Temperature, pressure, and the amounts of all other species are held constant. So G is a function of pressure, temperature, N1, N2, N3, etc. dG can be expressed as the sum of many terms: the dt term, the dP term, and then dN1 term, dN2 term, dN3 term, etc. Also, we can write dG is equal to negative S dt plus VdP plus the sum of mu I dNi. Negative entropy is delta G over delta T. Volume is delta G over delta P. By holding all other independent variables constant, S and V are the total entropy and volume of the entire system. What if there's only one species in the system? And then over here, the sum of mu I dNi contains only one term, mu1 dN1. And what if this N1 is constant? And then this equation is reduced to dG is equal to negative S dt plus VdP. It's a simple expression of dG we have learned in the previous sections. What if the temperature and pressure are held constant? And again, this equation can be reduced. In a different way, dG is simply mu1 dN1. And mu1 is dG over dN1 under the specified temperature and pressure. In this case, chemical potential is simply the molar Gibbs energy of this pure species. But is mu always equal to molar Gibbs energy under constant temperature and pressure condition? The answer is no. In a mixture, mu is often different from the molar Gibbs energy under constant TP condition. We'll derive this, we'll calculate this a bit later. We have learned a few equations about U, H, A, and G. H is G plus Ts, A is G minus PV, U is A plus Ts. By using these equations and also the equation of dG in terms of chemical potential, we get three other equations for du, dH, and dA in terms of chemical potential, here, here, and here. And you can see this equation and the three other equations are very similar to each other. You basically just replace this -1, -SdT plus VdP to just different expressions that we have learned before. Now, by looking at these four expressions, we have four different definitions of chemical potential. It's delta U over delta Ni, delta H over delta Ni, delta A over delta Ni, or delta G over delta Ni under different conditions. Over here, when we use U, make sure S and V are constant. When we use H, SP should be constant. When we use A, T and V should be constant. When we use delta G over delta Ni, then temperature and pressure should be held constant. This is the UPAC definition. We have more definitions for mu. If we use the triple product rule in calculus, delta U over delta N can be expressed as negative delta U over delta S times delta S over delta Ni. Just need to pay attention to the subscripts, and then we can see mu is negative T times delta S over delta Ni under constant UV condition. It's also negative T times delta S over delta Ni under constant HP condition. Again, we use the triple product rule to finish this derivation. So we can express mu as the variation of entropy with respect to the amount of the species. And also we can define chemical potential in terms of PVT, but I want to remind everyone the two most commonly used definitions of mu are the variations of A and G with respect to the amount of the species. Delta A over delta N under constant TV condition, delta G over delta N under constant TP condition. It's just because it's easier experimentally to maintain a constant TV or constant TP condition. I'm going to show you how to express mu in terms of delta T over delta N, delta P over delta N, or delta V over delta M. However, those are trivial. Again, we want to focus on these two equations under a constant TV condition. Let's use A. On a constant TP condition, let's use delta G over delta Ni. In this video, we will review several commonly used criteria of spontaneity and unify all of them based on the concept of chemical potential. We learned this before. In an isolated system, entropy can only increase. On a constant temperature and volume condition, the Helmholtz energy of the system A can only decrease. At a constant temperature and pressure condition, the Gibbs energy of the system G can only decrease. Now we'll combine all of them into a single inequality expression. First, let's look at the definitions of the chemical potential. This equation, dG is equal to negative SdT plus VdP plus the sum of mu I dNi. This is based on the UPAC definition of the chemical potential. We can easily derive three other equations because H is simply G plus Ts, U is H minus PV, and A is U minus Ts. So we have a total of four equations that involve this chemical potential mu sub I. And we can actually move this TdS term, PDV term to the left hand side, And then we get the sum of mu I dni is equal to du minus TdS plus PDV. We'll write it here. And also we can use this equation. We get the sum of mu I dni is equal to dH minus TdS minus VdP. Similarly, the sum of mu I dni is equal to dA plus SdT plus PDV from this equation. The sum is dG plus SdT minus VdP from this equation. Why do we need all these equations? Now let's get back to the criteria of spontaneity. Under constant TV condition, we learned that dA must be negative. Now look at this equation. Under constant TV condition, dt is 0, dV is 0. Then dA is simply equal to the sum of mu I dni. Because dA must be negative, the sum of mu I dni must be negative. Under constant temperature and pressure condition, the criteria is dG must be negative. And again, under constant temperature and pressure condition, dt is 0, dP is 0. So dG is equal to the sum of mu I dni. We draw the same conclusion. Under constant TP condition, the criterion of spontaneity is also the sum of mu I dni being negative. In general, regardless of the condition of the system, the criteria of spontaneity for a closed system is always the same. It's this: the sum of mu I dni must be negative. And from the previous page, we learned that there are 4 different expressions for the sum of mu I dni, and this must be negative. That means du minus TdS plus PDV must be negative. dH minus TdS minus VdP must be negative. And this must be negative. This also must be negative. So we have these 4 inequalities here. Again, du minus TdS plus PDV must be negative. And then we have 3 more in terms of dH, dA, and dG. Now let's look at the first 2. When entropy and volume are constant, du must be negative. You cannot increase. The internal energy of the system must decrease until the equilibrium is reached. When entropy and pressure are held constant, then dH must be negative. H can only decrease. However, constant entropy conditions are rarely encountered. That's why we often look at A and G as the criteria of spontaneity. Under constant TV condition, we know dA must be less than 0. Under constant TP condition, we know dG must be less than 0. And therefore, we have a unified expression here. The sum of mu I dni must be negative. The sum of mu I dni must be negative under constant TV condition, under constant TP condition. Finally, for a constant energy system, that means du is 0, that means dq plus dw is 0, and because the sum of mu I dni is du minus TdS plus PDV, we learn this must be negative, du is 0, and then therefore TdS must be greater than PDV. For example, if we have an expanding universe, and let's assume the energy of the universe is a constant, and then we have TdS must be greater than PDV, and dV is greater than 0. Therefore, TdS is greater than 0. This inequality can be further reduced to TdS greater than 0 or ds is greater than 0 if the volume of the system is held constant, as well as U. In this video and for other videos, we will either calculate or derive the chemical potential of a helium gas in a mixture under various conditions: constant TV, constant TP, and constant HP. Now let's look at the simplest case. When temperature and pressure are held constant, The chemical potential of a pure species is simply its molar Gibbs energy, and this is a relative quantity. We can set different zero references. There are two ways to define this standard molar Gibbs energy. One is this: the standard molar Gibbs energy is equal to the standard Gibbs energy of formation. Another way is this: it's the standard enthalpy of formation minus temperature times the standard molar entropy. Using this equation is more convenient because the second expression, well, involves the value of the standard molar entropy. We need to look it up. So let's stick to the first expression to calculate the chemical potential of the helium gas in a mixture first. And later I'll show you these two expressions will result in the same expression for chemical potential. The second expression is just a little bit more tedious. Now let's use this equation. Let's assume the standard molar Gibbs energy is equal to the standard Gibbs energy of formation, and we know these two are equal to 0 for a pure helium in the standard state at room temperature, just by definition. Now we have this equation from UPAC. Mu is delta G over delta N. Alright, and then we're going to use the finite change of the Gibbs energy divided by the finite change of the normal mole to estimate the numerical value of the chemical potential of a helium gas in a mixture. Alright, let's focus on this. To perform the numerical calculation, we need to know two things. We have learned those before. Number one, Gibbs energy is additive, so delta G is the sum of the Gibbs energy changes of all components in the system. Number two, the molar Gibbs energy of an ideal gas is simply the standard molar Gibbs energy of this species plus a correction, RT times the natural logarithm of the partial pressure of this species divided by 1 bar. Now let's quickly review the various definitions of chemical potential. We introduced 12 of them, but many are less commonly used. We will only verify these three definitions are equivalent to each other. We will see the chemical potential is equal to delta G over delta N on a constant TP condition. Also, it's delta A over delta N on a constant TV condition, or negative T times delta S over delta N on a constant HP condition. We'll show you all three expressions will end up to be this. The chemical potential of a helium is just the standard chemical potential plus RT times the natural logarithm of the partial pressure of this gas over P naught. Over here, I'm just showing you the wheel of thermodynamics, U, H, G, and A. Again, U plus PV, you get H, H minus TS, you get G, and G minus PV, you get A plus TS, you get U. Mu is the central piece of this wheel of thermodynamics. Now let's look at the first numerical example. Let's look at the simplest condition, constant temperature and pressure. So under the constant temperature and pressure condition, mu is delta G over delta N. We'll just calculate the finite change of G and N. So first let's look at a simple system. There's a 1 bar gas mixture. Inside we have 0.4 moles of helium, 0.6 moles of argon. We can get the partial pressures of the two gases, and then we add a very small amount of helium into the system to get a finite change of G. And we have this finite change of the amount of helium. And then we do the division, we get the chemical potential. After the addition, we need to calculate the new partial pressures for helium and argon. So the partial pressure of helium is now a little bit more than 0.4. the pressure of argon is a bit less than 0.6, but the sum is still 1 bar. Again, we are holding the total pressure of the system constant. Now we need to compute the finite change of the Gibbs energy. It has 3 components. So first, we added this amount of helium, so we need to compute the Gibbs energy of the added helium. And then we need to calculate the change of the Gibbs energy of the pre-existing helium and also the Gibbs energy change of the pre-existing argon. So first, the added helium. Well, what's the Gibbs energy of the added helium? It's the number of moles here times RT times the natural logarithm of the pressure of this added helium, 0.4006, divided by P naught. So it's simply this. Again, we're assuming the standard molar Gibbs energy is the same as the standard Gibbs energy of formation for helium, which is just 0 at room temperature. Therefore, this is the absolute value of the Gibbs energy of this small amount of added helium. Now let's look at the change of Gibbs energy for helium and the change of the Gibbs energy for argon. It's here and here. Look at this. We have 0.4 mole of pre-existing helium. This is the pressure change. We have 0.6 moles of argon in the system, and this is the pressure change from 0.6 to 0.4 or 0.5994. So again, there are 3 components: the added helium, the change of the pre-existing helium, the change of the pre-existing argon. We sum it up, we get the finite change of G divided by the finite change of N helium. We get negative 2.2696 kilojoule per mole. This is supposed to be the numerical value of the chemical potential of this helium in the mixture. Now we use the analytical expression of the chemical potential. It's this: mu naught plus RT times the natural logarithm of the partial pressure of helium over P naught. We get negative 2.27144. If you compare these two numbers, well, they differ by a very, very small percentage. And we can even do better by changing this 0.001 to a smaller amount. So here's our second example problem. We will add only 0.00001 mole of helium in the system, 10 to the power of negative 5. And also, we follow the same steps. We calculate the new pressures of helium and argon. We add up the 3 components of the changes in Gibbs energy. We do delta G over delta N. We get this negative 2.27143. Compared to this analytical expression, well, they differ by, I think, less than 0.001%. Again, if we do this numerical calculations by adding a smaller amount of helium, we get more accurate numerical result. So both numerical calculations agree with this analytical expression. And then we will prove this by adding a infinitesimal amount of helium. So we're going to use d sub n, dn here in this same mixture. We'll get this analytical expression in the next video. In this video, we will prove this equation by adding an infinitesimal amount of helium into a gas mixture of helium and argon at constant temperature and pressure condition. The total number of moles of these 2 gases is denoted by uppercase N. N is PV over RT. Assuming the mole fraction of helium is X, then the number of moles of helium and argon are X times N and 1 minus X times N. After we add this infinitesimal amount of helium in the mixture, the amount of helium is Xn plus Dn. The number of moles of these 2 gases becomes this uppercase N. This is the previous number of moles plus Dn. the added amount of helium. The mole fractions of helium and argon change to these two different expressions, and their partial pressures are this times P and this times P. Again, pressure remains unchanged after the addition of the infinitesimal amount of helium. Now let's look at the Gibbs energy change of the entire system. There are three components. We'll calculate the Gibbs energy of the added helium and the changes of the two pre-existing gases. So first, the Gibbs energy of the added helium is this amount of helium, added helium, dN times RT times the logarithm of the pressure of this helium over P naught. What about the change of the Gibbs energy of the pre-existing helium? It's the amount of helium times RT, again times the pressure change, final pressure over initial pressure. Similarly, we get the change of the Gibbs energy of argon with this expression. Now, because the Gibbs energy is additive, we'll just sum up this term, and this term to get the total Gibbs energy change expressed here. We need to simplify this expression. So we're going to use the truncated Taylor expansion of this. The natural logarithm of 1 plus delta is really close to delta when delta is close to 0. And then we can simplify this logarithm to this. We can simplify this further into just the logarithm of x times p over p naught. And we can also simplify this natural logarithm here. It's just dn over x minus dn divided by this uppercase M plus dn. We further simplify the last logarithm over here. So again, we simplify the three logarithms using the truncated Taylor expansion of the natural logarithm of 1 plus delta. So after we do all those mathematical treatment, in the end we have the exact differential of the Gibbs energy of this system to be equal to dN. This is the infinitesimal amount of added helium times RT times the natural logarithm of the mole fraction of helium times P over P naught. And again, we're going to use this equation. Mu is dg over dn. Both dg and dn are infinitesimal. We do the division. In the end, we get RT times the natural logarithm of P helium over P naught. In the analytical expression of mu helium, we should have this mu superscript naught term. This is the standard chemical potential. Why don't we have this? Well, this is simply because we assumed the standard molar Gibbs energy is equal to the standard Gibbs energy of formation, and for helium, these two are just exactly 0. Therefore, mu naught is 0. So over here we have 0 plus RT times this natural logarithm, and the 0 I mentioned is simply this value of mu naught of helium. In this video, we will calculate the chemical potential of a helium gas in a mixture, but under different conditions. We will look at constant temperature and volume condition. So let's assume we have a 1 bar mixture, 0.4 moles of helium, 0.6 moles of argon. We can get their partial pressures, and then we add a very small amount of helium in the system under this constant TV condition. We have this equation as one of the 12 definitions of chemical potential. dA is negative S dt minus PdV plus the sum of mu I dNi. When temperature and volume are constant, these two terms vanish. dA is equal to the sum of mu I dNi, and also dN argon is 0, and then we can numerically calculate mu helium by using the finite change of A divided by the finite change of N sub helium. So after the addition of helium, the partial pressure of helium increases. The partial pressure of argon remains constant. Therefore, we don't have to worry about the Gibbs energy change of this argon. Now, again, we're going to assume the standard molar Gibbs energy is the same as the standard Gibbs energy of formation for convenience. We get a change in Helmholtz energy of the entire system. Delta A is delta G minus delta PV, and delta PV is just delta N of gases times RT. And then we need to look at delta G. Delta G consists of three components. This is the Gibbs energy of the added helium. This is the Gibbs energy change of the pre-existing helium. Plus 0. Why do we plus 0 here? This is the Gibbs energy change of argon. There is no change, so we put 0 here. And finally, minus RT times delta N. Delta N over here, this is the small amount of helium added into the system. We do this numerical calculation, we get this expression. We have delta A over delta N, both are the finite changes. We get a numerical value for the mu of helium. It agrees with the result from the analytical expression over here. Compare this to, they differ by a very small percentage. And the calculation of the chemical potential of helium, assuming the constant TV condition, agree with the calculation assuming the constant TP condition. It does not matter whether we add helium under constant TV condition or under constant TP condition. We verify this same equation of the chemical potential of helium. It's the standard chemical potential of helium plus RT times the natural logarithm of P helium over P naught. Again, this is 0 when we assume the standard molar Gibbs energy is equal to the standard Gibbs energy of formation. In this video, we will derive the chemical potential of helium by adding an infinitesimal amount of helium into a gas mixture under constant temperature and volume condition. So in this equation, the chemical potential of helium is the standard chemical potential of helium plus RT times the natural logarithm of the partial pressure of helium over P naught. Now let's look at the system before mixing. Let's say the total number of moles of the two gases is denoted by uppercase N, N is PV over RT. And then let's assume the mole fraction of helium is X, lowercase. Then the numbers of moles of helium and argon are X times N and 1 minus X times N. After adding this infinitesimal amount of helium in the mixture, the mole fractions of both helium and argon change. They change to these two expressions. This can be easily derived. It's just algebraic operations. The partial pressure of helium changes to this. It's Xn plus Dn over uppercase N times the pressure, but the partial pressure of argon is unchanged under the constant temperature and volume condition. Now let's derive the exact differential of the Helmholtz energy. A is G minus PV, so dA is dG minus dPV, and dPV is simply dN times RT. This dG includes three components: the Gibbs energy of the added helium, the Gibbs energy change of the pre-existing helium, the Gibbs energy change of the pre-existing argon, which is 0. So we combine all those terms and we will be able to get a very simple expression for dA over dN. It's just RT times the natural logarithm of xp over p naught, or RT times the natural logarithm of the partial pressure of helium over P naught. So again, this equation is slightly different from this equation only because we assumed the standard molar Gibbs energy of helium is equal to its standard Gibbs energy of formation. In that case, this standard chemical potential of helium is just 0 at room temperature. Again, under constant TV condition, the analytical expression of the chemical potential is standard chemical potential plus RT times the logarithm of the partial pressure of the gas over P naught. We get this equation under both the constant TP condition and the constant TV condition, both numerically and analytically. In this video, we will prove this equation of chemical potential by adding an infinitesimal amount of helium into a room temperature gas mixture of helium and argon under constant enthalpy and pressure condition. Under constant HP conditions, mu is negative T times delta S over delta N. We're going to use this equation to calculate the entropy change of an ideal gas that undergoes pressure change. The entropy of the added helium relative to its standard state is this. dN is the number of moles of the added helium, and then over here this is simply the partial pressure of the added helium divided by P naught. The absolute value of the entropy of the added helium is thus this relative amount plus the entropy in the standard state. There are two terms. What about the change of the entropy of the pre-existing helium gas? Again, we'll use this equation. We'll use its final pressure over its initial pressure multiplied by negative nr. So we get expression here for the pre-existing helium. Similarly, we get the entropy change for the pre-existing argon. Okay, again, we add this three components together, we get the overall change of the entropy of the entire system. The first two terms are the entropy of the added helium. This term is the entropy change of the pre-existing helium. This is the entropy change of argon. It looks very complicated, and over here we have actually 1, 2, 3, 4 terms. But again, we can just use this approximation to simplify all these terms. For every single term that has logarithm, we'll just use this Taylor expansion of logarithm. As long as delta is very close to 0, the natural logarithm of 1 plus delta is approximately delta. So we can simplify this logarithm and also this logarithm and then this logarithm, and we get the final expression for the exact differential of the entropy of the entire system. It's here. We have only two terms. So again, under constant HP condition, we get the chemical potential of helium by doing negative T times ds over dN. ds comes from here, only two terms. We just plug in those expressions, and then finally we get this expression for the chemical potential of the helium gas. It's RT times the natural logarithm of the partial pressure of helium over P naught minus T times the standard molar entropy of helium. So again, we get this equation, but this looks a little different from the equation we commonly use over here. So what's the difference? You can see this term RT times the natural logarithm of the partial pressure of helium over P naught is exactly the same as this one. So is this equal to the standard chemical potential of helium? The answer is yes. If we assume the standard molar Gibbs energy is the same as the standard Gibbs energy of formation, then the standard molar entropy is H minus G over T, that's simply just 0 for this helium at room temperature. And this part disappears. And also we know the standard chemical potential of helium is 0 if we make this assumption. That means this equation and this equation are essentially the same. We derived this same equation of chemical potential under the constant temperature pressure condition, constant TV condition, and in this video, constant HP condition. Again, the standard chemical potential of helium is 0 if we make this assumption. We can also assume the standard molar Gibbs energy is the standard enthalpy of formation minus temperature times the standard molar entropy. I mean, we can do this as well. This time, this standard molar entropy is only 0 at 0K for a pure crystal. So this is supposed to be positive for the helium gas. But nonetheless, we will end up with the same expression for the chemical potential. So we get this equation, and this part is simply just mu, not helium. Why? The standard chemical potential of helium is again the standard molar Gibbs energy of helium, which is delta H minus T delta S T times the molar entropy. And we get this equation because the enthalpy of formation of helium is 0 when it's in the standard state at room temperature. So in this section 5.9 chemical potential, we have proven actually numerically and analytically this equation, and whether the condition is constant TP, constant TV, or constant HP. The chemical potential may take various forms, but its essence never changes.